It'll be obvious.
So we're going to wait a couple of minutes just for people to drop in, and then we'll start. Let's give it a go. Yep.
Ready to start?
Yep.
Okay, welcome everybody who got up early on the fourth day of the conference. It's a long week, but all the papers are about INSAR, and so it keeps us going. So let's begin this session, which is part 2 of Advances of INSAR Theory. And our first paper is entitled A Novel Multitemporal D-INSAR Phase Unwrapping Algorithm Based on Compressive Sensing and Minimum Cost Flow Techniques. The first author was, or is, Mohammed Yasser. He's not here, so Michele is going to give the talk.
So, good morning. Thank you, Howard, for the introduction, and thank you for coming so early for the first talk. So, I'm going to talk about a new multi-temporal phase unwrapping algorithm for multi-temporal DINSAR approach for the generation of deformation time series. And this approach, this algorithm, has been developed by benefiting from the minimum cost flow technique and the compressive sensing theory. Even if the algorithm has not been developed for any specific multi-temporal approach, we tailor the algorithm on the small baseline subset algorithm. I'm pretty sure that you know the SBAS approach, so I don't need to go in the details of the technique, because we know that SBAS has been presented more or less 20 years ago, has been applied with different SAR systems in different deformation scenarios for different applications. Here we have just a recent example that we produce by processing the Sentinel-1 archive collected over Europe between 2015 and 2019. So SBAS approach in the last 20 years has been validated and tested by exploiting different independent measurements such as GPS or inclinometers or leveling measurements. However, we know that the phase unwrapping procedure still remains one of the most critical procedure in the approach, and by improving the phase unwrapping, we can produce more robust deformation time series. So we work on the phase unwrapping procedure, and we start from the extended minimum cost flow algorithm that is the most largely used phase unwrapping algorithm within SPAS. The idea of the EMCF approach is to implement a cascade of two different phase unwrapping procedures, the temporal phase unwrapping and the spatial phase unwrapping. Both procedures are implemented by using the minimum cost flow approach. In order to carry out the temporal and spatial phase unwrapping, we have to build two different networks. The first one is relevant to the temporal domain. It's implemented in temporal and spatial basin plane. Here on the left graph in the slide. And here each point represents SR acquisition, and each arc represents an interferometric pair. On the right, we have the spatial domain in the azimuth range plane. Here, each point represents a star pixel, and each arc is a phase gradient. So the phase difference between two pixels. In order to select the pixel to be unwrapped, we apply the triangular coherence. In other words, we estimate the coherence by taking into account the residuals within the triangles of the temporal domain network. And we select only the pixel that have coherence larger than a pixel threshold. Since we are using only very coherent pixel, we can assume that we don't have any effect related to bias or similar effect or similar behavior. In this work, we mainly work on the temporal phase unwrapping in order to improve the quality of the temporal phase unwrapping that constrain the spatial domain. To understand what we have done, let's start from a very easy example. It's relevant to tree acquisition, ABC. From these tree acquisition, we can generate three interferograms. And we know that if we are working with unwrapped data or correctly unwrapped data, we don't have any residual within the triangle. Of course, we can translate this simple equation in a matrix formulation. Here we have the whole network in the temporal domain. C represents the matrix of the temporal network, and Q is the number of triangles, M is the number of interferograms. What I have said is correct, is true if we are working with unwrapped data. But if work with wrapped data, this one is not true. In particular, our condition is not equal to 0. But we can include the K vector in order to include the vector, the integer vector, corresponding to the 2 pi multiples that we need to add to the wrapped phase to unwrap the phase. In particular, we have the last equation that I highlight in red. The problem is undersampled because the number of equations corresponding to the number of triangles is smaller than the number of unknowns. So we have an infinite number of solutions. But we can assume to search for the solution that corresponds to the minimum number of 2 pi corrections. This, in other words, corresponds to solve an L0 norm optimization problem. But unfortunately, this problem has no mathematical representation or computationally efficient solution. But we can benefit from the complexity sensing theory to convert the L0 norm problem in a L1 problem. We can do it when our solution, our vector is a sparse vector, when the K vector is a sparse vector. Sparse means, or a vector is sparse when the number of non-zero elements is much smaller than the number of elements of the vector. So if the number of 2π correction is much smaller of the number of interferograms. If this hypothesis is satisfied, we can convert the zero norm optimization problem in a L1 optimization problem. We can solve the L1 problems because we have several algorithms to solve L1 problems and that are also computationally efficient. In our case, we use the iterative reweighted least square approach. So now let's try to understand how we benefited from this technique to improve the extended minimum cost flow algorithm. Here we have the spatial grid. The spatial grid, each arc is a phase gradient between 2 pixels. So let's consider just one arc. We have the phase corresponding to this arc in each interferogram. So we have the phase of each arc in each interferogram. The idea is to solve to unwrap each arc in the temporal domain in order to constrain the subsequent spatial phase unwrapping. In other words, we can use the unwrapped phase in the temporal domain in order to constrain the spatial phase unwrapping, in order to have an input, a starting point for the spatial phase unwrapping. Moreover, from the temporal domain, we can retrieve also a cost function. In particular, in our case, we use an on-off cost function. We assign 1 to the arcs where we are not confident on the quality of the solution. And we assign a very large cost, 100,000, to the arcs where we are confident on the solution. To understand or to decide if the solution is good or not, we use 2 different check functions. In particular, we use the temporal coherence that here I call gamma R&D, and the number of correction that represent the sparsity of the vector. For the arcs where one of these 2 check is not satisfied, the arc is not, we consider the arc not well unwrapped, and we assign the 1 value. In the other case, where both thresholds are satisfied, we assign the large cost. In this way, we can retrieve a cost function for the spatial phase unwrapping. Of course, we can change the 2 thresholds in order to retrieve different cost function. In particular, by changing TH and TH sparse, we can retrieve a different cost function. With different cost function, we can implement a different spatial phase unwrapping. In other words, we can iterate the spatial phase unwrapping in order to have more solution in the spatial domain that we can average, properly average, to retrieve the final solution. Here, in this slide, I represent how we can average the different solutions. So by changing TH sparse, we retrieve different cost function. For each cost function, we have different spatial phase unwrapping. So we have phi1, phi2, phi-n. For each solution, we apply SVD or least square. We retrieve time series, and we can extract, we can compute the phase residuals. Phase residuals represent the error of our system. So from the phase residual, we can retrieve the weights, and the weights with the equation. No, sorry. This equation. That, and the weights can be used for a weighted average of the solution to retrieve the final, more robust result. So now let's move to see some results that we retrieved by processing Sentinel-1 data. In particular, the first data set is relevant to the Monte Etna, that is the largest volcano active volcano in Europe. We process the ULA Sentinel-1 archive collected between 2015 and 2019 from descending orbits. Here we have the results that we achieved from the EMCF and the CS-based phase unwrapping procedure. I'm showing you the mean deformation velocity maps. It's not easy to appreciate the improvement that we achieve by applying the new algorithm, because the EMCF is a well-established algorithm that demonstrated the capability to unwrap multi-temporal DINSAR data. However, if we zoom on the top of the Etna, where we detect the largest deformation, we can see important differences between EMCF and CS-based. In particular, we are considering points with a large coherence, larger than 0.9. With the EMCF, we unwrap more or less 93% of the points that we compute with the triangular coherence. And here we have the results of the CS-based. You can appreciate how, with the new algorithm, we are able to go on the top of the Etna, where the largest deformation has been detected. Of course, we can have a look to the time series to understand how the new algorithm is able to unwrap the data. Here we have points relevant to the western flank of the volcano. I wanted to highlight that Etna is an active volcano that is where several eruptions occurring in this period. But here the most important are relevant to the 2017 and the 2019 eruptions that generate a sequence of seismic events. In the last plot, we have the difference between the two solutions. We can appreciate how the new procedure is able to detect around 3-4 centimeter jump of 3-4 centimeter in corresponding of the 2018 and 2019 volcanic activities. I want also to highlight that we improve the coherence from 0.8 for the EMCF and 0.9 for the CS-based solution. Here we have another point relevant to the eastern flank of the Etna. In this case, the main unwrapping errors are relevant to the 2017 eruption. In this case, we lost more or less 6 centimeters with the EMCF procedure, and the coherence also in this case increased from 0.8 to 0.9. Another point, in this case, we have several unwrapping errors, mainly in corresponding of the 2019 eruption, and also in this case, the coherence increased from 0.86 to 0.9. So we understood that the algorithm, the new algorithm, is able to preserve the capability of the EMCF approach to unwrap very large data, so to unwrap very large areas. However, the new approach is able also to better tackle very large nonlinear deformation signal, in particular when in corresponding of volcanic unrest or earthquakes or this kind of deformation that usually are very, very hard to be managed by phase unwrapping techniques. In order to stress the capability of the algorithm to work with nonlinear deformation signals, we process the Stromboli area. Stromboli is a very small volcanic island located in Mediterranean, and is interested by very strong deformation related to the activity, volcanic activity. Also in this case, we process the Sending Sentinel-1 dataset acquired from 2016 to 2021. So let's go faster. Here we have the two results relevant to CS EMCF. Also in this case, we cannot appreciate in this figure the improvement, but if we zoom in the Sciara del Fuoco is a sliding area located in the northern flank of the volcano, we can see the improvement that we achieve with the new algorithm, in particular along the edge of the Sciara, in the middle of the Sciara. All the points, the more or less 200 points that we retrieve are located in this area. And if we have a look to the time series, we can see how the volcanic activity that occurred in 2019 generated a very strongly nonlinear pattern that is not detected by the EMCF, but is detected by the new approach. In particular, in this case, we correct more than 10 centimeters of deformation for a total deformation about 20 centimeters. More interesting, if we have a look in the middle of the Sciara, where the total deformation exceeds 40 centimeters, also in this case, we correct a jump about 20 centimeters in corresponding to the 2019 activity. And this nonlinear behavior cannot be detected with the EMCF. So I have concluded, and thank you very much for your attention. That's all.
Thank you. We have time for one quick question. Do I see a question? Charlie.
What do you think is the influence of the phase closure discussions that we've had earlier on phase unwrapping?
Here, the phase closure is not a problem because we are considering only points that don't have residuals within the triangles. So we don't have residual because only very points with very high coherence, triangular coherence, has been considered. So we don't have effect. No, multi-look. So in theory, there are pixels that are affected by bias or this behavior, but are not considered in the phase unwrapping because, sorry, I go fast. Okay, here. Only 0.9 or larger coherence points are considered.
Okay, thank you very much. We'll move on with the next talk. So this talk was about getting more pixels, and now we're going to get rid of pixels. But the fortunate thing is that these are decorrelated pixels. And this talk will be given by Howard Zepker.
Thanks, Ramon. Okay, so what I'd like to talk to you about today is essentially how we are trying to cope with the coming true onslaught of large amounts of data. So, here in Europe, there's going to be follow-ons to Sentinel-1, there's going to be Roselle, there's going to be Harmony, there's going to, the whole list that we've seen. In the US, we have the NISAR mission launching next year. There's going to be a great deal of data coming, and at least in the US, we're thinking of going to future concepts where we might have whole constellations of satellites that are interrogating the Earth every 6 hours rather than every 12 days. So we really need to have a way to deal with these large amounts of data, and it is already impossible for any one of us to look at maybe you're doing a study that uses 5,000 interferograms. You can't go through and fix all the little things in each one. Especially if you're looking at lots and lots of baselines together to do SBAS calculations or whatever. I mean, the volumes are really, really large. And so we need to have a way to do this in an automated way where we don't have to interact very often at all with the system, and it spits out high enough level data products that these are useful for being applied in a number of different ways. One flip answer to this is, we're just going to dump it all into machine learning and it'll sort it all out. Well, I hope that that's where we get someday. We're not really quite ready for that. So what I tell people is that one of my future students is going to tackle that problem. In the meantime, we're going to try to do it in a more conventional way. So we're talking really here, even though the paper is a scientific result that is stated, what we're really talking about is the engineering problem for exactly how to do this. And so basically, how do we make INSAR time series that are can be generated routinely and people don't have to interact with it, and that the results are robust and can go along in a reasonable trade-off of quality and speed. So the innovation here is less on the individual steps in doing this. We've seen a lot of good papers on these things, in fact, already in this year's FRINGE meeting. But we basically have put together these pieces that already exist into an overall data flow that includes developments from the last 25 years, and everything will work together in a nice harmonious way to generate the data that we want. And hopefully we will integrate this into packages such as the ICE package that's being developed at JPL, and we hope that it gets enough notice to make it into some of the other processing packages that many of us use. So the data flow at the very high level looks something like this. You can start with either L0 or L1 products. We actually prefer to start with L0 products in many cases for a variety of reasons, but there's no reason you can't start with level 1 data and go through the same thing. But essentially what we do is we generate geocoded versions of the single look complex images. Then we go through a PS filtering and interpolation step, which I'll get a little bit more detail into. And then it goes into the usual phase unwrapping and atmosphere removal and SBAS for the time series, and then comes out with a result that is a time sequence of deformation across whatever the size of the scene is that we're doing. I'm not going to read all of these, but the details, as I said before, is that we start out with these level 0 products. We're using typically a PS filtering step, but you don't have to do that if you don't want to, but I'm going to show that it actually helps us in a couple of cases. We simply use snafu with, as it comes out of the box to do the phase unwrapping. You just heard other approaches to that even in the previous talk. You can stick in whatever that you want. For the atmosphere removal, there's been a number of discussions about that. There's lots of ways to use different models and so on and so forth, but we actually find that it works as well to simply do regression versus height of the unwrapped phases. And all these different algorithms, they all get rid of half the noise and half the noise stays. It may be a different half each time, but the overall result is always about the same. And then we know SBAS and everything is unweighted because that way we don't have to worry about a way to calculate the weights. So the way that we are doing our PS step, I'm going to spend a couple slides on that because not everybody may be familiar with the algorithm that we're using. It's fairly recent. But we start out by using an MLE criterion to pick the PS points, and we overselect on purpose. So here's a region in California's Central Valley. It doesn't really matter. That's why there's no labels on the image. But every white pixel is one that has been above a threshold for the maximum likelihood estimator. Again, the threshold is set low, and we know that we have many, many points here that are not true PS points. And so what we do then is that we send those to a cosine similarity measure, which goes through and makes sure that every one of the ones that we flagged was actually a PS. So as you can see, this has got a lot less white than it did before, but it still maintains quite a few of them. So we've gotten rid of all the false positives, and then we apply the cosine similarity again to all the unflagged points in here and fill in the remaining points that actually seem to be PSs. And we end up with an image that looks something like this. And given that this is an agricultural area, it actually fills in quite a bit. And then we take these individual points, and for everything that remains black in here, we interpolate given all the other points in the image. So we end up with continuous coverage. And if you do that, you get an image that looks something like this. It's the same area that we had before, and it's it's a subsidence bowl in the Central Valley. And in this particular case, the scale here is in terms of radians per day, and if you convert that to centimeters, you'll get what you get, but it matches reasonably well. We'll talk about that in a minute. And I also showed on here the location of GPS stations in this area, essentially to show that there are GPS stations in a lot of places, but they're not, as always, they're never exactly where you want them, and they're not particularly dense, and so we have the map from INSAR, which is much more dense spatially than what we had before. And if you take the ones that I saw there and that you saw labeled, we can look at a result of a derived time series here. So this is this is about 4 years worth of data. Shown here in green are the PS solutions. In red are the conventional SBAS only solutions, and then the dotted black lines are the GPS. They look like they're pretty comparable here, but we can make a little chart of what the RMS error is at every one of those GPS sites. And for the most part, the ones that have gone through this PS filtering have a fraction of the error than we got in the conventional SBAS. So this seems to be preserving some pretty good quality. Again, we remove the atmosphere simply through a elevation regression. I mean, I chose an example here from Hawaii because there's a lot of elevation change, and so it's a very easy plot. We just assume that it's linear, fit a line, subtract that everywhere, and that becomes the atmosphere-corrected image. Like I said, it gets rid of about half of the atmosphere. As an example of that, on the left are the raw interferograms over a variety of different periods. Once they go through, then that atmospheric correction, you get what you have on the right, and it's much more clear where you do have the deformation along the volcanically active area in the lower part on the right-hand side of the image. But basically, it's blue everywhere else, so it's done quite a good job of removing the noise from the atmosphere. So let's look at two other examples. One is measurement of the creep rate along the San Andreas Fault in California, and the other is subsidence due to water withdrawal in an aquifer in Texas. And the goal for this one, it's an area that is pretty highly decorrelated because of the amount of vegetation in the area. And there's a poster over in the poster area describing more details of the water withdrawal problem that we had here. So here are the maps. San Andreas Fault is in California, for those of you who are less familiar with that. The specific example for the aquifer, it's in Texas. Texas is a big state, but it's a pretty big aquifer. So here's two different solutions. On the left is what we see in the conventional SBAS solution, and on the right is what we get from using the PS one. And we'll look at it in a little bit more detail in a moment, but it's much more clear, at least to me, because maybe I know what I'm trying to look for, that you really see the San Andreas Fault creeping section stand out quite well here. And it's hard to pick that out when you look at just the SBAS one. So the combined method is really doing quite a good job of isolating the real signal because we've thrown out all the pixels that add decorrelation. Here that is blown up a little bit again to show and highlight this creeping section that runs from a town called San Juan Bautista in the north down through another town called Parkfield in the south. Well, we can measure, if we assume that all the displacement that we measure is due to right lateral slip rates, which is a pretty good model for the large scale part of the San Andreas Fault, then we can get a fairly dense long track measurement of what the slip rate is in terms of centimeters per year. Now the average rate across the San Andreas Fault in this region in California over very long scales is closer to 2 to 3 centimeters per year. We're getting places where it has 5 centimeters, but that could be either that there are little bits and pieces that are moving episodically, or there could be some vertical motion and we've assumed everything is in the plane And so that could be overestimating it. But the point here is that these points are actually pretty dense with latitude. And if you look here, there's a combination of, on the left, the white boxes show where we made those measurements. We just draw a little box around the fault, and you average on one side of the box and the other side of the box, and you plot that what was plotted in the point there. On the right are the GPS sites along this area. And there's not many parts of the world that are as instrumented as the San Andreas Fault. And you can see that our measurements are already much, much denser than is obtained from the GPS system. Just one slide on the aquifer region. The top is the SBAS solution. Something that you could convince yourself is a subsidence bowl, but in fact, that's almost generated entirely by phase unwrapping errors in the SBAS solution. If you apply the PS filter and go through the data flow, you see something on the bottom, which I guess you'll have to take my word for it, but it's much more plausible given the watering records and such in this area. So in conclusion, I think that we have a pretty robust system. We basically give it a list, a latitude and longitude, and say all the data from 2017 to 2021. It spits out the time series, and they seem to match pretty well with what we know. You can run this standalone. You can integrate it within other processing packages. Probably all the pieces are in every one of the packages that you use, and so it's just a matter of writing the right Python script that runs things in order. But you don't have to fiddle with any parameters. It just goes. The performance is quite good in many cases. It's a finer spatial result, of course, than we get with GPS. The routine application, again, without any tuning, works quite well in highly decorrelated areas, which is what we tried to show with that image over the aquifer. It would be interesting, and I think in the future, to develop some context-sensitive parameter tuning. We don't do any of that now, but again, here's where places like some kind of artificial intelligence may be able to look at your data and say, well, you really want that threshold to be 0.85 instead of 0.8. Maybe that's a good thing. And so if you have a large enough data set, we may be able to learn enough to be able to feed these more automatic models that will, again, require less and less individual persons interaction. So I will pause there, and I'm happy to take any questions.
Okay, thank you very much, Howard. Yeah, we have time for questions. Sang Ho here.
Thank you so much for your presentation. You lumped the atmosphere into regression, and that seems to solve everything. But we know that sometimes it's positively, sometimes negatively correlated with topography. And you showed us an example of Kilauea where it's mostly one side, so it's bounded by the mountain range. Could you elaborate a little more on the regression of what you did?
Well, the regression is just a regression. So basically, at some step, we have all the unwrapped interferograms. So for every unwrapped interferogram, we simply plot on the x-axis, the height, and on the y-axis, the unwrapped phase. We fit a line, and we subtract that everywhere. So we don't really think about it beyond that. So it's most obvious in a place like Hawaii where you have the tall mountains, so there's a big elevation change. This was actually applied in that San Antonio data as well, which is flat. And so since there's no change in elevation, it doesn't even really matter what the phases are. It just doesn't try to apply a correction. So all it can correct for is the stratified component of the wet troposphere. And that's what gets corrected. And I made a pretty flip statement in that there's lots of different corrections, and they all get rid of half the noise, and they leave half the noise. And that's kind of what our experience is here. If you have a better algorithm, as I say, this is modular. You can pull out what we're doing, which is simple, and put in what you want, as long as you don't have to interact with it. So that is really the key in that, again, if you are generating 7,000 interferograms, you're not going to go in and solve each one of those independently.
Other questions?
Yes, first a comment to what First, a comment to what Sangho was saying regarding regression with topography. I've seen in certain volcanoes where you will lose in a time series, half your true amplitude if you do that. So it must be used, I think, with caution. But my question is, or concern was, like in the Central Valley, if you're filling in big holes with this cosine interpolation, I guess I have two things that concern me. One is, what information are you truly getting in these big holes? Because the deformation there can be somewhat heterogeneous, even if in broad scale you get these large subsidence bowls. And so it just seems that you're kind of trying to add information where you really don't have it. And either you need a better sensor that can fill in, or just ignore it, because that's one case, but you may have other cases where you either have no idea what the functionality of the signal might be, or there might be more complex signals, and then you're kind of inventing something. So.
Yeah, okay, so that's a good point. Let's do the second half of what you said, because we addressed Sangho's already. But I take the note of caution. It is true that the only place where we have reliable measurements are at the PS points. Now, we happen to have a lot of PS points, but those are where the only places where we know the data. The system does spit out that mask, so you can look at that. And so when you have a hole in between, it is simply interpolated from what we do. We pick between 20 and 50 nearby PS points, and then we fit some kind of a weighted average to that based on the distance. So if you have deformation between those big points that are not adequately sampled with a PS point, yes, you won't see it. So you're stuck making a best guess. So you could just multiply the output data by the PS mask and say, here's where I believe the data, and we'll just ignore the rest of it. But we all have many, many analysis routines for working on spatially continuous data. And you just plug this into those same codes that you have, and whatever you're doing for your analysis will run. That doesn't mean it's going to be right, but it's going to run and probably not crash. So you're correct. We're not generating any kind of information that isn't already there. Now, what you can do, if you want to fiddle with it, you can lower the PS threshold a little bit, and it'll find a few more points. Those will be there. They'll be not as rock solid as the ones that we're using, but maybe that's a reasonable trade-off as well. Again, our goal was to do something that works most of the time and produces reasonable results. It's never going to be the best result that you could get from going in and hand-tuning all of your stuff. I mean, I guess, so it's a question of what we're trying to accomplish, I think.
Yeah. Thank you very much, Howard. I think we need to move on. So the next presentation will be given by Carlos Lopez Martinez. And it's called the Reinterpretation of Temporal INSAR Coherence for Multitemporal SAR and Polarimetric SAR Data Classification.
Thank you, Ramon, for the introduction. Okay, so we're going to switch a bit topic here. So I'm going to present a little piece of work on how to reinterpret temporal coherence, and we will use classification here just as a tool to show the changes or what we observe in this case of reinterpretation. So this is the outline of the talk. So I invite those of you interested into the technical details that I will skip on the presentation to go to this paper we presented last year, where you have all the details. So basically, which is the context of this presentation. So when facing the analysis of temporal series, we ask ourselves, what is the temporal information, or where are the changes, or where we could identify changes? So we can identify changes on the temporal series of intensities, or in case of polarimetry, in the temporal series of covariance or coherency matrix. But in repeat SAR interferometry, we have also temporal information in coherence. Of course, this coherence depends on the targets, but has a little problem that we cannot use it when the coherence is very low. We have many scenarios where this happens: low temporal coherence, long temporal baselines, strong weather effects. So the goal here is to try to extract information from low coherence, but from our point, or philosophically, we wanted to try to find a mathematical network that may connect both sources of information to detect changes. So the theory is pretty simple. Here you have the classical expression of coherence. So it's very easy to decompose this coherence into two terms we call a symmetric term, which is in essence the classical coherence under the assumption of no radiometric changes. So there are, in the case of interferometry or single-dimensional data, there are no changes in the intensity. So this is basically, this plays the role of the classical coherence. You can find the different multiplicative terms that affect that symmetric term. And we have a second term, what we call asymmetric term, which basically accounts for the departure of this symmetric assumption. Basically, this asymmetric term is the ratio between the arithmetic mean and the geometric mean of SAR images, and it's very nice and very simple to demonstrate that this term contains the same information as the ratio of intensities that many of us, we use it to detect changes in temporal series. Here you have the expression that relates both of the things, and the most important thing is that the range of value of the asymmetric terms goes between 1 and infinity. So if we take the inverse as a side product, we can have a bounded term that can be used to detect changes between 0 and 1. So we are not, we don't have to face with infinities in detecting changes. We have a term very simple to detect changes between 0 and 1. So we are facing some scenarios. When there are no coherent changes, there are no radiometric changes, coherence is equal to 1. So life is easy. When we have only coherence changes, we turn out to be in the classical coherence. But when we have both coherent changes and radiometric changes, we have two situations. Case number 3 is what we call high coherence scenarios. So this is the most general case. You have radiometric changes, coherent changes, you cannot differentiate them. But when we are in low coherence scenarios, the symmetric term that basically goes to the classical coherence goes to 0. This will cancel the whole equation of coherence, but we can observe that we can still get information from the asymmetric term, which basically contains the information departing from the symmetric assumption. So basically, this very simple piece of theory allows us to connect the changes that we can detect from coherence and the terms we can, or the changes we can detect from changes in radiometry. So at the end, we are able to combine the two sources of changes under the same mathematical framework. And as I said before, we have this asymmetric term that can be used to extract information of changes for low or even very low coherence scenarios. What happens if we add polarimetry? The advantage of polarimetry is it doesn't, when we apply polarimetry, we can extend the idea when we can still separate coherence, the Pauline-Sarr coherence into two terms, but the advantage of polarimetry is that we can optimize. In this particular case, the symmetric assumption refers to polarimetric scattering mechanisms, not only to intensity. So if we apply optimization, the optimization of the symmetric term is the classical Pauline-Sarr optimization, but we can also optimize the asymmetric term. And again, it is possible to demonstrate that this asymmetric term is related, in this case, with the polarization optimization ratio, which is used to, with polarimetry, to increase the separability of targets, if you want. Again, it's very easy to demonstrate that both are related, but in this case, as we have polarimetry, we have 3 optimum terms. We have 3 asymmetric terms due to the polarimetric diversity. Again, we have also shown, or in polarimetry, or when we talk with, when we work with multidimensional data, we have also the concept of distances between matrices. I mean, you have the geometric distance, the symmetric revision, which are dissimilarity, the likelihood ratio that are able that used to distinguish targets. So basically, this theory allows to decompose this distance measure into 3 components. So at the moment, we don't really know the consequences of this decomposition in terms of the distances, because still we haven't worked on that piece of work. Okay, we wanted just to show that somehow this decomposition of the coherence can be also related with the concept of distance, and we can separate it. We can decompose it at the end. So in order to show the information content of these terms, we will use classification. But bear in mind that here, we don't really care about classification. For us, classification is just a tool to show the information content. So we are using 3 data sets. First, a UAV SAR data set at L1, a temporal series of 5 images that refer to a high temporal coherence scenario, a low temporal coherence scenario in which we have 8 pulsar images with Riddersat-2 in the Netherlands, in Flevoland, and finally, we also apply that to Sentinel-1 data. In this case, we have 32 images, dual pole over Barcelona, in Spain. And in this case, it's a mixed coherence scenario. So here are the data, 2 data of the data set, together with the ground truth for classification, so we can compare against a ground truth. So here is how the things look like. So on the top, you have the classical coherence. On the middle, you have these asymmetric terms. And on the bottom, you have the optimized value. On the right, what you have is all these values considered into the complete temporal series. So on the rows on the top, on the 3 row tops, you have the classical polarimetric coherence, and on the bottom, you have the optimized values. So as you can see, the 3 rows on the top and 3 rows on the bottom, they have different information, but we cannot really distinguish, or we cannot say that one is much better to the other to detect changes, because in this case, we are in a high coherence scenario. Nevertheless, if we go to a low coherence scenario, in this case, it's the Netherlands test site, the Riddersat-2. If you go to the right and you look at the coherences on the 3 rows on the top, and you look at the ranges of coherence, you see that you cannot distinguish anything because the values are very low. Nevertheless, if we go to the optimized asymmetric terms, you see that in that case you can see a lot of difference. So in this case, if you take a look to the coherences, they are very low. So you cannot obtain anything. Nevertheless, if you go to the case of these asymmetric terms or to the optimized values, automatically you get a lot of information in a low coherence scenario. For the Sentinel-1 case, in here the information is arranged differently on the columns, in the 2 first columns in each case for different classes, okay? You have the coherences. Coherences are in some cases low, in some cases high, but if we move to these asymmetric terms and the optimized asymmetric terms, you see that you can be much more sensitive to changes between the images. So how do we use this to demonstrate the information content? Again, we use classification. In this particular case, we use a recurrent neural network. Recurrent in order to take into account, it's a convolutional neural network that it's recurrent in time, so we can take both into account space and time. So here are the classification results. The picture shows the classification results considering only coherences on the left. So you see that the overall classification accuracy is about 60%. Remember, this is a high coherence. But if we use the optimized coherence values, we increase the overall accuracy to 80%. On the right, you see the confusion matrices, and you see that with the optimized values of the asymmetric term, the confusion matrix is just much more clear. Just for reference, I present here which are the classification results using the intensities, and on the right T3, all the information we have, okay? So it's just as a reference. Of course, with the coherences, we don't have access to the intensity, so we cannot achieve those numbers. But at least in a high coherence scenario, we can see that this asymmetric term includes more information. What happens if we go to a low coherency scenario? The change is higher. In this case, if we use the coherencies, remember again, this is a low coherency scenario, you obtain an overall classification accuracy of about 35%. If we move to the optimized, we increase up to 85%. So the change is dramatic in this case, and it is shown, it's clearly shown in the confusion matrix. So as you can see, in low coherency scenario, this new asymmetric term is able to better differentiate the classes. But remember, the pictures are only classified results with the coherencies and the optimized asymmetric term. Again, for comparison, we present the results with the intensity and with the full polarimetric information in this case, and in those cases, the classification is about 88%. So as you can see, this new term, I mean, of course, it doesn't beat the classification accuracy with the full information, but it's not really far. It's just about 4 or 5% far from those numbers. We go now to Sentinel. In here, and there is, we have also dual polarimetric, dual polarization, and the important message here is that in this case, despite we don't have fully polarimetric information, we can still optimize with dual pole, because in this case, the polarization is just a mathematical treatment, and we don't care about the scattering mechanisms. So in this case, we are still studying what happens with dual pole with Sentinel, but still in this case, we see that these asymmetric terms improve the classification accuracy. So also in this case, bear in mind that it's a mixed scenario, it's a low coherence, high coherence, so we have still to study the implications of this coherence. But still, in Sentinel-1, we can improve the extraction of temporal information. So just to close, we have presented here a new interpretation of the temporal coherence. So we have two terms, a symmetric term that basically takes into account the coherent changes under the symmetric assumption that no radiometric changes. We have a second asymmetric term, which basically accounts for the departure of this symmetric assumption. We have seen that this asymmetric term is especially useful when we face low coherence scenarios. So in our group, we are still not aware of the implication of the asymmetric term. We just use classification to see the information content. So there are many other applications where we could apply this technique. Okay? The usefulness of this term, we have proved it quantitatively. In terms of classification, we have seen that in some scenarios, low coherence scenarios, we can improve classification by 50%. In high coherence scenario, the improvement is not that high, but still we have been able to demonstrate that you can obtain improvements of about 20%. So this is the end of my talk, and now I'm open for questions. Thank you very much.
Thank you, Carlos. So we have time for a couple questions. I know, on Thursday, it's hard to think of new questions.
Thank you, Carlos, for a very good presentation. So I have two questions.
Speak up a little bit.
Okay, a little bit. Okay, so I have two questions. So the first question is, you told us that you're using the temporal coherence with the polarimetric information. You can decompose into components, symmetries, and asymmetries. So the first question is it possible to get the same result if we combine in a certain kind of covariant matrix with a bit?
Could you repeat
so
that?
We combine two components with temporals and polarimetrics to put it into the big covariant matrix and then decompose it in a certain kind of Koranacker products and get the first component and the second components. Can we get that similar performance or no? That's the first question.
I don't know. I cannot really answer that part because we have just established the mathematical framework and we are now going into the implications of that. So there are many, even me, I have a lot of open questions still to answer. So.
Okay, thank you. That's the first question. The second question is about the closure phase. So you study about the temporal coherence. So basically, we have the time series data. So did you try to use in the phase closure to predict something? If there any expected to improve the performance for classification, if we include the phase closure in your procedure? No.
No, no. It's
Is
just
there any
preliminary
expectation to
result.
improve or not?
No, I don't have that answer.
Okay. Okay, thank you.
Time for one more? I have a real quick one. It's a nitpick, but the asymmetric correlation, I notice, is defined such that its inverse goes from 0 to 1, but correlations always go from 0 to 1. So is there any reason that you didn't define it as 1 over your quantity, and then you'd have two correlations that both went from 0 to 1?
Sorry, repeat again.
The asymmetric correlation that we're talking about, the range is essentially from 0 to infinity.
Yeah.
If you took 1 over that, then you'd have a correlation that goes from 0 to 1, which is more conventional with what we usually think of as correlations. Did I miss that?
That's what I said. I mean, this is a side product. Here, I mean, if you take the inverse of the asymmetric term, it's a coherence-like term.
Oh, okay, and you want to call it, okay.
Yeah, I mean-
Anyway, if you're going to call it a row, that's why I got confused, because I assumed
Okay.
rows went between 0 to 1. Anyway, like I said, it's a nitpick.
Okay.
All right, thank you. All right. Let's move on to the last talk. It is entitled "A Generic Noise Model for INSAR Time Series Based on Stepwise Error Propagation," and Sami Esfahani will be giving the talk.
Thank you, Howard. Good morning, everyone. My talk today is about noise modeling in INSAR stacks. And I want to start with FRINGE 2021 recommendations. And if you look at the document, you see one of the recommendations that communicate regarding communicating results and their uncertainties. There are two recommendations, key recommendations. One is a standardization of output products, and one is to provide error bars and easy to understand statistics with final results of the formation time series. And this talk is actually regarding both of them, mainly the second one. Why we need a noise model? Of course, it is clear, but just to review, proper quality description. Actually, we want to know how large or how wide should be the error bars. Proper weighting in geomodeling and data integration. We want to give a weight to our data, so we want to know how precise they are compared to other data and their weights in the geomodeling. Proper noise filtering. If we want to separate noise from signal, then we should know statistics and about the noise to separate it from the signal. And proper interpretation to decide what we see is a signal or it is a noise. Just very simple example. At the end of presentation, I will come back to that. Here we see a time series. All the trends and linear velocity are removed already. And here we see some ups and downs in order of 5 millimeter in this time series. Is this the formation or this is noise or correlated noise actually? Or in space, I have the one simulated interferogram here, but you see in the center something around 10 or a little bit more than 10 millimeter subsiding. This is noise or this is signal. We need noise model if we want to have these kind of decisions, especially when we go to localize the formation and these localized applications. There are two aspects of quality: precision, accuracy. Precision, what is the dispersion around the mean? How wide should be the error bars? And accuracy, how close are the measurements to their true value? Regarding INSAR, the main part of accuracy is mainly because of unwrapping errors. In this talk, we're not talking about unwrapping errors and accuracy. We are mainly talking about noise models and precision. There is a poster number 83 if you want to follow about accuracy and quality of phase unwrapping. There are already good body of knowledge on noise components in INSAR. A lot of papers, I just mentioned a couple of them in this slide. Coherence affected noise, it means all the scattering, the correlation, thermal noise, co-registration noise, everything that affects the coherence. Atmospheric noise, coherence affected and atmospheric noise in the time series. Plenty of papers and studies. But are these models representative for final INSAR time series and products delivered by different algorithms and softwares? I think no. Why processing in this noise? There are different spatial or temporal filtering steps, reduce the noise magnitude, it's noise reduction we have, and different spatial and temporal filtering steps alters the noise structure, not only magnitude of the noise, but noise structure. Here, just very simple, purely white noise, uncorrelated, blue ones. With moving average, we filter that, it's smooth, but this smooth signal, it is just noise. It's already purely noise that is now, the variance of that is smaller, but now it is correlated, it's smooth. And our eyes usually try to interpret this smooth signal, smooth noise as a signal. So because of this processing in between, these currently available noise models is not representative for the final products that we have from the software. The noise structure of final time series is dependent on different factors, scattering characteristic of the targets, atmospheric delay, heterogeneity via atmospheric noise models, data characteristics, multi-looking factor, number of acquisition, revisit time, type of the deformation that we are looking at, and the special temporal behavior of that. The kernels that we use in the space or time for filtering, they affect the final noise, and distribution location of targets that you use for this kind of filterings and interpolation. So we need some generic noise model to account for all these factors together and in an easy-to-use way. Our rationale here to use error propagation, uncertainty propagation, we have from our already knowledge about atmospheric and scattering, all these models, the noise of the initial INSAR products, and then through processing, we want to propagate it to the noise structure of the processing INSAR results. It is complex, we have a large amount of data, there are different processing strategies between different softwares, we want to be generic as much as possible, and let's see how we want to do that. And because of the large data, the goal is finally to have one analytical closed form expression that to construct variance covariances for any set of observations that we want. Because if we want to make one variance covariance matrix for all our points in all time series, a huge matrix we cannot use with that, use that. But if we can make some expression that for any set of points or one time series or set of points in one interferogram, we can make then variance covariance matrix, then that's actually a goal here. So steps, we first exploit the existing body of knowledge about INSAR noise source to propagate errors through the interferogram generation. It means from SLCs to statistics of interferograms, and then further error propagation in the filtering steps. We formulate our mathematical model is based on prediction theory, called it least square collocation, or in signal processing Wiener filtering. It is generic, it can cover different existing methodologies, it's flexible, it can digest different kind of assumptions and kernels and different noise components in it. And it is simple, it is linear, so we can use linear error propagation for final quality. Generic functional, the mathematical model that we have, we put here Y vector is not necessarily time series. It can be time series, it can be set of points in different interferograms, it can be a spatiotemporal data set. In generic form, Rx is our functional model. Any trend or anything that we estimate from data like velocity or spatial trends. S, unmodeled deformation, something that we cannot model, but maybe we can model it stochastically. Atmospheric signal, and all other noise components, coherence-based noise components. And the final covariance matrix of this vector Y, it is the summation of variance covariance matrix of unmodeled deformation S, atmospheric A, and Qn, that is the noise components. Then in the filtering step, we want to compute something else. We want to use this y computing something else. That something else, I call it z here. So z is something that we want to derive. So the z also decomposed in two parts. One deterministic part that is Azx, it's our functional model, trend, velocity, whatever. And Sz is unmodeled deformation. We want finally the deformation time series or deformation product. So all deformation is there. Okay, if this is the construction of the model, then in two steps we can solve it. First, we can use solve for x using least squares. I put it in the most generic form. The weight matrix can be whatever user decides. So it is not one particular kind of least squares. Generic form of least squares, we estimate x. And then step two, we can predict actually z. And if we combine these two equations, finally, we see that the z that we derive, it is a one linear relationship of y. I don't want to go to details here, but I want you to get the concept that if we can formulate everything as a linear relationship of each other, then we can easily do error propagation later. So if we have this matrix F, then we can simply propagate variance covariance matrix of y to Qz. But how to get Qy? The existing body of knowledge that I already told about atmosphering, about the scattering noise, about the deformation patterns that we have in the area. This is the big question, how to get it. I will come back to that later. But if we have this, now the question is how to propagate this in the processing chain. Challenges of full propagation is that we have some steps in time domain, some filtering in the time series. Then we have some filtering in the space domain. So somehow we should connect these two in the error propagation if we want to apply error propagation, merging these temporal and spatial models together. What we do is we first, usually this filtering in most of the algorithms are based on the two steps. One, they apply high-pass filter in time domain and over points, or some set of points. I call it set n, initial points. Then they apply some low-pass filter in the space domain to separate low-frequency signal in space, mainly atmospheric noise. Then interpolate this atmospheric noise on other points. We call it set p. And then apply correction of this set p. And finally, have a filtered time series or products on set P. If you want to do it in a mathematical way, I'm going very fast. Again, the point is not going to the details of these equations. The point is to see how we convert everything in a linear form finally. So if we, in the time, for each time series, we have this model, then based on the model that I already told, we can estimate x, and then we can estimate high frequency signals that compose noise and atmosphere. And then we can write everything again in a linear form based on our initial observation yi, the equation bottom of the slide. This is just for one time series. If we have m number of points in this initial set n, then we can put all these vectors in one vector, and this operation become like this. There are big matrices, but it's possible to handle with that. And again, this final high frequency components En in the bottom, it is a linear relationship, a linear function of the observation that we have in the star. Then we go in the space domain. Then in the space domain, these vectors that we already get from time domain, this En, now we can pick one of them, for example, for kite, in the interferogram K or some other interferogram, and then write some model in a space domain. That B here is the trend or special trend for Unisphere or whatever trend that we have in a space. AK and NK is the components of atmosphere and noise in the K component. Then we can do again the same filtering approach. Here also, there are some kernels involved also in time. I forgot to say there are here the vector L is a kernel in a space. Also we have another kernel in time K. Then again here we can write in each interferogram the estimated low frequency corrections, that is mainly atmosphere, as a linear relationship to En. But this En, it is for En is for all the time series in all the interprograms. En with K is only for K interprogram. So we need somehow to connect these two. So we have a selection matrix here, SK, that it can connect the K components from all the time series and it put it in the one vector, become EK. So with this SK or selection matrix, then we can actually write the final correction as the linear component of the first vector that is all the time series in one vector. Now, if in two different interprograms we want to correct for this term, we should subtract the initial observations from the corrections that we get. That is the linear relation to the initial observations in the point N. Just I want to emphasize here the correction is over the pixels in the set P, and the N is the initial points that we use for interpolation. So they can be the same, but not necessarily. So the final precision of the filter phase that we get from this equation is it is the dispersion of the error in the dispersion of the remaining noise in the data. So initial noise that we have was this E components. Now we have the correction that is F multiplied by Y. So if we subtract these two from each other, it's the remaining noise in the final INSAR time series or INSAR in each INSAR points in each interprograms. And here again, you see that we can write it in a linear form from the original observations, and then simply we can write this error propagation and come up with the final equations. In these final equations, the first one, with the first one, we can compute the variance of any target in any interprogram. With the second one, we can compute the covariance between any two phase values in the time and space domain. Two phases in time, two phases in space. In one phase in one interprogram with another phase of another point in another interprogram. All the correlations are there. So with these two equations, actually we can reconstruct whatever we want for the final noise components. And these F matrices here captures all the filtering settings, types of the kernels, location of the points, functional models that we use. And this Q matrices captures all the initial noise structures and effects of pre-processing. For example, how phase linking convert coherence matrices to covariance matrix of the final stack. So everything is there, multi-looking is there, functional models are there. So all components that we have are either in this F or Q matrices, you can find them. Just to check the validity of the final equations, we simulate very simple scenario. We simulate also different noise components, and we use our proposed analytical closed form equation to find out the covariance matrix. So I call it A here. Also, we have empirical covariance matrix by producing 1,000 realization of the noise and do the same processing all 1,000 realizations and get the empirical covariance matrix. And when we look at these two final covariance matrices are very similar, and actually it validated the equation, at least the propagation is correct. In this simulation also it is nice this is a very good tool to that show us what is the effect of different processing steps or different settings that we have in the final solutions that we get. Here there are 4 points, and in the 4 time series, in the right also you get the covariance matrix of 4 time series. And there are 2 covariance matrices, before filtering, after filtering. You see that before filtering we have higher variances, but with filtering we get lower covariances, but we introduce a lot of correlation in the data. So we actually convert uncorrelated noise to correlated noise. The density of the points in the initial network that we use for the interpolation of the atmosphere, filtering the atmosphere. You see, for example, for 3 points that I show with red here, the covariance matrix of the 3 times time series, it's in the below. So, and in the right, for example, you see one of the points has a very, actually the filtering doesn't affect that much a lot because there is no point around it. The revisit time, I go a little bit fast because of time. On-model deformation, very interesting. It is, we have modeled two different stochastic or on-model deformation, and then we see that when this on-model deformation, the characteristic of that in a space is very similar to atmosphere, the filtering is not very effective, and it show up in the covariance matrices. The different kernels that we use, different kind of covariance matrix. Again, you see in the variance is not much different in the bottom row, but if you look at the covariance matrix, you see there are a lot of different correlation. It is same data set, same processing, but different kernels just used for processing. One demonstration of real data, I'm going to Tehran. It's south of Tehran, large deforming area, maximum 28 centimeter per year. I'm focusing on a small area here. I want to show you how the variance covariance matrix looks like for this data. You see this is every 6-month data, but for this data, we can create now the full covariance matrix based on this error propagation and get the error bars or standard deviation of the cumulative deformations that we have. Or we can, for different time series, again here we see the filtering, before filtering and after filtering, how much we introduce correlation, noise correlation in data. And also we can further propagate it to velocity. So we have velocity, also we have an standard deviation of error bars for velocities. Come back to my first questions. This is signal to or noise. We need error bars here. Error bars come from the diagonal elements of the covariance matrix that we use. Still, if we look at this 95% confidence interval, we say, okay, these ups and downs could be signal. But if we look at the covariance matrix, not, because the covariance matrix show we have correlated noise. We can simply do the test, and the test is rejected. It means it's not really the signal, these ups and downs that we have in the final time series. It is smooth, but it's not signal. It is just noise. In a space, I get the profile of this. If you look at the profile, we have a subsidence. If you put the error bars, still this subsidence makes sense that it's subsiding. But if we test based on the covariance matrix, then we see that the test is failed, and it means this profile that I show you here, it is just purely noise, but smooth noise. So this is, I conclude here, and I just focus on the last conclusion here, that based on this, I think error bars are not enough. We need somehow to adjust the covariance in the final data. Thank you very much.
Thank you, Sami. So let's have one question before we move on to the discussion part.
If you think of one, we'll do it in the general discussion, unless, was there a hand up? I didn't see.
Well, maybe I'll have a single question,
Okay.
a small question, Sami. So I guess it always depends on what you want to do with the data, right? So how you parameterize your problem. So the variance covariance matrix you want to end up with in the end is dependent on whether you want to have a kind of functional description of a subsidence ball or some kind of accelerated deformation or so. So how generic is your method for these different types of parameterization?
I think that the covariance matrix of the non-model deformation that we put there, it allows us to whatever kind of a signal we want to include in data. If we assume that the model is correct and there is not that much on-model deformation, based on this assumption, we can put this QS to 0 and apply this error propagation. Of course, it depends on your assumptions, but for any kind of quality description, we should start from some assumptions. But again, as you said, it depends what we want to do, but this is generic to digest whatever we want to do as a kernels or covariance matrix in it.
Okay, so we're now to the point of our round table, which is the more general discussion, and we are also including points brought up in the first half of this session, which was in this room yesterday morning. So could we ask Pao, and who was the other chair yesterday? Is he here? Oh, could you both come down as well, because that was in your session. And we have a few questions that are here as guides. And so yesterday's talks were actually, there was quite a common theme in terms of the closure phase and presence of phase bias and such. So that is something that is clearly being thought of by a number of people, and so there may be some good discussion points people want to continue to bring up about that. Today's session had more of a variety of different talks, but if there's a question that's lingering someone would like to bring up, then that is perfectly fine. So
Yeah.
let's
Maybe just to add on to that, so we have 20 minutes here. I think what is probably most interesting is to go towards recommendations for ESA, right? So because the scientific discussions will go on and on. So that's one remark I would like to make. So try to see what is practically relevant. And the other thing is, so which is now the questions which are projected now. It can be a lead for discussion, but feel free to come up with any other point you want to bring up. We don't want to go sequentially through these questions anyway, right? So if you want to address something, then that's fine. Frans.
So I believe that the closure phase issue is one that faces the entire community. Right now, there are lots of studies that all have their own sites. It might be useful for ESA to establish a set of closure phase super sites, field sites where the relevant field measurements are taken, one that's maybe more arid, one that's, you know, a variety of different environments and everybody could use that same site so that methods can be cross-compared and results can be cross-compared. We have all the relevant reference data we need.
Now you're then also referring to having ground truth at these super sites, because I guess doing it, probably people will come up with the same results, but the thing is what is going on. Huh? So collaboration maybe with other parties which could provide soil moisture or whatever.
Another comment or suggestion? Yes.
Yeah.
I'm wondering, I'm addressing the
Can you speak in the microphone, please? Yes.
Okay. I'm addressing the first question, and I'm wondering that all the approaches presented here process a full graph or a large set of interferograms, and usually they don't address their coherence, because for many of the interferograms it's just pure noise.
I didn't get the point, sorry.
I wonder why most of the algorithms which were presented use all the stack,
Right.
while most of it may be just noise because of the low coherence, and coherence is always non-zero, even for pure noise.
Yeah.
Yeah, so if I can reinterpret that, maybe I didn't understand it correctly, but how can we be sure that we are estimating a non-zero closure phase rather than something that's an artifact of the noise in the measurement? Is that the question? So that's a good question. Anybody? Dave, you want to make a, or you?
Just back to the closure phase and the Cal-Val aspect of this. GNSS measurements can also measure soil moisture with reflections from the surface, you know, so people do. And so those are obvious sites to do Cal-Val, closure phase, INSAR, GPS all together. And so, but that's at L-band. And I think at C-band, the closure phase is going to be very different. So we have some natural L-band closure phase Cal-Val sites to use.
Elizabeth? Oh, well,
I mean,
We'll go.
continuing with the
Your
same
hand was up
comment,
first.
there is a companion system from Roselle, is Simmer, which is a microwave, passive microwave. So one of the, and SMOS and all these people there, one of the main variables they are targeting is soil moisture. So maybe they have already these super test sites with soil moisture measurements. It's true that this Simmer is working at different frequencies, but at least they may have ground truth measurements of soil moisture. You could combine in the frame of Rodel, Sentinel-1 NG and all this. So you don't need to make new things. You can maybe collaborate with those people to get these test sites to get the information about the phase closure.
In terms of CalVal, I think that we do have a lot of soil moisture ground truth, and what we have less of is ground truth about how vegetation moisture is changing. We have proxies like NDVI, but not so much not very many in situ measurements of vegetation change, and especially vegetation moisture change. So if we're looking to more sensors, that's what I personally would find the most useful in terms of isolating different sources of closure phase.
Charles? Microphone, please.
Is there a consensus that you can actually separate out the closure phase from, let's say, deformation? Can you separate those two terms and methodologies for doing that? And then the closure phase itself does become an interesting signal for whatever application.
So let me try to, since we're trying to eventually figure out some kind of recommendations for ESA, let me just float sort of a general idea and then we can comment. I mean, this is clearly a topic where there are multiple people working on it now. And so it seems to me that it would behoove us to, at a future meeting that many of us will attend, at least have a session or two dedicated to phase closure papers. And if this is really an open issue and there's a lot of things that are not well understood and requires a larger number of people, folding in different kinds of ground truth and that kind of thing, is this something we might want to think of in terms of having an informal working group or even a focused meeting at some point in the surface, in the future? So the idea is that if there are, if there are 25 people who are all working on this, that's a lot of people to work on exactly one thing, and so there may be something to gain from that. So we could perhaps list a variety of things that we might want to propose under the auspices of FRINGE or of ESA or of NASA or the International Consortium or whatever.
Yeah. Irina.
I think diversity in the research is fine, Howard, like everything else. 25 people working on it, I think it's okay.
Oh, no, of course it is. I mean, I'm always of the let 1,000 flowers bloom approach, so I'd rather everybody would look at it.
Okay, yeah, thanks. So I think it's also important to understand or to develop algorithm really to see how vegetation is really impacting this closure phase. Not only, there's three components for me. The one is a deformation, the other thing is a soil moisture, and the third thing is a vegetation impact, which we see is quite strong. And the question is, can we first decouple the effects of soil moisture and vegetation on deformation? And then the second question is, can we decouple soil moisture from vegetation in order to get soil moisture really, and not the vegetation content? So there's a lot of questions that we have, and I think we need to develop more understanding on it, but also algorithms. So for me, it would be very important to have a study actually, not only to discuss, but to have a kind of study which is really framing this, and that people can work on this study, finance, somehow support the financed on it.
This one way up here and then back to you.
Hello. I agree with the idea of the supersites. I think it's a very good idea. And maybe it would be interesting to have several bonds, C, X, and L, and maybe X also. Because yesterday there was a comparison between C and L. It was very interesting.
Yeah, thank you. So let's go to Carlos and then
Just
Okay.
in connection with question number 4 and the use of polarimetry, if I got well, you want to separate the different components, the formation, vegetation, and soil moisture. That's right. So maybe polarimetry could be used to, I mean, not to make something operational, but to separate the components. Because there are already some research directions in the polarimetric community trying to separate vegetation from soil moisture. So maybe this could be used. The question mark is that if we are going to have a data set, a polarimetric, interferometric data set at a given frequency, C-band, L-band, I don't care, but the problem is to have the data together with the soil moisture. And that comes back to the first question about TESA with ground truth. So theoretically, it would be possible to have that study, but only if we have the data, the proper data, that could be done with a ground-based sensor, for instance. You don't need to go to space, and also the ground truth. Theoretically, it's possible, but to have all the ingredients on the same time in the same place is the difficult part.
Question is to use airborne, or the comment is to use airborne sensors as well. There are a couple of questions way up over here. It's easy to neglect people because it's too many steps for the microphone.
So in terms of the phase closure mitigation strategies, there are already actually some methods already developed in the literature. I mean, some methods by Yuji that described yesterday, and also another method by Falabella in Italy that developed a mitigation strategy for the phase bias, and also another method that we developed in Leeds. So one of the challenges here is the main assumption that most of these methods that I use is the availability of a long-term interferogram which is bias-free, the phase bias-free. And so this assumption in many cases is under question, because in the decorrelated region, there are many pixels for which we cannot have this long coherence. And so this assumption might not be true for many pixels especially in the highly vegetated region. So maybe the main challenge that we have to solve a robust solution is to find a strategy which is not dependent to the availability of the long-term interferogram to mitigate this issue. And also it is very important to check the universality of the method. I mean, most of the methods have been checked in several studies, but it is good to check the universality of this method in several different scenarios with different scattering mechanisms.
Thank you. And I think there was another question, just 2 down.
Yeah, so I'm talking about the first questions. So we all know that phase closure are caused by the multi-looking operation, because it's use both the phase and amplitude to do the multi-looking. That's why it breaks the phase consistency. So I'm wondering if there any way we can look back to the multi-looking, so the way how we do the multi-looking, there any develop some algorithm approaches, try to use different alternative ways to migrate or remove the phase closure from the very beginning. That's my suggestions.
Okay, yes, thank you. Over here.
So, different topic, moving on to Sammy's talk at the end there. One of the recommendations from the previous Fringe was that we need to be implementing uncertainties and understanding the covariances in the data better. And Sammy's talk is a great progress on that. But we don't see that being in use in the majority of papers publishing time series yet. I think there's significant work to be done there still to actually take what Sammy's done or others and implement that fully.
Yeah, don't feel like you have
Yes,
to comment only on phase closure.
Oh, okay, so
Maybe can I just bring in a little bit different topic?
Well, I think Andy had a question.
All right,
and
okay.
There's a question up here as well.
Okay, go ahead. Yeah.
So, I saw the session C questions is all 4 questions about the keywords, the non-closure phase. So, and then I try to characterize a little bit. So the first question is about statistical methods, how to avoid that one. And the other question is about how to exploit the physics information signal inside that one. So I first just focus on the first question is should a study in this direction to remove the non-occlusive phase is initiative? I think it's yes, I totally agree because I totally recommend that there should be a dedicated study to understand this one because application information is important and critical for everyone. Especially true when we go to future mission which related to the longer wavelength like the ROSA L or the NISA. With the longer wavelength, we better penetrate to vegetation. In this case, we can understand what happened under beneath of the forest. And also related to tree automation, we using that non-occlusive phase to retrieve the signal under the forest, like something like vegetation, moisture, water content inside the forest, or even maybe we could use something like non-occlusive phase to understand some species like forest high, forest biomass. I mean, there will be a possibility to explore that signal. So about the second question, so what kind of study to initiate to achieve this one? I think that's we can start with airborne data because with airborne data we have a lot of airborne data from the L band, even with the B band. And spatial we have a lot, but a little bit limited to everyone. But the airborne, the ESA, they open a lot in the data for the L band data. So it's free for everyone under the scientific research. So about the third question is, do we need something like evaluate the performance inversion under different conditions with respect to vegetation cover? I think it's true because under the forest everything is crazy. So basically, that in the forest we had to make some assumption like, okay, is there any failing? Is there any phase center to be sure that the non-occlusive phase is okay or not? So we need to understand a lot under the forest with respect to the soil, to the basalt. Basalt is more straightforward. And the last question is about valorimetry.
Since you were making many comments, I would like to give Andy a chance to talk. And
so, okay,
then
let's
Ramon a chance to change the subject.
okay, sorry.
You don't comment more about them. There are more.
I'm sorry. But everybody needs to talk.
Yeah, just one comment. I think that's maybe partly the point that was just made, but I think the idea of a test site is a great idea. It's important then, I think, to have multiple sensors with different wavelengths. So if we do airborne, that's great. We can do all kinds of different things. But yeah, we see clearly that different wavelengths will help, I think, distinguish between soil moisture and vegetation characteristics.
So before we switch to the other topic, I want to make two observations. One is that I hope that people are listening to this and we get a plethora of proposals to investigate all of these things and people are getting good ideas and starting to think about it. And I forgot what my second point is already. Oh yeah, no, we've already made a great deal of progress at this meeting because yesterday everybody was calling phase closure phase bias. And now we're saying phase closure, so we're recognizing it as a signal with information in it to parrot what Ricardo was saying yesterday. So we've done something at this meeting. All right.
Yeah, just on a whole different topic, maybe something to discuss further in the coffee break. So in the previous time when we gave recommendations to ESA, it was many times because there were new missions coming up. Now the next two missions will be Sentinel-1C and 1D, which are operational. We cannot influence that much. But then we're going to have the Sentinel-1 next generation and ROSE-L together. And I think the current line of thinking is that so both missions with 2 satellites, 6-day repeat if you have both of them, to intersperse them symmetrically. So that means that you get one acquisition with Sentinel-1 next generation in C-band, and then 3 days later you get from the same point in space, from the same orbit, with the same, more or less the same resolution, the same viewing geometry in L-band. So we have, let's say, equidistantly spaced sampling. 1 day C-band, 3 days later L-band, then C-band again, and so forth. And I think at this time, it is because people are thinking about these concepts, it's also good to help them and to come up with different arguments. I think it's a great scheme, but I think it's something that is worthwhile for us to consider and maybe come up with different ideas for ESA to consider.
I remember also about the validation. I know our colleagues in CONAE with SAOCOM, they are routinely producing soil moisture measurements in Argentina. And there is the PUMAS program between ESA and CONAE. So maybe that could be an avenue to explore, to combine SAOCOM with Sentinel in Argentina. I think Sentinel in Argentina is only 12 days, but I mean, there are some technicalities that you can solve. But at least there is already a framework of collaboration between ESA and CONAE, and maybe the Argentinians are producing soil moisture, so that could be a good setup to
For the
produce
alternating
something
C-band,
more.
L-band.
Yeah, I mean, to explore if you can have the data, the ground truth, the estimations to test these kind of things of phase closure, even on national scale.
Yeah, and just to add on to that, don't forget that NISAR, which launches in a short few months, has got 2 frequencies. It's got a large soil moisture group, and there will be many, many field sites and things like that with open data that will be available to everybody. So just add that into your list.
So Ramon, building on what you said about, and following from your talk, Howard, how the automation of the data products now and the release of data products, particularly in this now geocoded SLC, which we're trying to encourage, I think. But I think, is it on us to set some minimum requirements on the DEM qualities people are using and how regularly are they updated when they are delivering these geocoded SLCs as standard data products?
Yeah, I mean, if this is an issue, then we never definitely want to say that. And, you know, I mean, the Copernicus DEM is great, but it would be nice to have 5-meter postings at 0.5 meter resolution. I mean, would that make things better? If so, can we think about, you know, tandem X or L or whatever it is in the future to do it again and do it better? I mean, that we want to keep improving.
I have one more can of worms, and I admit that I'm both frequency and geographically biased here. When we talk about signals that I don't think we understand enough, with L-band coming up with Roselle and NISAR, we'll have suddenly coherence 365 days a year in many places. And we'll run into having to better understand the impact of snow. I don't think we know enough yet how snow impacts the phase and how it may impact closure phase if there's gradients of moisture in the snow. And I think more study on, first of all, how to utilize the signal to understand snow, but also then add it to the list of phase components that we have to separate in a time series analysis, I think is also something to look into.
I want to point out some minor mathematical point. All these processes that involve closure phase are something like rain when coherence breaks down, or there is, regarding vegetation, there's maybe some harvest where coherence breaks down, but in the interpretation, the time series are put together as if they were continuous, while in truth we do not know how it goes on. And this missed a discussion of that in the talk, so that's why I wanted to point this out.
I think probably we should slowly start to wrap up if people still want coffee. Yeah?
Yeah, so if somebody wants to raise a new topic, do that. Excuse me, we will talk at the coffee break about it, but let's get it out. So you get the last
maybe
word.
one remark there on Ramon's line on spacing the. So on Ramon's line on spacing the satellites there, I want to bring up the topic a bit of error handling. I mean, you can either prioritize the temporal sampling by spacing them equally apart, but having L-band, C-band, and maybe others right next to each other, then really observing same atmospheric problems. This may be value more in terms of error handling than having a temporal sampling. So people maybe have to think about it and make up their mind which value more.
All right, thank you. And with that, we will wrap. So thank you to all of our speakers and to all of you who sat in the room, and we'll all talk at the coffee break. Well, you just had to stand there, but.
Because Catherine Guns is not here.
Oh, okay. I didn't know that. Right. Yeah. Okay. She's your postdoc, of course. Yeah.
Where's the list? Do the first couple, but Fernando's not here, the last speaker. So we got to look out for him. And he can still get his. They said if he brings a memory stick, he can just get on.
Okay.
Otherwise, we'll end early again. So what do we do for discussion? Go to lunch. Well, if there's only, I guess we shouldn't worry so much about the time if they're showing.
But if it's the last one. Okay. But there are other people from IREA right here.
But they didn't insert the talk in the lineup.
Okay, welcome back everyone for the second. We're on time, aren't we?
My talk's short. So.
Okay. Yeah, the second in the what are we, tectonic session. So we're going to kick off with the first talk, which is the calibration of seismogenic thickness for estimation of seismic moment accumulation rate from strain rate. This will actually be given not by Catherine Guns, but by David Samwell, my co-chair.
Okay, thanks. I can let people wander in a little bit because I think my talk is not that long. I'm hopefully not that long. So what I want to talk about is quite a bit different. I'm not going to show any INSAR results, or just a little bit at the end, but I want to talk about how we interpret surface deformations from geodesy. And one of the main things we'd like to learn from geodesy is how much seismic moment is accumulating in the crust, because if we know the accumulation rate, and we know the time since the last big event, we can say, well, the next earthquake has this moment available for release. And so that's sort of the objective here. And I'll start off showing a motivation slide, but then get into the issue that there are two ways of measuring seismic moment accumulation. There's one using, block models with backslip, measuring the moment on those models. But there's also another method using strain rate, and the strain rate is used to estimate the moment accumulation rate in little cells. And so I'll point out that at least for a model, these two methods should give the same amount of total moment. Model, a perfect thing, so we know what we're putting on the faults, and we know what we're measuring on the surface, and these should match. In order to get them to match, there's a free parameter called the Kostroff layer thickness. Actually, that times the shear modulus, but we don't really know what that number is. People have assumed a number of like 11, but it's based on really old information. So we want to update that number using models, and then use that information to try to estimate how much seismic moment is accumulating away from the major faults using geodesy. And of course, that's very controversial because we don't know where all the faults are, so it depends on your set of faults. But I'll go through some examples, and then finally about how INSAR can be used to maybe improve the whole thing. So here's the motivation here, a paper by Elliott and others showing that the major earthquakes usually occur in areas where the strain rate is greater than about 50 nanostrain per year. And so that's sort of the accuracy that we'd like to get to, 50 nanostrain per year. And that's actually quite a challenge for INSAR. And strain rate, as I said, can be converted to moment rate, and then that times the time gives you the total moment. Okay, so as I said before, there are two methods of measuring moment accumulation rate in the crust, and one is this fault-based method, and then the strain-based method, and I'll go through both of those right now. Relatively straightforward. Okay, approach one, fault-based models. And you see the equation here. I guess I don't have a pointer, but you can see it. It shows the moment accumulation rate divided by the length of the fault, because you don't really know how long the rupture is going to be. But the moment accumulation rate divided by the length of the fault is equal to the shear modulus times the velocity of the block velocity, and then times the area, or times the depth of the lock zone. Very simple idea. That's for a single two-dimensional fault, and we can use geodesy, of course, to measure the depth of the lock zone and the slip rate and so on. For a more complicated set of faults associated with the block model, one would simply add up all those contributions to the moment rate. So when we build a model, a backslip model or a viscoelastic type model, we can know exactly how much moment we injected into that model on all the different faults. And I'll be talking about 3 models because the different models have different results. And the 2 types of models I'll talk about, three types of models. One is a pure, just elastic half-space block model, backslip. The second one is an elastic plate over a viscoelastic half-space, a little bit more complicated. It includes the time element. And then our third model would be that same thing, but with variable crustal rigidity to simulate things like low rigidity areas along the Salton Trough, we'll see. Okay, so here are the 3 models that we're using. I'll start with the model on the right first, Zheng and Shen. That's a standard backslip block model, and we can use the numbers from their publication to get the total moment accumulation rate per year, and it's 1.18 times 10 to the 19 Newton meters per year. And so that's a number we can use. The center one is from a paper by Ward et al. It has fewer faults, lots fewer faults, but it's a viscoelastic model. And so in both of these cases, these models are tuned to fit the surface GPS velocities and INSAR in the case of Ward. And in that case, the moment rate is 1.52 times 10 to the 19. And then the one on the left is really just showing that same model, but with variations in crustal rigidity. And you can see low rigidity along the Salton Trough, where the Salton Sea is, and then high rigidity in other places. And this has a pretty big effect on the moment accumulation on those faults. And overall, it has a lower moment accumulation rate. Okay, so that's, that's cool. All right. So that's approach 1, backslip models. We know that. Approach 2 is to measure the strain rate on the surface everywhere and then convert that strain rate into moment rate. But actually, we're measuring a tensor, a 2-dimensional strain rate tensor. So we have to summarize that strain rate in terms of a scalar strain rate or a scalar moment rate. And you can see there are 3 equations here. These are 3 equations put out by Savage and Simpson, 3 ways of summarizing the strain rates into moment rate. They're almost the same, and I'll show you some examples, but there are slight differences here. So this is the second approach. We can just go directly from surface strain rate measurements to moment rate. Okay, those 2 numbers should agree, right? These are models, they're perfect. So we know the fault-based number, we know the strain rate-based number, but the strain rate-based number had an unknown in there, and that's this Kostroff thickness, H. And so we're just gonna vary the Kostroff thickness until those 2 numbers match for these 3 models. And you can see the one on the left, this is the uniform rigidity viscoelastic model, I believe, and that requires a thickness of about 11.5 kilometers. The central one is a variable rigidity, 9.7 kilometer thickness, and the one on the right is the block model, 7.3 kilometers. So they give different numbers. In the literature, people tend to use 11. 11 sounds like a great number, but it's just based on a previous publication where they said 11 was good. So this is sort of an unknown in this whole process. So we can now, just using these 3 models, put some bounds on this Kostroff thickness. And basically, it depends a little bit on which moment, going from the tensor to the scalar, depends which equation you use.
although those are pretty close, but it depends more on the model. And as you saw before, the variations go from 7.3 to 11, but this is much less than the seismogenic thickness. Normally, people talk about this as the seismogenic thickness, but that's more like 11 to 20 kilometers. So they aren't really the same thing. Okay, part 2 here is how do we estimate the off-fault moment accumulation? This is something people are really interested in because, of course, in California, all the big earthquakes we've had recently are away from the major faults. So there must be a lot of moment accumulating away from the major faults. And so we can use this approach now to say, we'll calculate the strain rate from, this is all done from GPS. We eliminate the creeping section because that sort of gives the wrong answer. It's not a high moment rate of the creeping section, it's essentially 0. And then we can subtract off, so we take the original GPS velocities, we subtract off the GPS from that particular fault-based model and take the residual and compute the residual moment rate and then see how that compares with the fault-based one. And you can see in these 3 cases, the uniform rigidity Ward et al. Model has about 41% off-fault moment. The variable rigidity has 43, and the Zhang and Shen has 32. So these are in pretty good agreement, but there's a lot of uncertainties in all this, and I'll go through that next. It turns out that the biggest uncertainty in that whole process is how do you derive strain rate from GPS velocities. This is not straightforward. There's a nice paper by Marr and Materna that just came out, but there's been other papers. You can give the same people the same GPS velocities and ask them to compute strain rate, and they'll come up with big differences. And it just depends on how much smoothing you inject into that interpolation process. So in this case, we put in sort of a reasonable amount of smoothing, and we got sort of a 17% variation. Okay, so finally, how accurately do we need to measure the surface velocities, and can INSAR contribute to this? And from this diagram here, it sort of says we need 50 nanostrain per year to really make progress here. And 50 nanostrain is 0.5 millimeters over 10 kilometers. 10 kilometers is a pretty big cell. INSAR is giving us much smaller things like a kilometer, but that's not going to help us because it'll come out noisy and have more moment than we expected. Well, we're reaching this sort of 0.5 millimeter a year accuracy from Sentinel-1. This is just an estimate based on the atmospheric noise, and after 8 years, you'd predict about 0.5 millimeters a year of error. So we're getting there. And then maybe I'll skip some of these. This is just putting in a plug for some of the work that we're doing, and Katya will talk about it next, combining GPS and INSAR to really improve the accuracy of the velocity field and ultimately the strain rate measurements. And we're making progress. It's, again, most of the information on the moment rate is coming from the GPS in this case. The INSAR is not really providing that much, but we're working towards that direction. And here's some examples. We decompose the interseismic deformation line of sight in terms of average velocity and an annual term, semi-annual term, co-seismic, post-seismic. I think Katya will talk about these. But the figure on the right shows the uncertainty, or what's left over in that fit. And it's about 0.5, in some places about less than 5 millimeters a year RMS. So we're not really getting there. I mean, we're getting there slowly. And again, finally, we want to take those velocities and compute strain rate, and there's different ways of doing this. And wow, that's cool. It doubled the the imagery, but it's you get the point here. With the one on the left, I think is GNSS only, and the one in the center is GNSS and INSAR, and the one on the right is the difference. And back then, when Jawad did this study, he found about 100 nanostrain per year differences, which is too big still to constrain the models. Okay, so in conclusion, we use these 3 published models to estimate the Kostrov thickness, and we find values between 11.5 and 7.3 kilometers. Using the same 3 models, we can estimate the off-fault rates of about 41%, 32%. There's a model where the variable rigidity has less moment accumulation rate because the Salton trough is sort of weak and it doesn't accumulate moment as fast as a uniform rigidity. And then there's an issue with how do you define faults? How many faults do you have in your model? If you put more faults in, you're going to get less off-fault accumulation rate. And of course, the geologists have been telling us that for years. And the biggest uncertainty in this whole process is still, how do you interpolate the velocity fields to get smooth grids of velocity and then strain rate? So I guess I'll end there and take questions.
Thanks. So yes, we have time for a few questions. Tim.
Sorry, I was sitting in the most inaccessible bit of the theatre. Thank you, that's a great presentation. I have lots of questions, so hopefully we can catch up properly later. But the one was about your Kostrov thickness kind of equivalent. What does that really mean then? Do you I mean, I guess there's a question of whether it's, well, maybe you answer that question and then I've got a follow-up.
So I didn't explain that very well, but in that Kostrov, the figure's missing. Okay, so there's a figure that you can't see, and and it's a polygon with a uniform thickness, and the corners are being perturbed by something. It's straining, so that whole volume is straining. So it's the area of that times the thickness times the shear modulus is the moment accumulation, basically.
Yeah, yes. So I guess I meant, what does it really, how should we physically interpret that thickness? Because obviously it's basically saying that's the equivalent thickness of moment rates. Yeah, so, but the earthquakes are rupturing a bigger thickness. So what does it really mean, I guess?
You know, in the literature, some people call that the seismogenic thickness, but the numbers don't match up. And then because the numbers don't match up, they say, well, there's some surface creep, so we can remove that little bit, and maybe there's slip on the bottom, so we can remove that and match the numbers. But yeah, it's a fudge factor. This is what Steve Ward calls it. It's just a fudge factor to make everything work.
And I guess the other thing that could be a fudge factor would be time varying, but I'm asking too many questions, so I should let somebody else go.
Yeah, just while you pass the microphone to Ekbal, one comment on that. I mean, it's right, it doesn't agree with the seismogenic thickness, but I notice as you introduce more realism to your models, it gets steeper, right? So is it just actually that we don't have enough?
Maybe, yeah.
David, I wonder if you comment on the non-heterogeneous moment accumulation rate with depth. You sort of did that by removing the creep at the top, but we know that strain is released in a non-heterogeneous way, so it's probably right to assume that it's accumulated in a non-heterogeneous way. And how will that affect your calculations?
So I think the strain rate to moment thing is very approximate. It's, there are going to be variations in the thickness of this layer that's accumulating stress, and then at the faults it might be different than away from the faults. So it was just an approximation that was useful for getting moment rate.
Eric, you have the microphone?
Yeah, and you're assuming this Kostrov thickness is the same for the whole of California, even though there's huge variations in crystal thickness?
Yeah, I mean, that's what people have done. Yeah.
Yeah, one more quick question from Paul. Oh, sorry, Laura's already got a microphone.
Hi, Gideon.
You go first.
Do you think that the strain rate should equal the moment rate? And I'm thinking about places where strain rates are incredibly low, if non-existent, and we still get big earthquakes.
So there are places where it doesn't work at all. A top to bottom creeping fault has no moment accumulation, and yet if we use that methodology, we'd find a huge strain rate. So, yeah.
So, Dave, just a very quick question on the off-fault strain. So, of course, you could see earthquakes like ridge crests seem to show up prominently in some of those plots. But I guess my question is, it looked like the boxes, the size that you were, calculating that over was fairly coarse.
Yeah.
And it seems, I think when we think of off-fault strain, we're really thinking of kind of small fractures in some kilometers within distance of a fault. So I guess I wonder how well you can resolve that scale.
So those blocks were made large because if you make them very small, you'll end up with velocities that create high strain, plus or minus everywhere. So it's pretty artificial. You better get going.
Yeah. Next door. That's great. You going to introduce?
No, I try.
Okay, so the next talk is going to be Consensus INSAR Time Series and Velocity Model for Southern California by Katja.
Hi, my name is Katya Timofeeva, and I am from NASA JPL, and I'm going to tell you about this collaboration that we've had to create a consensus INSAR time series and velocity model over Southern California. So we have quite a few, if you look at the slide, quite a few participants in our group and quite a few different research institutions that are participating in this exercise, and I'll try to tell you all about it. Some of them are in this room, so thanks for that. This is how we started. Our goal is really to provide a self-consistent and well-documented set of products, namely INSAR velocities and time series, and also GPS velocities and time series, but this group in particular and this talk will be focused on INSAR over Southern California, and the word Southern is in brackets because we're rapidly expanding, as David kind of hinted, over to cover the entire plate boundary here, there in the western, northwestern America. That's the primary thing that we've committed to, but really what we really enjoy doing is comparing different existing methods for INSAR processing and post-processing and error correction, and trying to figure out some best practices, trying to figure out what the different impacts the different methods have on our results, and generally trying to put together some kind of consensus. Because if there's something that we've seen so far in this meeting and many other meetings, is that everybody has their own way of making INSAR time series. That's just true. So we have this exercise going on where we compare all of our methods and results, and it's been really fun and interesting. So we began as part of SCAC, Southern California Earthquake Center, and we're trying to put together this community geodetic model. SCAC has several community models: rheology, stress, fault. We're the geodesists. And here on the right, you see our first result. That's from a few years ago. It's just one test, one track, one frame from a Sentinel track, number 71, over Southern California, descending track. And it is obtained from a combination of results, since we're trying to build a consensus, of 5 different research groups at the time. We've expanded a bit since. So you see in this consensus model, and I will tell you in a minute how we got here, that the colors, of course, are INSAR displacements in the line of sight, and there are colored circles also, which are also in the line of sight, but GNSS measurements, both campaign and continuous velocities over the same time period. And I think the agreement is generally pretty good. The places where the agreement is not so good are mostly where there are local effects affecting the GPS velocities, and also where there are nonlinear effects affecting the velocities overall, and there's some disagreement between how the INSAR and GPS velocities were calculated. So for example, here, oh no, spoilers, here, there is some disagreement over there, and that's a big aquifer that's moving up and down with a seasonal signal, big seasonal signal, so the velocities just don't agree between GPS and INSAR. Otherwise, the agreement is very good, which is maybe surprising because we didn't actually constrain the INSAR, as many people do, to conform to the GNSS velocities. So this agreement is pretty natural due to other corrections that we're applying. So how did this come about? So these were the 5 participating groups and their 5 different results. For each of them, there are 2 results. One of them is the velocity, and the other is what would happen if you averaged all these velocities together, which is how we actually get our consensus model. And on the right for each group is a plot that is a difference from the mean model for each of them. So you could see how much they deviate from each other, basically. And there's a whole big summary of the different methods that were used and their pros and cons by all the different groups. And you can see that there are a lot of people have tried many different things, many different corrections. Processing softwares are different. People apply DM corrections, various kinds of atmospheric corrections, phase closure masking, things like that. Each of them, of course, have some impact on the results that you will get at the end for your time series and velocities. And as I mentioned, our consensus model is actually just a simple average of all of these results. However, what that does, and hopefully we can convince ourselves and you of that, is that it will average out these artifacts that come about as a result of the different processing methods that are used in each of these cases. So once we have created our consensus model, which I showed on the first slide, again, we're trying to convince ourselves that a combined model is better than individual models, and we're doing that by validation against GNSS, which again, sometimes it's a good idea and sometimes it's not, but in this case, for most points, it ends up working quite well. So in rows 1 and 3, there are comparisons between the different individual solutions from the different groups. They're just plotted in different colors. But in rows 2 and 4, there are corresponding what happens if you collapse all these solutions into one, and you compare it to the GNSS time series. So if you spend some time looking at this closely, you can also convince yourself that the combined model is better than the individual ones. This is where we are now. We have expanded and we are continuing to expand. So this is our current consensus model. It is now 4 tracks, ascending and descending. And we're spanning the time period between 2015 and 2019. And the reason that we stop at 2019 is because there was an earthquake. There were 2 earthquakes, actually, a whole sequence of them, in Southern California at Ridgecrest. And the biggest challenge that we currently face right now is how to create a time series that spans that earthquake, because it's going to depend on how you deal with the co-seismic offsets, how you deal with the post-seismic offsets. And it turns out that that's quite a challenging problem. I'll talk about that in a moment. So another big challenge before we get to that was calculating the uncertainties, something that is, again, everybody does this differently, probably, because there's no one single correct way to calculate uncertainties for INSAR time series and velocities. So here, what we decided to adopt is basically to do it the same way that it's done for GNSS. And these end up being the uncertainties for each of our velocity models, the consensus velocity models. And the reason we think they're reasonable is because they actually end up having higher uncertainties in regions where you would predict higher uncertainties, such as where there's more topography or decorrelation, and in dry, arid places where, where the motion is very well constrained, the uncertainties are low. Also, they're higher for ascending tracks than descending tracks, which is something that we've always observed and never have been really able to explain in this study area. So it makes sense, we think. But I will move on to the Ridgecrest results because they are probably the most interesting thing that we've done so far. So how do we deal, again, when you have an earthquake in the middle of our time series? Everybody has a different way of doing this, and so far we have just done a comparison between all of our different results. So a couple of the groups use kind of a physical model of a coseismic offset and plug that in as the earthquake and calculate the time series around it. There is the Scripps group have kind of an iterative approach of estimating the offset and then applying corrections and so on. There are 2 JPL groups now that did not agree on a method, so they're using different methods, which is interesting. It's great. So as you can see, the results are, there are two rows of results. What they are is they're the cumulative post-seismic deformation. So I took an observation right after the earthquake and up to 1 year after the earthquake. And you can see that the results from the different groups that have tried to make these time series can be quite different, different noise levels. There are certainly common features, such as you could see to the north of the big star. The big star is the epicenter, the hypocenter. There is a discontinuous feature in all of them. So there are common features, which is encouraging, but there are a lot of differences. And these are the differences that we are now exploring in terms of how people calculate time series across an earthquake, how they calculate their offsets and post-seismic deformation. Again, we did a time series comparison, and again, the results are variable. For some groups, the agreement is quite good. Others are more noisy. Overall, it looks fairly okay, fairly successful. We're kind of able to do that, but we are exploring what these differences mean in terms of what the best practices are for applying methods to calculating time series across an earthquake. I don't know how much time I have. I think I tried to go through this quickly.
You've got plenty of time.
Plenty of time, okay. Well, I don't have much more to say, so I would like to have more of a discussion. I'll just say that this exercise is not restricted to people who are from Southern California. If you want to join, we're always welcoming new people with their other methods who can come to our virtual meetings and argue with us about how their method is better. I love that. So please join us if you want. We have a lot of things planned. As David showed, we're trying to expand to cover more area. We're expanding down into Mexico as well as northward. We are trying to incorporate into our big time series some of the legacy data sets from ERS 1 and 2 and NVSAT. Most of our groups already have those results. It's just a matter of compiling them. Campaign GPS, ALOS. And of course, we're looking forward to new and upcoming missions from ESA and also NISAR. So that we will have longer continuous time series. We're looking forward to continuing our work on creating a time-dependent three-dimensional deformation field from a combination of GNSS and INSAR, and calculation of strain and strain rates. Of course, more research into best practices. We are transitioning for some of our pre-processing, just interfered ground formation, into cloud computing and automation. And of course, we'll have some workshops to actually get people to use our model and see what they think. So anyway, that's all I have, and I will welcome questions and criticism and things like that.
Thanks, Katya. So yeah, we do have time for some questions.
Sorry, thank you for a great talk there. And it's really great you're doing it's such an important aspect to get at the uncertainties. So my question is around those uncertainties. You've got one way by comparing 5 or so models, but then you're taking their uncertainties, and your slide that you showed had areas of the map with near zero uncertainties. So what do you plan to do with that kind of artifact of the assessment of the uncertainty level?
Okay, so I want to explain the areas of zero uncertainty first, and maybe that will make more sense. They're not quite zero, they're close to zero, but so again, one of the reasons is because the time series there are quite dense. There are a lot of measurements, and the region is pretty dry, and so it's easy to measure, and there's not a lot of topography. But the other thing, of course, is that INSAR measurements are, at least in our case, always done with respect to a point. So of course, close to that point, the uncertainty will be very small, and far away from that point, it'll get bigger. That's what's happening. That's why you could see this, especially in track 166 right here. See there's a patch of blue? That's where the reference point is. That's why they're so low.
Yes, and certainly that's what we find. So the best
Yep.
thing is to inflate those back up so that it's reference point independent, because then if you want to pass that on to other people, they don't have to worry about that. You have a more of a uniform approach to estimating the uncertainty across the area.
You don't think it's realistic that they're smaller there?
No, it's not. And if you then push that on to someone else, unless that subtlety of the referencing is meaningful to them, I think it gets lost, and you want a better estimate of the uncertainty. Because obviously weighting at 0.01 millimeters per year would really heavily weight that area.
Yeah.
So yeah, I think thinking about how you propagate that.
We've had a lot of arguments about this actual point. Do you use some kind of a function, like, it's decaying away from the...
Yes, there's a spatial variogram to just jack up that reference so it represents more something at tens of kilometers, yeah.
Okay, I'll try to convince them. Thanks.
Next, Titus. The microphone will come.
It's my new favorite person. Hi.
Hello. Thanks for the great talk. Also on the uncertainty point, but I wasn't thinking about the referencing issue. I was thinking about whether your uncertainty map would match up with the difference between individual velocities and the consensus model. You showed this difference between them, and I wonder whether the areas of larger uncertainty are also where the difference is larger, and whether the number match up as well.
To some extent, that's true, because the places where the differences are larger are just generally places where it's harder to process the data, right? So again, places where the topography is large, so there are more errors, more atmospherically related errors maybe. Places where there's more decorrelation. So to some extent that's true, and to some extent it's not. So yeah, they're different uncertainties. So I guess for time series, actually, we still do that thing where we, this approach is for velocities. For time series, we still do that thing where we just estimate kind of the variance between the different models and the deviation from the mean for each of the models. But yeah, and those are kind of the epistemic uncertainties. They're model-based uncertainties, as opposed to these ones are supposed to be more physical, except for that reference point issue.
Right, great. Maybe I missed it. When you produce the consensus model, do you just do a simple averaging, or do you do the weighted averaging based on the uncertainty maps? And whether all models have the same reference? Sorry.
We don't do weighted averaging, because what if one of the models has a large deviation from the mean in some place, but that one is actually right? Like, why would you prevent that? So we couldn't agree on a weighting scheme because of that, because we don't know what's right? If you know, come and tell us.
So yeah, both as an answer to that, and also just in support of what you're generally doing.
I like answers.
Sorry?
I like answers.
Okay. We have the exact same problem in statistical seismology with smooth seismicity models. I have coworkers that have convinced themselves that basically nobody's smooth seismicity model predicts any earthquake location more than a few years after it was made, unless you make it completely uniform. And they've proven that to be true in a lot of cases. And so what they've started doing is something called expert elicitation, where you grab We actually do this for seismic hazard models, but you can do this for smooth seismicity models. This was done for the Christchurch earthquake aftershocks. They grab a bunch of people's models, and then you do a process to evaluate how individual users are, like, so you get a separate team of people that are going to be your voting team, do a test process to evaluate who's overconfident and who's underconfident about their state of knowledge, then have them vote on which models they like, and you use those underconfident, overconfident metrics as your weighting. It's called
Wow.
classical method. Anyway, we use it in seismic hazard. And it's, I mean, it probably, a lot of it comes out 50-50, so, you know, your straight up averaging would be right about right, but that's how you would, that's one way of getting, it's a subjective, but.
It's very interesting. Put it to a vote. Okay, so everybody has to come to our meetings now and they can vote. Come on. Yes. Anyone else?
Were there any more questions? Tim, I think.
I guess you said California and beyond, but to Southern California. Or China, elsewhere in the world, where there's more vegetation and there's other challenges you don't have here, and it would be interesting to pick a different area as well, and obviously we'd be happy to be involved as well.
I am personally very interested. Actually, we have talked about it. We did talk about it, about getting people involved who are processing and doing research in other areas. And yeah, I think that that's a good way. We just haven't recruited anyone yet. So if you would like to be recruited, we'll be happy.
What if you picked?
Right, okay.
Well, this is
That's fair.
sponsored by SCAC.
And yeah.
So when we write the
and
proposal,
GPL, so.
SCAC.
Yeah. Well, not anymore, but
Yeah,
they don't really care. Okay.
Andrew.
Just checking one of the points you said, it was the average of the velocities and the displacement series generally gave you the better fit to the GNSS, broadly.
Yeah.
Is that implying that the noise in them is basically random, or does anyone's method work better in a given area? Like, just
That's right,
someone's method is sometimes better in lowlands, someone else is working better in mountains, or is it basically just random?
I mean, it's kind of hard to say, I guess, but yeah, I mean, I can show you that plot. You see how the individual models differ from each other, and some of them have quite large differences. And then when you average them together, you kind of get rid of these artifacts that are introduced just by individual approaches. And yeah, I agree that it could be interesting to look into, like, what exactly is causing all of that. And we have been doing some of that, but it's, for the most part, it's kind of hard to say, but it works.
Just on that point, I mean, I also thought that, I mean, you can't use the agreement with the GNSS to actually locally weight different models, so where one model is doing particularly well.
We have also thought of that's a lot of work, because you have to account for, like, again, the local effects, because some of the GNSS stations, they're capturing something that is super local, so we would have to actually really go in detail through the GNSS data to do that well.
Yeah, fair enough. All right, John, I think there's one talk that's actually not going to be given, so
Yeah,
we can stretch this out a little bit.
Is Fernando Monterroso here, or someone from his group? Otherwise, we have plenty of time, but if he's here, we should move on.
We can make a community genetic model right here, right now.
So one thing.
Oh, you are here?
Oh.
Is your talk uploaded?
Is your talk loaded? Okay.
Okay. In that case, we'll move on.
We didn't know this. We're very sorry. Thank you, everyone.
Right, you want to take over?
All right, so the next talk is locus and types of seismic secondary fault slip during large magnitude earthquakes, and Henriette Sudhaus will present.
Okay, thank you. Yeah, thanks. So this is a small author group. Two of them, Vasiliki and John, are geologists. And Tilman is a master student at Kiel University. So I'm very happy for comments and so on, because many things, yeah, I'm coming up with. And I actually benefited already from comments last night during dinner, and also from EGU, from Shoni. So thanks for that. What? Yeah. Okay, synseismic secondary fault slip. I would like to make a comment based on an interferogram. So synseismic means we observe this in co-seismic interferograms. And you know the time resolution of interferograms is not that great. So synseismic means it's connected to the earthquake. How closely, it's unsure. I think it's very closely, so maybe almost instantaneously, but this is maybe, we can argue about this. Secondary means it's not connected to the co-seismic signal from the earthquake, but it's actually, I think, a passive reaction, and it's a very small signal compared to the main one. So you can see here the arrows pointing to offset phase. So you have the feeling that the fringes are cut, and you can follow this sometimes really long kilometers, but it's a very small signal, so it's easily overlooked. And then we say fault slip, and I had the comment that this is maybe too liberally used. So it's an activation, it's a motion across a fault. Yeah, if this is fault slip in the meaning of stick slip, we cannot say. Yeah, and it's likely a very shallow feature. Okay, so this is a normal fault, is a signal of a normal faulting earthquake. It was a blind rupture, so we have no real surface trace, or if it's very hard to see. And the main signal is this concentric co-seismic signal. Yeah, but you can see this this offset. We move out a bit. So what is this offset? Where is it? Maybe we can have a look at thanks. At a more regional tectonic. So this is in Tibet, and you can see that's a kind of a pull-apart basin. And what has developed, according to literature, is the negative flower structure. So during this evolution, we have many, many faults that have been formed there and that can be reactivated. And I think this is what we are seeing here. This is the faults that are mapped here from the active faults of Eurasia database. This is not very detailed, of course, in this region. Oh, why does that? Oh, yeah. So going back to the signal. So we see there is an activation, and I can tell you, if you look in optical images, you can actually see morphological features, very faint ones, but they are there, sometimes covered a bit by sediments. So to now look maybe at how does the fault move? Yeah, we make use of an ascending interferogram. This is the one that you see here. We unwrap this, we take a descending interferogram, unwrap this as well, and then we have seen also many examples of this. We derive from that east component and also an up component where we may have like north component contamination. So what you see here is the east displacement for this normal faulting earthquake. Yeah, so you can also see that this signal where the arrows are pointing is kind of tiny. I would quickly like to change perspective a bit. So we are making a profile across, so perpendicular to these fault structures. And I just show you here the east-west displacement. You can see a nice curve. This is the blue one. You can see some disruptions where there's maybe also some decorrelated areas, and we have also reduced the signal. But you can see where the black line has the minimum. This is the vertical displacement. You can see this one little step. So this is actually where this signal that I've pointed out is before. And maybe just as a conceptual sketch, so we have a blind rupture. So we're looking at depth, and this blind rupture did not reach the surface. So we can call this a slip deficit at the surface, or maybe there's something else. And what we have at these secondary signals is something that, I would put like this. So it's not to scale. It's just to make the concept clear. They have to be shallow, otherwise they would have had a larger signal or longer wavelength. And what is interesting a bit here, when we think of some of the profiles, we think of seismogenic depths, we think of the loose surface. The question is a bit, of course, have these signals anything to do with the earthquake deformation cycle? Well, I think they have to do with that. Is they are part of this? The question is there any significance? Because they're really, really tiny, and this is something that I'm not sure. So we're talking about a phenomenon at the moment. Yeah? And I'm happy for ideas later on. Okay, we go back to the signal. What you see here is not the east component, but now I'm calculating the gradient in the east direction. This is I do this very simple. I take my displacement map in east displacement and I shift it by 2 pixels and I calculate the difference. Super puristic. And you can see, maybe I hope you can see these steps where the arrows are pointing. And in the northeast, you can see that the step is now something like a reddish line. This means that the pixels east of the fault have moved further east compared to west of the fault. So there's some kind of extension. And you can see that further down the line, so where there's this blue arrowhead, actually we have a blue line, so it's the other way around. And then we have again a red line. So we have a fault activation, but it changes the motion direction, which is very interesting. I would like to go to a different earthquake because this is nothing special, I think. But we are not looking at interferograms that closely anymore. And we now have these very nice interferograms with high coherence and so on. So we have been in Tibet, where the blue star is, and we move now to Greece. And I will start with an earthquake in central Greece, and I will have just one slide on an earthquake in Greece, in Crete, in 2021, both of them. So this is another normal faulting earthquake displacement signal. We have concentric features. It's partly blind, so you can see that we have a very high fringe rate in the southwest, and there's actually partly surface rupture. If you model this earthquake, this is a very simple rupture model, but it's constrained also by seismological data. Uniform slip, so you see this is the main rupture extension. The projection to the surface is relatively shallow, dipping to the northeast. And I mark there where I try to map the surface rupture, which is partly based on post-seismic data where it's much clearer. What you can also see apart from this predominant signal are again cut-off phase, so disrupted phase in a linear manner. This is one point is here. There's one interesting small bifurcation there. And we have another one here in this black box, also disruption of phase. And I would like to look a bit closer into this one. We have a disruption of phase, and we can unwrap the interferogram, we can unwrap the descending interferogram, and then we can again come up with maybe an up component. And this is what I'm showing you here on the next slide, and I'm drawing a profile across this fault. And what you can see is that you have towards the northeast, you have an upward motion that is increasing, so there's kind of a step across this linear feature, this fault, and in the east component, we have a less east motion on the northeast side. So there's also a compressionist signal. When you see the topography in the background, it's very clear that this, on the long term, this fault behaves as a normal fault. Yeah, so we have the mountains on the southwest side, and we have kind of a graben structure on the northeast side. So due to the earthquake, this fault was activated in a reverse sense. This is not, I mean, we have seen this also for the Ridgecrest earthquake, we see this for strike-slip earthquakes, but this seems to be also a common feature for normal faulting earthquakes, that we have these surface activations of fault structures that have maybe no friction at all. So when I take these measurements and I'm calculating here like a more compressional sense, a more extensional sense, I'm making the disclaimer here, the north component, we have no grip on this, right? So this is completely ignored, and this may be a real limitation and a weakness here. But let's pretend we have an extension regime, and this is dip-slip pooling. So we can see that we have these fault activations that I've mapped. Some I've shown, the one in the south I've not shown. But there we have also a reversal of activation. So the question is, of course, if this is due to the co-seismic stress change, then we should be able to prove that, right? So let's see, can we use our strain maps to verify this? Well, the problem with strain and INSAR, so we have a strain vector, we can calculate the strain tensor, and we can calculate a dilation and see where we have extension and where we have compression. The problem is we don't have the north component. Yeah, and this is a very these are magnitude 6.3 earthquakes. We don't have pixel offsets or something like this for the north component. Sometimes they are small, so it's also hard with burst overlaps. But we can have a workaround. If we have a good rupture model, then we can predict the surface displacement. And it has been shown that for shear dislocations, actually the two components are very good to constrain shear dislocations. So the north component is not completely unconstrained. So this is so we're taking synthetic displacements and we're calculating strain and we calculate dilatation. So we will see some of these signals. So dilatation maps, positive means we have extension and negative means we have compression. So I'm jumping back to the Tibet earthquake. Yeah, you have seen these like reddish lines and bluish lines in this east-west gradient map. And this is here now with just normal faulting and thrust faulting signatures, the changes. And what is actually very interesting when you follow the fault from the northeast to the southwest, that you have this normal faulting activation in areas of extension and you have the thrust faulting activation or this compressional signal where there is compression. So this fits very nicely and is actually kind of a proof. You can also see that there's some things that are not quite matched. So I've in the map it looked like an extensional feature right in the middle. Maybe this is some unmapping problem or something, but there's also clear normal faulting activation at the site where yes, there's some dilatation still. Yeah, so it fits quite nicely, despite the model that we use is just a simple rectangular fault. But it's at depth, so maybe you don't have more resolution for anything more complex. I'm jumping now to an earthquake in Crete. Yeah, it's a normal faulting earthquake. It's a blind normal faulting earthquake. There is a dominant normal fault that is mapped. This is the black fault outline that you can see. It runs north-south. It's a Castelli fault. And this earthquake we think it ruptured the Castelli fault at depth, but it did not really reach the surface, despite that we see also steps directly at the fault. These are the blue markers here. These are mappings by a student. Also, the fault model is done by a student. The interesting thing is that apart from this very prominent fault zone, we have some activations of fault perpendicular to this fault. And this is in a sedimentary basin. No faults are mapped there because they are covered by sediments, but we see disruption of phase, and this seems to be along a continuation of another fault system. So this is actually very interesting. So my geology colleagues said, great, we can map faults now that we haven't known of before. The interesting thing is that these faults, these perpendicular faults, they seem to stop quite at this similar point. They are a bit in the bluish areas where you say, actually they're clamping, right? We have more compression. But yeah, we use a very simple fault model. Maybe the signal would look different if we had something more complex, and then it would all fit perfectly. We're going back to the Central Greece earthquake. I hope you are still following me. So here again, we have the mapped faults. The green ones are the synseismic activations, as we call it, and this is the predicted dilatation for this earthquake. And you can see that the surface rupture, this is the blue normal fault in the south, is perfectly sitting in this dilatation zone. We have also other activations, the one that is more to the west. We have in the very south the green line, the green fault activation that turns from south normal faulting to thrust. It actually turns to thrust where it starts to come into the bluish compression area. Very good. So this is nice. Above the fault, we have extensional activations seemingly that are in a compressional zone. This does not fit that well. And we have also this reversal of motion at this long fault to extension, also in a bluish regime where we don't expect this. So at EGU, Johnny pointed out, well, we could maybe, this model is constrained with displacement data and seismology, so it's good. And we, master student Tillman, he also tried to have a two-plane rupture model. Yeah, to say we take two planes, do we fit the signal better, of course. But the question is it justified to use more complex model? based on an informational criterion. And it turns out it's not. So the fit is better, but not that better that you can really justify that many more parameters in your optimization. So, but when we use this data and we calculate the dilatation, so this is so the first plane remains pretty much the same, but there's a second rupture plane that sits beneath this relatively shallow dipping plane, and that is antithetic. And now we have also an extension regime above the fault plane, and so this fits with the observation. Also, this very small extension regime sits in a very localized area of dilatation. So it looks like with this rupture model with extra data, which is basically gradient and very sensitive to surface things, we could argue that this is the better model. So I'm coming to the conclusion. So what we see is that faults react to earthquake at neighboring faults. So this is something that we intuitively would expect, and we can observe this with INSAR. We have 1 centimeter slip across kilometers. Try to map that in the field. Yeah, so this is great. We can do this. So this synseismic fault activation, it releases a bit of stress, yeah, but it's tiny. So I'm not sure how significant this is. We can use this for fault mapping, and potentially one could use this to constrain some of the co-seismic models that we have to some extent, yeah, to say which one is better. Thank you very much.
I think we have time for 1 or 2 questions. It's a very interesting topic to me.
Thank you, very interesting talk. Have you considered the impact of shallow rheological variations in terms of concentrating the stresses? Because you're presumably looking at really very shallow features. And in the case of this earthquake in Greece, you've also got the Taverna Spacing, which is bounding, I think, the fault where you get this transition.
Sorry, I didn't get the last bit.
So you've got the sedimentary basin to the
Yes.
north of the fault where you have this transition, and the impact of that change in geology.
We haven't looked into this, but it's actually very interesting to say we have a lot of faults. Some of them, seem to be very weak and they react, and some of them are not. And then, yes, so we see also in the sedimentary basin that faults show up that cannot be mapped because there's some alluvial sediments across. So this is quite exciting for a geologist. But we haven't looked into this systematically. Yeah. That's a good idea.
1 more quick question, then we'll move on.
Hi, Henrietta. Do you think there could be a way to explain this by looking at the rupture propagation direction? So whether it goes from the bottom of the fault to the top or the top to the bottom, if that could affect these localized movements?
Possibly. I mean, so according to our model, the rupture started for this event on the bigger plane on the lower part and ruptured upwards. Yeah, I haven't looked into this into detail, and this nucleation point is not very well constrained, and the depth of the hypocenter from seismology is also not so very well constrained. So this is, yeah, but I keep this in mind. Thank you, Egbert.
Okay, I think we need to move on, but it's a really interesting topic. Thank you. Okay, the next talk is recovering the post-seismic slip of the 2019 Ridgecrest earthquakes using INSAR, along-track burst overlap, interferometry, and GNSS measurements. And Yohai Majin will present the talk.
Thank you. That's not the right... Okay, thank you. I will show today our reconstruction of the post-seismic deformation field of the Ridgecrest earthquake. And this will be done with INSAR, GNSS data, and maybe most importantly, burst overlap interferometry. And I will try to show to you the importance of a long track measurements in northwest striking faults. So the Ridgecrest earthquake was a pair of foreshock, main shock earthquake, which occurred in 2019 in east of California, just north to the Garlock Fault. And in the lower panel, we can see the foreshock seismicity pattern, which was a pretty unique seismicity pattern of a perpendicular set of faults. And in a previous work, we showed that both of those faults has been ruptured during the foreshock earthquake. And in the upper panel, we can see the seismicity of the main shock. And from the seismicity and from slip solution, we can say that the faults that have been ruptured predominantly the northwest striking faults. So this will be the main fault that will produce post-seismic signature. And we can see this when we're looking on the post-seismic signature as it's viewed from the GNSS network of California. And we can see the cumulative displacement of the first 5 months following the earthquake to the left. And we can see that it's agree with right lateral strike slip movement on the northwest striking fault. And to the right, we can see the two stations most close to the earthquake rupture. And not surprisingly, we can see that the post-seismic displacement is just a fraction of the co-seismic displacement. So when we're looking on the co-seismic event, just using regular interferometry is not a problem. But when you're moving to the post-seismic deformation, which is very small, using only line of sight interferometry, which is mostly sensitive to the east-west component of the deformation field, is becoming problematic. So to mitigate that problem, we will use a burst overlap interferometry, and this method is taking advantage of Sentinel-1 TOPS observation mode, and essentially Sentinel-1 is observing Earth in bursts, and each 2 consecutive bursts are overlapped by 10%, this creating 2 kilometer wide strips that viewed twice in each satellite pass, and they viewing those bursts in forward-looking and backward-looking geometry, and we can perform the following interferometric scheme. We can take the interferogram of the forward-looking and the interferogram of the backward-looking to get 2 interferograms in the light of sight of the backward and the forward-looking geometry, and then the interferogram of the interferograms to get the deformation in the flight direction of the satellite. So before jumping to talk about the post-seismic displacement, I want to show you the co-seismic displacement as it's viewed from the burst overlap interferometry. And here to the left, we can see the line of sight interferometry or traditional INSAR of the ascending track of of Sentinel-1. And in the middle panel, we can see the burst overlap interferometry. And the profile in the right panel compare the two. So B3, which in the upper left corner, is comparing a burst that's crossing the fault. And we can see that the burst overlap interferometry in gray essentially showing us maybe the classical view of displacement perpendicular to strike slip fault with more than 2 meters of offset across the fault, where in the line of sight interferometer, we're seeing only 90 centimeters of offsets. And we can see meaningful deformation above the noise level in the burst overlap interferometry much farther than the fault. We can see maybe even in B7, so more than 70 kilometers away of the fault, but definitely in B6, we can see deformation above the noise level, where the line of sight interferometry is already well below the noise level. So this is giving us an example of the importance of the flight parallel component of the displacement field in the case of this earthquake. So in order to retrieve the post-seismic deformation, we perform a small baseline subset time series analysis, both for the ascending and the descending track. I will show mostly results from the ascending track as it has favorable geometry in compared to the fault geometry. And here are the cumulative displacement over the first 5 months following the Ridgecrest earthquake as it's viewed from a line of sight interferometry to the left and burst overlap interferometry to the right. So we can see that we do have some very substantial deformation in the line of sight, but those deformations are concentrated in places of fault geometry complexity. So they probably related to this geometry complexity and some poroelastic rebound processes. And to the right, we can see the burst overlap interferometry where we can see nicely the offset along the fault in burst B2 and B3. And we can also see that there is a significant amount of deformation of the fault in B4, so 10 kilometers out of the fault tips. So we can compare the post-seismic versus the co-seismic deformation, and we can see the post-seismic deformation in the burst overlap interferometry in the black dots, and we can see the bursts that crossing the fault are B2 and B3, and we can see that we have about 2 to 3 centimeters of offset, where in the co-seismic deformation we reaching 2 meters of offset across the fault. And we can also see that actually the maximum post-seismic deformation is lie in B4, so not across the fault trace, in almost 4 centimeters of displacement, and also some meaningful deformation in B5. And if we're comparing the post-maximum displacement to the co-maximum displacement, we're getting that the ratio between the post to the co-displacement are 10 times larger in B4 and B5. So we have something up there in the north that we will try to explain. So then we will move on to talk about the temporal evolution of the displacement field. And to the left, again, we can see the temporal evolution of the cumulative displacement of the burst overlap interferometry, now with the cumulative displacement of the GNSS. And to the right, we can see the temporal evolution of the displacement field. So we took the horizontal component of the GNSS data. The vertical component was too noisy, so we only took the horizontal component, and we project them to the satellite parallel, satellite perpendicular direction. And to the right, you can see a comparison between the burst overlap time series, a line of sight time series, and the GNSS data. And we can see that we have, where we have GNSS data, we have almost a perfect fit between the burst overlap interferometry and the GNSS data. And we have about 1 to 2 centimeters of offset between the GNSS data and the line of sight interferometry. This is giving us the vertical component of the displacement field in the line of sight. We also can see that the displacement that we see in the north is completely missed by the GNSS network. So both the GNSS network and the line of sight interferometry missed those displacement. And we can also fit some logarithmic function to the burst overlap interferometry. These are the pink curves. And we can see that we have a different decay rate between the bursts that crossing the fault and the bursts that are off fault. So we will try to compare those decaying rates with the seismicity rate. And here in the middle panel, we're seeing the post-seismic seismicity, or the aftershock following the Ridgecrest earthquake. But maybe before, I should mention that the Ridgecrest co-seismic rupture ceased at the tip, so almost at the tip of the coastal geothermal area, which is an area with high heat flow, very shallow interseismic seismicity, so high transition between brittle and ductile crust. And we can see that the color are representing the distance from the coastal geothermal area. And to the left, we can see the normalized earthquake count in strips perpendicular to the fault. And we can see that that the seismicity rate is decaying faster as we're getting closer to coastal. We can see the same pattern when we're looking on the deformation. So the deformation is in the right panel. The dashed line are the same curved, pink curved line that we saw in the previous slide. And we can see that the blue line that represents burst 4, which is off the fault, is decaying faster than the red and green line that represent that the bursts that crossing the fault. And if we're looking on a co-located seismicity with the burst, so the polygons, the red, green, and blue polygon in the middle panel, and we're looking on the normalized earthquake count, we can see that where we have really co-located seismicity, in B2 and B3, we have almost a perfect agreement between the seismicity and the deformation. And in B4, where we don't have a really co-located seismicity, we do see the same pattern of decaying faster, but at a different rate. And finally, we will try to suggest some post-seismic sleep model to explain those observations. We will first suggest, or we will consider model 0, which consider only sleep along the faults that have been ruptured during the co-seismic sleep. This will be model 0. And then we search for an off-sleep transient with Monte Carlo Markov chain inversion scheme. This yielded two off-fault geometry 1 and 2, where 1 is a strike-slip fault, or it's both strike-slip and normal fault, but left lateral, so a mirror image to the fault that has been ruptured during the foreshock. And fault number 2 is predominantly normal fault. And you can see the slip distribution to the left, so mostly wrapping the co-seismic slip with model 2 needs some extra slip to the north to fit B4 and B5. And we can look also on the data to model fit. So generally all the models are fitting the INSAR data similarly well, so they do succeed in modeling the general pattern of the formation, but do not succeed in fitting the near fault high deformation, which I mentioned earlier that they are probably related to poor elastic rebound, which we did not include in our model. And when we were talking on the burst overlap interferometry data to model fit, model 0 that consider only slip on the co-seismically ruptured faults, doing pretty poor job in fitting B5, where both model 2 and model 1 doing very good job in fitting this burst, and model 2 doing also very good job in fitting B4, and model 1 doing slightly better than model 0. And we can also try to compare our off-fault transient to the stress regime in that section of the fault, and this can be calculated out of the moment tensor catalog of Wang and Zhang Wen. So we can take the moment tensor catalog and transfer them to a stress regime in the upper right, and we can see that model 1 is agreeing very well with this stress regime, where model 2 not agreeing very well with the stress regime. So we conclude from the suggested model, we find model 1 the most probable. I think I will finish with showing the summary and taking questions, comments. Thank you.
Great, thanks. Well, we have time for a few questions. I mean, you're right on time there, so.
In some of the post-seismic interferograms, that something close to where your fault 1 was showing up as a obvious discontinuity in some of the interferograms. So I think that, did you notice that in your interferograms?
In the line of sight interferograms?
Yes, the regular line of sight interferograms.
Where did you see the uncontinuity?
Where you had put your fault 1.
I think I didn't notice it in my interferogram, but this could be a good result if I would.
Well, I'll ask a quick question about the effect of the COSO geothermal area. I guess you're implying that the crust there is behaving in a more viscoelastic manner, and because of the excess heat, or?
Yeah, probably. That the reason also the formation and the seismicity is decaying faster.
More questions? We have time for one other question since we were about 5 minutes behind schedule before. Now we're catching up. There's one.
Thanks for the talk. Just quick question. How is the noise level to your burst overlap interferometry compared to classical interferometry? Do you see a big difference in terms of noise?
Sorry, I didn't get that.
The noise of your burst overlap interferometry compared to a standard interferometry, like is it more noisy, different frequencies of noise? Or?
So the burst overlap interferometry are more sensitive to coherency than traditional line of sight interferometry. But in other terms, they are more easy to handle, so they are blind, almost blind to atmospheric because of the interferometric scheme, which is an issue with the interferogram, the line of sight interferogram in that area. We did perform some empirical analysis of the noise by calculating the same time periods of burst overlap interferometry during the interseismic periods and expecting zero deformation, and we find they are sufficient.
And it looks like you have a high frequency noise on this figure, for example.
That's due to the sensitivity to correlation of the burst overlap interferometry.
Okay, thanks. We'll have some time for more discussion this afternoon before the poster session, so keep your questions in mind. But let's move on to the final talk of this session, automatic seismic source model retrieval by exploiting the Sentinel-1 DNSAR co-seismic displacement maps available through the EPO SAR service. And Fernando Monterroso will present.
Okay. Okay, good morning, everyone, again. This is a pleasure to me again here to sharing my experience about this project working in IREA CNR with National Institute of Seismology and Geophysics in Italy. Basically, this job raises a summary of how to do different algorithms that we development with automatic processing change, with DINSAR products in EPOS catalog, and a National Institute of Modeling and Automatic Modeling. So basically, with the outline of this presentation is, I will explain in general way to EPOS service that I already know. I explained the Monday about this service. After I will explain the automatic processing change in general way. I will explain how we can introduce the data setup, how function in general way in the aspects to nonlinear inversion, and how after the linear inversion to generate a slip distribution for every earthquake while they are working. I will show you some experimental results that are working in this project. More or less, we are tested with 100 earthquakes for the big catalogs, and also after I will explain the conclusion and future developments that we are approaching in the future. So, with as you know, we development automatic tool that provide the DINSAR products by EPOS service and thematic exploitation platform GeoHazard. We can check the code to visit the site, in this case the paper that I published in 2020. Basically, these automatic tools function every time there occurs an earthquake. The system catch the earthquake from different earthquake catalogs. We are working with USGS catalogs starting 5.5 until to the high magnitude, and National Institute of Geophysical Volcanology of Italy. Remember that we need to be in an institute to work in parallel with Department of Civil Protection, so we need to be operative in the seismic crisis, specifically in Italian territory. So basically, for Italian territory, we developed the algorithm that catch the earthquake for 4.0 until for 5.4. So this automatic tool works implemented in Amazon Web Service, and we produce every time there is a significant earthquake to different products. 2 days ago, we shared the experience with this automatic tool, with the automatic tool for Comet with Milan. We shared experience about to do how time of the download data, the Sentinel-1 data, and also the time for processing the DISOR results. So in this case, basically, we are processing total more or less on the 600 earthquakes from 2015, the launch of the Sentinel-1A, until to September 2000 of this year, until yesterday, basically, we are producing 45,000 products and interference maps, loss displacement maps, and occurrence maps. So every time that the system now is available, so every time there is, of course, an earthquake, we can access to information to the DISOR products. It's available in EPOS SAR system. So this is the char automatic chain implementation on automatic processing. Basically, we start to catch the information related to DISOR products from the EPOS SAR system and the focal mechanisms provided for different catalog of the seismology. In this case, we are provided with data USGS and also a National Institute of INGPU. So basically, I explained before, when I start the earthquake, this system in automatic way catch the information throughout the earthquake, start the processing, select the images, start the parallel space baseline, because it's the algorithm they use to produce this algorithm, produce this project, these products, and after to put all this information in the catalogs of the EPOSAR and geohazard expedition platform. So with using the focal mechanism, we create an expected, using the focal mechanism, the foul plane, and the foul plane 2, we are basically extract the expected area affected by the ground displacement. So in this case, we create a small bounding box that we suppose that maybe occurs the significant deformation of the area of earthquake. So in this case, this is an example for, in this case, with the improvement that we performed on the SBAS algorithm specifically to earthquakes. In this case, this is an example from Badran earthquake in Iran in 2021 in 5.8 magnitude. You can see here the interference, the ascending and descending interference. So basically, with the bounding box expected with automatic for the focal mechanism, we select the area and we cut just the area for the unwrapping phase. So it's not necessary, basically, in this case, let me say, works with all the descent of the Sentinel-1. Just we select the area of interest with support to this deformation area. So we are, in this case, the input information to the automatic modeling. In this case, there are different criteria to select the products of Sentinel. These are products. In this case, the first criteria is that we have to know the number of ascending and descending orbits using the inversion must be the same in this case. Just for example, of the earthquake, a cover just for the one orbit, automatically the system selects the co-seismic event of this track. So if we have the system of the automatic tool processing of the earthquakes basically works and produce in real time two co-seismic, these are co-seismic products. So using the two for 3 images. In this case, to select which interference, with loss displacement map, we need to select the short temporal baseline for every available track. In this case, if we have two co-seismic interference, we select, in this case, the short temporal baseline. So after to select, we select, in this case, the interference that has more current points in the area of interest. The other input parameter that we need to do to work in this algorithm is the loss unique vector files and digital elevation model provided by SRATM model. So we have input the loss displacement maps, we have the loss unique vector files, and we have the depth of this area of interest. So after to select the data, after to generate and start the input processing, we start with the nonlinear inversion. It's important to take account that this algorithm just function on this is a development just for the one foul source mechanism fault. So it's not, for example, if we apply this algorithm to job the earthquake, the Turkey earthquake in the past February, the automatic tool failed because just this automatic tool uses work with no fault, one fault parameter. So the nonlinear optimization is defined for the fault location, geometry, and rupture mechanisms to when you sleep, uniform sleep. This is basically the aiming of the nonlinear inversion. The nonlinear inversion works on also the refined source and coarse source. So this is basically how the function, the parameters. The first one, we are the source know the input insert products. We have the focal mechanism parameters, so we start to define the constraints. In this case, for defining constraints, we work on the range interval for every source parameters. We select the fault dimension, the position of the fault, the depth, orientation, take, and sleep. After to define the constraint, you start to the nonlinear optimization. In this case, we start the nonlinear optimization to find the best fit solution. In this case, a nonlinear inversion fault, using the Lambert of market scheme for marketing in 1963. Okay, so the algorithm tried to do obtain the constraints using the different parameters like the available in Simone Azzori in 2018 on the paper of Mexico. One of the parameters is the digital elevation model for the duration of the sleep. For these aspects, I suggest you to visit the paper to obtain more parameters in this case. So basically, after to select or create the first best solution source, there are different criteria to define the base source. In this case, the first parameters is constrained and corresponding to use with nonlinear optimization. All the parameters as constrained and they have best fit values with the minimum and maximum ranges. The direction of the sleep vector and the treated space different from that of the focal mechanism, more than 5.5 degrees from the foul. Okay, after to select, let me say the respect of these different criteria parameters, we start to do perform the more or less 30 iteration by default. If the process comes okay, the algorithm starts to function the linear optimization. So the linear optimization, basically, the objective is to retrieve the distribution of the shared dislocation of overfall plane identified by nonlinear inversion I explained before. So the first parameters for the nonlinear inversion is the B4 solution that I explained before and the source optimization to the subdivide the different page of the fall on the fall and the sleep. So in this case, we need to extension of the length of the width of the feed source. We have the fall the plane of subdivision of the number of different page, more or less, in the area of the fall mechanism. So, and after we work with this linear system. This linear system basically works to the parameters, the epsilon exchange for the small thing of the area of the sleep. So there are different values to this equation. Basically, the M is the vector of the sleep values, the D is the vector of the observation, and the G is basically the matrix of the sign values. The M, I will explain in the next slide how we select the matrix and division in G. So basically, subdivision page, we need to bear on numbers of very different page of the area of the mechanism of sleep. And we define different values in this case to define the matrix G. For define the matrix G, we basically define the number of inversion points that these inversion points comes for the loss displacement mass produced by insert products and subdivide for the page of the subdivision. In this case, the page subdivision is of the 100 of 1,000 page. So define of the stress consistent, basically the epsilon for a strain deformation consistent is basically of these values. I don't want specific details about this part because obviously this part concerns of all the geophysics aspect of the algorithm. So if you want more information about this aspect, you can check the paper that I will show you after at the finish of the presentation. So after to define of these models, we need to start to take different criteria to select to the data fit model, roughness, the curve characterization, and define for the specific event field of fit max and minimum to worsen the best fits of the values respectively. The damping factor is to set values corresponding to 95% of the field Feynman. In this case, the Feynman factor is in this equation. So we have defined the matrix in value UG. We have the value of D. So it's basically to say to find the value of M for arrive to of sleep distribution of the linear inversion aspect. So obviously, we need to establishment the algorithm is a completely automatic and unsupervised result, cannot be shared with scientific community without any validation. So the National Institute of Geophysics Volcanology in Italy have the different experts that are working in this project, trying to validate the products of the automatic linear inversion. So basically, this is an example of the results of earthquake in Ethiopia. We are experimental results for more or less 99 earthquakes tested for magnitude 5.5 until to 8.2. In these cases, we are using the earthquake catalog of the EPOS project. And just we are working with the small magnitude of 5.5 earthquake occurred in Umbre in Italy. So, but all these cases, basically 16 cases, 16 earthquakes, let me say, valid, but no, it's not visible the ecosystem pattern. So we select, in this case, just as 16 earthquakes of these 99 earthquakes, but there's no valid and ecosysmic pattern. The second 6 cases with the ecosystem is very, very small, so the signal was small, so it's not possible to select, let me say, the bounding box using the focal mechanism parameters. So in this case, it's discard these 6 earthquakes. And 6 cases with the rupture of different faults, the significant of the Hawaiian events of Amblin earthquake in New Zealand. In this case, the algorithm followed because obviously we have more or less the two-fourths of distribute in the interference. So in the loss displacement mass, it's not possible to start to do nonlinear inversion. And 11 cases, the modeling failed because there are displacement mass were affected by strong decorrelation. Remember that with EPOS our automatic tool, we don't discard the atmospheric effects because obviously we produce two cosmic interference. So to be sure that signal we tend to see in the interference is related to the deformation pattern in the area of interest. So in this case, 11 cases of the modeling failing because of displacement maps is affected by the strong decorrelation, let me say, of vegetation of atmospheric effects. So, and 60 cases, more or less, the 16% of the results, and in this case, the experimental results in modeling, processing is used faithfully and end with the retrieval of the variable sleep distribution. This is basically the map that represents the significant earthquakes. If we ask more or less why we select these earthquakes, basically we are based on to select these earthquakes dependently of the signal of the deformation pattern in the interferogram, ecosystem interferogram, and the loss displacement map. So this is some results on the sleep distribution of different significant earthquakes that you select for the catalog. And up to this moment, at the past Saturday, we are experimenting the seismic races in Morocco. So I show you these interference on the past Monday. We show you the disco-seismic interference for produce the loss displacement maps for the sending area of the Morocco earthquake. So in automatic, when I spoke and when I explained you the civil protection tools that we developed and I explained the past Monday and the last moment, the sleep distribution start to work in an automatic way. So basically, we need to be in Irasian air with support to civil protection. We need to be operative. So in this case, this automatic tool chair, the focus is focused to generate information in operative way. You can see the Twitter. I posted the Twitter, and in the same time, Simone Azzori, this is the colleague that works, and then they said, is the scientific that developed the algorithm to implementation post the distribution in the real time after the occurrence of the disinterference. So this is the paper that we can check. This is automatic seismic modeling source of the insert displacement. Basically, this works. This job joined the different efforts for research in Irasian air, experts in INSAR technique, and National Institute of Geophysics and Volcanology, the as experts in modeling source. So the conclusions about this and future advances that we are working now with this project is basically we create an instrument for quick and robust identification of the source parameters after of earthquake. Remember that I explained again that this automatic tool just works on the fault mechanism. So we developed an active service with the future magnitude 5.5 event of the global scale, and obviously the magnitude of the 4.0 until to 5.4 of European territory, just for study Italian cases. And the future, obviously, the extension of the catalog to all the sources detected for the INSAR Science 2015. We have, I explained before, we are processed more or less 605 earthquakes. So we have more or less 45,000 products so that we can create a big extension catalog about to do all these earthquakes that I performed to these products. So we are consolidation of the formats and metadata with EPOS now. Still, we are working on define the metadata parameters to put the result of the automatic modeling and with EPOS. So still, we are working to define the metadata to put this information in EPOS system, and obviously publish it to validate in the scientific community. And we are assisting the preparation for incoming SAR missions like NISAR, NASA ISRO, Roselle, Sentinel-1C. So we are here to wait for this future constellation to automatize and also to produce to this kind of results. So the extension of the LCLT, the extension to multiply source to modeling with artificial intelligence. We are working on to recognize basically the parameters to define, using the interference artificial intelligence to recognize the pattern deformation with using the interference. So this is all we can check here, the paper that published in the past August, the catalog sources, we can also access to all the information to all the more or less 100 cases that we are studying, and the catalog of the EPOS SAR service. I have in my email and Twitter from Simone Azzori and me that were the experts that we are working in this job. This is all. Thank you. Thank you very much.
Great, thank you. We have time for a few questions.
Thank you. For the 60 successful cases, were they fully automatic or were there some intervention still?
Okay, basically, these 60 cases all are functioning in an automatic way. But when I explain the presentation, the experts in geophysics area check that really validate the parameters so this is okay to produce the Lipps distribution. So nothing is in automatic because obviously we need to check if really the information that we are publishing in the scientific community is very effective. So we need to check before to publish something.
You showed one example where you said you could not really constrain the fault parameters because the signal was really small. Yeah, but it was clearly visible. And your catalog is meant to complement, I guess, the seismic catalogs that we have. I mean, it's building up on this, but it adds information. And one of the crucial information for shallow earthquakes is depth. So I'm wondering, so it's actually sad, right, that this is disregarded because we can say that it's not very shallow because the signal is very small. Yeah?
Yes.
So you can give constraints on the depth. If there's no mechanism, or you can say I don't know the strike or slip. So how do you deal with these? If there's something not constrained but other parameters are constrained, it would be very valuable. Are you thinking about changing this in the future?
Yes, obviously. For example, we are working with, National Institute of Geophysics and Volcanology catalog that basically we are working with, we are processing earthquakes more or less the 4.0 to 5.6. The automatic faults create the really small bounding box, so sometimes it's difficult to model in this data because it's not signal, so, and also because we are working with the Sentinel-1. We can consider the Sentinel-1, the pixel diameter is a little bit high to detect, let me say, these fault parameters for these small earthquakes. So we are experimented working the automatic processing of the
Oh.
Yes. So you said you're validating it before it is put online. I think it is, if I understood this right, I think it would be it would be useful just to produce something, put something out as fast as possible without having anybody look at it and just annotate it. Nobody has looked at it, and then it can be updated.
Sorry, can you repeat me again, please?
I mean, first to put something out as soon as possible without
yes.
without having it validated, and you just say
yes, obviously. Every time there occurs the earthquake and you see the signal by the interferogram, we know that the earthquake, we need to create the automatic mode, the start of automatic modeling to see really if it's necessary to change some parameters. If it's not necessary to change parameters to define, we can publish this information.
Yeah, I just want to make the point. I think it is important to have something out as fast as possible, even if it is not 100% right.
Yeah.
Great. I think we ought to wrap this up because we have time for discussion again this afternoon before the poster session, but very interesting results. Yeah.
Thank you very much. Just about this occasion, thank you very much for all, and also for Simone Azzori, that is the person that basically developed all the automatic modeling that we are working together. So thank you very much for your attention.
Okay, and let's thank all the speakers for their interesting talks.
This is session. From here. Okay. Earthquakes and tectonics. Yeah. Good afternoon. Welcome and welcome back. I think we should get started. Welcome to the Earthquake and Tectonics, the third session. In the interest of time, we'll get started. The first speaker here is Brian Rambo. He'll talk about surface displacement throughout the earthquake cycle over Haiti's southern peninsula.
Do you hear me well? Yes, cool. So my name is Rambo Brian. I'm a third-year PhD student at the École Normale Supérieure, and today my talk will be about the surface displacement throughout the earthquake cycle over Haiti's southern peninsula. So we are located in the Caribbean, where the North American plate subduced beneath the Caribbean plate at a rate of 2 centimeters per year. And actually, you can see that it is a quite active area with a lot of earthquakes. And we are going from a frontal subduction in the Lesser Antilles to almost a collision when we reach Hispaniola Island, which is there, with mainly strike-slip faults. So if we zoom in, this is the context of the Hispaniola Island, which is composed of two countries, Haiti and the Dominican Republic. And as you can see with the white stars, the past seismicity and tells us that this is an active area that delineates two major strike-slip fault systems. In the north of the island, you have the septentrional fault, which has a fault slip rate of 9 plus or minus 3 millimeters per year. And when you go down in the south, near Haiti, in the southern peninsula, you have the EPG fault, which has a rate of 7 plus or minus 2 millimeters per year from paleoseismology and models of blocks. So the EPG fault is actually quite well known for the the deadly and famous earthquake of 2010 and 2021. And you have also plotted there the GNSS velocity in the North American reference frame. And you can see that from the north of the island to the south, there is a huge velocity gradient, meaning that strain is actually heavily accommodated to the entire island through multiple faults. So we're gonna ask an easy question, which is not that easy to answer. There is, all strain is partitioned along this transpressive system. And as we have two earthquakes and geodetic data that covers one of the earthquake, we can go through multiple phases of the earthquake cycle. So here is the view. We have 6 tracks covering the island. So we're gonna process them all and stop at the correct time for the interseismic period for the track 4 and track 142. And for the post-seismic, we're gonna start right after the earthquake. So a bit of processing. I won't go too much into detail because this is not the point of the presentation, and this is well-known techniques. So we start with Sentinel-1 AB SAR images, and we do persistent scatter interferometry and also distributed scatter interferometry. First, for the persistent scatter interferometry, we process the SAR images with ICE2, and then we compute single-loop complex images in full resolution that will feed into stamps and to get a time series of PS, and then correct that time series with the train atmospheric toolbox. This will be it for the interseismic analysis. And on the other side, we will multi-loop the interferogram and wrap them. We'll use that for the co-seismic analysis and then correct the interferogram with PIAPS and ERA5 atmospheric models, and then feed that into the Kalman filter time series analysis to extract post-seismic displacement. So directly to the results, you have there plotted the PS velocities. On the top, you have the descending track, and on the bottom, you have the ascending track. And when you look at that, you can see on the descending track, actually, that there is a velocity gradient through the septentrional fault, which is there. So we have a velocity gradient on this fault, but we also have the same thing on the EPG fault, which is on the southern peninsula. And actually what you can see is that the velocity gradient is opposed in both line of sight, which actually means that strain is accommodated there, and also that given the line of sight geometries, that this is mostly left lateral. So we are happy in a sense that it matches the transpressive context of the area. So we also have the GNSS data in the ITRF reference frame that we projected to the ascending and descending line of sight. And we plotted one against another. And you can see that our velocities, our INSAR velocities matches quite well our GNSS velocities plotted in the ascending and descending line of sight, projected, sorry. We then reference the INSAR velocities to the GNSS velocities. So you have there an average profile along the septentrional fault, and what you can see, you have in red the ascending INSAR velocities, and in blue the descending velocities, and we reference each profile across the distance from -20 to -40, and you can see that at the fault position it diverged, meaning that there is an opposite gradient of velocities on both line of sight. And when we plot then the GNSS ascending velocities projected in the ascending line of sight, sorry, and the GNSS projected in the descending line of sight, you see that it matches quite well our INSAR data. And now, if we take a look at the APG fault, strike slip, we can see that we can fit the displacement that we observe in the ascending and descending line of sight very well with a simple strike slip screw dislocation. So this is a bit intriguing because we are in a transpressive system and we matches quite well the strike slip. We matches quite well, so is the velocities with strike slip only dislocation. So there might be things in the INSAR that maybe we cannot see the north-south convergence. So we extract APG fault looking depth and the APG fault slip rates. This is still work in progress, but this is actually good stuff in our opinion. So partial conclusions about the interseismic period. We have an interseismic PSTD that agrees well with the GNSS campaign data. We model with a strike slip only dislocation the GNSS, the ascending and descending velocities. So what about the convergence across the transpressive system? Maybe the ascending and descending line of sight might be insensitive to the north-south convergence, which is probably the case. So we're going to need to take the 3D GNSS in the future. So in our estimated rates also, we are in agreement with what paleoseismology and model of blocks says. So now that we have seen that in the interseismic period, there is a strain accumulation on faults, we're going to go through the coseismic period and see if the release matches the transpressive system in a sense that what is released during the coseismic period. So you have there the GNSS displacement, coseismic displacement on the top left corner. And on the bottom line, you have the descending Sentinel-1 and descending ILOS-2 data, and you see that the pattern matches quite well, while it is completely opposed in the ILOS-2 ascending track on the top right corner. So actually, what we can extract from that rapidly is that, this area has been going up because we can see that it is red in both line of sight, and this area, we have an opposed pattern in displacement, so it means that it is mainly strike slip motion. So we have a dual release during the coseismic with a strike slip and deep slip. So a rapid model of the coseismic displacement that you can see there, and you can see that we have two faults that matches well the displacement that we can observe at the surface. So we have the rupture of two faults, but not the APG fault, which is quite intriguing because it is known to be the fault that have been ruptured in the past years. And also we have an overall moment of 1/3 of deep slip and 2/3 of strike slip, which actually matches quite well the interseismic velocities that are being accommodated there. So we can see the partitioning. So this is a coseismic model from the published study, and actually we have the same story. It ruptures first a secondary thrust and then runs parallel to the APG fault with only strike slip motion, as you can see on there. First thrust and then strike slip motion. And it also ruptures another fault than the APG fault, as highlighted in red on the bottom left. So partial conclusion about the co-seismic period is that we have rupture of secondary thrust fault rather than the EPG fault, and we have also comparable faulting event in 2010 and 2021. Actually, we see the partitioning of the transpressive system during the co-seismic release. Now, what can we see in the post-seismic period, which is, in my opinion, the most interesting part? So, in 2022, Yin and collaborators, as I think Yin is there, Zoe, sorry, and they observed co-seismic fractures in the wake of the 2021 earthquake. So they also identify some post-seismic slip on secondary faults, and these fractures actually hold right lateral motion and left lateral motion. So this is a bit weird because we are in a transpressive context, which is mainly left lateral. To see right lateral motion is something that we did not expect. So to match this quite quickly to the Coulomb stress changes associated to our 2021 co-seismic model, what we can see is that for a vertical strike slip east-west fault, you can have the fault in green that are located in the areas of Coulomb stress increase, which matches actually the fault localization. So maybe the co-seismic fractures are linked to the Coulomb stress changes. So actually, we wanted to be sure of what we observed. So we processed Sentinel-1 data right after the earthquake. And we identified in the cumulative line of sight time series the multiple faults that have been activated. Some are matching the one that Yin and collaborators found, and some are new ones. We interpolated ascending and descending time series and project them to EPG fault parallel and vertical displacement. And after that, we draw systematic along strike profile for each fault with fault parallel displacement projected along fault azimuth. This is what we get. We have faults that are moving after, in the wake of the 2021 earthquake. We extracted a long strike fault offset displacement on regularly spaced along the fault, and as a function of time that is plotted there on the top. We measure the step across the fault by subtracting the mean values within a given length of the fault trace on each side. And actually, this is not the only one. We have 14 fault segments that are holding left lateral or right lateral motion. We also checked on the row ascending and descending time series to be sure that what we observe is actually something true. It is the case. And when you look at it in another way, on the, for example, the figure on the top left, you have the the cumulative offset at the maximum creeping location of the fault as a function of time. And you can see that it has a logarithmic decay characteristic of after slip, but that is not on the fault rupture. So secondary faults there are slipping after the 2021 earthquake. So as we see after slip, we linked that to rate and straight friction law. Basically, it tells us that the cumulative offset is equal to those parameters up there, and that we can extract A minus B values telling us the fault behavior and fault rheology. And what we get is that all fault segments have a rate strengthening behavior, which is characteristic of faults that are prone to slip aseismically if stress is applied on them. So we had a few questions about what we can see. So we first thought it was a compliant fault zone, but it looks like it's not purely elastic because we have a time dependency. We have a characteristic time for slip, and so we removed that hypothesis. So then we have the logarithmic decay of fault slip, meaning that the fault has a response through time. So we thought about a viscous response. But for a 5-10 week event, the drop of viscosity for such event will be very unlikely. It will mean order of magnitude for a drop of viscosity that is impossible. Sorry. So it's most likely frictional. And now, the most interesting feature is that when we compute the Coulomb and shear stress redistribution, we computed it for each fault orientation, and we see that fault creeping segments are in area of Coulomb stress increase. But when you look at the plot on the right, we have faulting type that depend on the shear stress variation. what I mean is that this part is for left lateral faults, and this part is for right lateral fault slip motion. So depending on the shear stress variations, we have faults that are moving in the sense of the shear stress. So this is a partial conclusion about the seismic period. We have multiple secondary faults activated. We have frictional rate strengthening behavior for all segments, and we have a strong link between the co-seismic stress redistribution and the Coulomb shear stress variations. And what we think is that secondary faults here are passive markers responding only to the shear stress variation in Coulomb stress variations. If you're not sure about what I said, we can have a look at what's happening after 2 earthquakes in 2022, 2 magnitude 5 earthquake, for which we extracted the displacement in the time series. And we plotted there the earthquake timing in red. And you can see that right after the earthquake, the fault NE1 and NE2 that are there are slipping. So this is something that is happening a few times in the same fault zone. And it matches the Coulomb stress increase areas. Now, if we take a look at the 2010 earthquake, because we have data also for that, but on the ALOS one, we have a small time series of 5 images, and we draw a profile to the red rectangle that you can see on the top left. We see that there is also a fault slip happening there. So, summary and conclusions. We highlighted in this presentation the partitioning of the transgressive deformation that is visible in the GNSS data and in the co-seismic period. We have large ruptures that initiate as thrust and evolve as strike slip fault when they get closer to the EPG fault. The EPG fault is actually locked at depth while presenting a rate strengthening behavior in its shallowest part. And the main result of this presentation is actually that we have a frictional response of multiple secondary faults to the Coulomb stress redistributions, which actually means that we have passive markers reacting to stress. Thank you. Sorry. Thank you for your attention.
Yeah, this is very interesting. It seems to imply that there is simply no stress in the topmost layer of the Earth. It's completely stress-free. Unless you have some kind of a compliant material and you're seeing some kind of a decay constant of a finite width zone, could you really tell if it's on a really sharp boundary? And then can you say anything to which depth it may extend this kind of motion?
Sorry, can you speak a bit louder for the last
Yeah,
part?
so twofold question. Can you rule out that this is not a shear zone with finite thickness? Is it really a sharp fault boundary that is moving? And can you say something about to which depth this secondary fault slip or motion reaches?
Actually, yeah. I will try to answer the question. I think that is something fault slip because actually we saw that from the study of Yin and collaborators in 2013 with values to stake phase gradient that there is no unwrapping in that. So it's most likely pure information. They identify the fault fractures, and if I remember well, they also identify some post-seismic slip on those fractures. I mean they say that they saw the fault slip. So I think that is a good agreement with what we are seeing there. And yeah, and about the compliant fault zone, actually the context of this area is a bit weird because we have oceanic crust that is the arc of the southern peninsula, and we have a fault thrust that is just north of the peninsula that is abducting what's can be called some other continental crust. So we have some kind of probably weak, very weak fault zone with a lot of stress in that. That can, I would say.
Okay, John.
Thank you very much for that.
the EPG fault seems to be not doing anything in your total analysis of the earthquake cycle. I mean, what strong evidence is there that it actually exists as a locked vertical strike slip with a shear zone vertically beneath it?
Okay. Yeah, actually, the field tells us that it is a strike slip fault. I mean, there is features from the field that actually this cannot be something else than a strike slip fault with large earthquake that happened in the past. But yeah, actually we do not have that much information for now because the political situation there is a bit unstable, and so I wish I could go there too.
but that it persists as a vertical extensive structure?
For the vertical, yeah. Some studies from geological mapping tells us that to the east, it's most likely not vertical, but southward dipping. But we do not know what's going on there, unless that we have some aftershocks relocations that seems to align along the vertical structures after the 2021 earthquake. So this is not an answer, but this is some first guess.
Okay, thank you very much.
All right, we should move on. The next speaker is Chi Yu from University of Leeds. She'll be talking about large-scale velocity mapping over Tian Shan Mountains.
Thank you so much. As Sanho said, I'm Chi Yu, a postdoc at the University of Leeds, and today I'm going to present our group's collective effort mapping the large-scale velocities over the Tian Shan Mountains. So here is Tian Shan, which is a reactivated orogenic belt at the northern front of the Alpine Himalayan belt. And these are the velocity vectors. As a whole, the Tian Shan Plateau is absorbing about half of the convergence between India and Eurasia. If we zoom in, we can see the velocity vectors fan out as it shortens. How this deformation is being accommodated through the fault structures here is not 100% clear, and which faults are more active than others, and how fast is Tian Shan rising, or is it? So these are the 3D vertical velocities being compiled from different studies. The brown points are showing uplift, whereas the green points are showing subsidence. So we are seeing really a mixture of both. From our past experience, we know that the high resolution INSAR velocities have really helped us identify the sources of the potential vertical motions. And we would like to do the same for Tian Shan. So this is our INSAR coverage. We processed 90 LIX frames of Sentinel-1 data acquired from 2014 to present. It's a really challenging area, as you can see from this average coherence map. And apart from the Kazakh platform, Stable Eurasia in the north, as well as the fold and thrust belt in the south, we almost have low coherence everywhere. And because it's a hard place to do, we gave it our best shot. We came up with a Tian Shan strategy, which is LIXAR processing chain with a twist. The differences are we used the Copernicus 30-meter DM to do the topographic corrections and the geocoding better. We chose a primary epoch somewhere in the middle of the long time series to facilitate co-registration. We processed interferograms to 50-meter resolution to give us a better chance of preserving more pixels in the end. And for the network, we make interferograms with every 5 consecutive links, as well as 3, 6, 9, and 12 months long temporal baseline interferograms. So I have a great redundancy to start with. For the time series analysis, again, we are using the LIXBus system and with the twist. So apart from picking out interferograms with missing burst, we also automatically detect interferograms with co-registration errors and implemented a way to automatically correct unwrapping mistakes rather than mask out unwrapping mistakes from our interferograms based on the residues derived from time series analysis. We use all interferograms processed to do this first iteration of time series of time series inversion and unwrapping mistake correction, so that we have more robust residues to help us with the unwrapping mistake correction. And once we are happy with the interferograms, we drop all the 6-day, 12-day interferograms to mitigate potential phase biases problems. So this is an example of our final data set. We are losing a lot of winter epochs, as understandably, because there's the snow cover in the winter. But in the end, we have strongly connected networks with no gap in between and no loop error, and with residue RMS below 1.5 millimeters. So the effort is paying off. If we mosaic the frames along track by a constant between them, we can get those long, smooth line-of-sight velocities. And this is what they look like in total as a whole. To the first order, we can see this ramp, a long-range ramp across all tracks. And then that is because of the plate motion as seen in the line of sight due to the changing instance angle. And this we can forward model and correct using an approach demonstrated by Stephenson et al. 2022. These are the plate motion corrected line of sight, which is totally independent from GPS velocities. However, you can see this mismatch between the tracks is starting to pop out as we move down the track. And then this is an example of the uncertainties being accumulated as we calculate more and more constant offsets between them. So maybe in the future, when we have the ETAD data ready, we can potentially see if the ionospheric corrections can help us mitigate such problems. But for now, GPS is our friend. I would like to thank Chris Rollins for helping me compile this great data set of 673 GPS velocities from 24 publications, and they are converted into the ITRF 2014 fixed Eurasia reference frame. All the velocities are cleaned by an uncertainty threshold, grouped by the station names, and averaged by location. You might notice that not all of my frames have a good distribution of GPS points. To solve this problem, we have to create some dummy GPS points. And as we can see from the backdrop, which is the interpolated east velocities from the GNSS in the top panel, not all GPS velocities in Kazakh platform have 0 velocities. So we decided to sample the interpolated east velocities from the GNSS at those locations, which we need to help mosaic the interferograms. And because they are interpolated, we also sample the uncertainties from the interpolated uncertainties. So those dummy GPS would have looser control to our inside data as compared to the real GPS data. And this is what our approach in the north. In the south, where there's the clockwise rotation of the Tarim Basin relative to fixed Eurasia, we decide not to use the interpolated GPS because the GPS is too sparse there in the desert. Instead, we forward calculate the Tarim rotation for the horizontal velocities and assign an arbitrary uncertainty for the vertical component. This is our stitched line of sight velocities after mosaicing by fitting planar ramps to fit the GPS line of sight velocities. And you can see they are much more coherent now. If we decompose the line of sight just now, we can get this large-scale east and vertical velocities in ITRF 2014 reference frame in fixed Eurasia. What do we get here? If we compare this data set to the GPS velocities, we can get this difference between INSAR and the GPS at around 1.5 or 1.7 millimeter per year. If this uncertainty is equally divided between the two data sets, then we have uncertainties of the INSAR velocities below 1 millimeter per year. So what do we get here? The most obvious signal, I guess, by far you have already noticed, is this subsidence near the city of Urumqi. And this is where we have groundwater extraction to help with irrigation. And if we zoom out a little bit, can you see this broad signal of gentle uplift? And if we plot this profile perpendicular to the field, we can see this shoulder of uplift on each side. And then this is likely an elastic bending, a bending beam problem, which can allow us to model for the elastic thickness. If we move here, this is the fastest melting glacier, where the glacier is thinning at a rate of meters per year. And what we are measuring is about 6 millimeter per year of uplift. So we interpret this signal as glacial isostatic adjustment. If we zoom in even more, we can see some earthquake signals. For example, here is the Jiashi earthquake, Jinghe earthquake, Hutubi earthquake. And if we want to zoom in even more, we get to the resolution of our data set, which is now at 500-meter resolution. And we get to see signals to do with the local mining activities, perhaps, and slow landslides. Now, let's come back and think what we can get out of this for tectonic signals. So we can calculate the tectonic strain by using both the INSAR and the GPS, interpolate the GPS north velocities and the INSAR east velocities on the left. We treat them equally and then apply the same filter, median filter, with a 100-kilometer window. Then we can calculate the horizontal velocity gradients for each data set. Indeed, we have most of the strain of velocity gradient signals in the GPS node component because this Tianshan is dominated by east-west striking thrust faults, which accommodate this shortening. But we can still see something in the dVe, dx, dy velocity gradients. If we combine the velocity gradient component, we can derive the second invariant, maximum shear, and the dilatation rate fields for this area. The strongest signal here is in the middle, which corresponds to the Kakura creeping section. But we don't see it much in the east-west velocities. So even though we have most of the velocity gradients in the GPS node component, I would still like to draw your attention to this very nicely localized shear, which is picked out by the dVe dy component. And if we compare that with the same component calculated from the east component of the GNSS, we can see how inadequately localized this velocity gradient is if we only have GPS velocities. And by the same reasoning, we can imply how the north velocity gradient components are also imperfectly localized at that point. Apart from that shear zone, we can also see this diagonal band of staircasing of the dVe dx gradients. And that seems to tell us about some distributed pull apart motion here, where to the right, the east velocity will be moving to the east, and to the left, it's moving to the west. And if we really try, we can see some small velocity gradients along the Talas-Fagana fault, on which we can then plot profiles to see a bit better. So these are the profiles on the Talas-Fagana fault, and we can just about measure about 1 to 2 millimeter per year of velocity step on this fault. And here, if we plot the profiles on the Kashgar coping thrust system, curiously, can you see this length of Kashgar coping thrust system being almost dislodged and moving to the east together with the wedge, triangular wedge on the east, also moving to the east, as if it's separate from the background in the north and south. Now, if we plot profiles perpendicular to the thrusts along the diagonal where we see the strongest velocity gradients, we can see mostly the gentle slope, almost with distributed uniform slope along the profile. But there are some localization which I picked out here with the red circles. If we draw this profile the other way around, perpendicular to the diagonal, again, we are seeing those smooth gradients and with some localization. So not all the localized share are associated with active faults in the global earthquake model fault database, but they are all in the COMET Tianshan active fault database, which is coming up. So yes, stay tuned for that data set as well. So we look forward to comparing both data sets and interpret a bit more on which faults are active and what do we know about them, the slip history, etc. So in summary, what we have done here is to process 8 years of Sentinel data over a large area to produce the east and the vertical velocities at 500-meter resolution, covering 1.6 million kilometer squares of Tianshan. Here we are observing distributed east-west extension with some localized share on faults which are currently missing from the global earthquake data fault database. And we are getting a lot of information, tectonics, non-tectonics, in the vertical velocities, and their spatial pattern is helping us interpret what they are. And both the velocities here, as well as the COMET Tianshan active fault database, are being fed into the global earthquake model to improve the hazard models for the next generation. That's all my talk. Thank you so much.
We have time for a few questions. I have one. That's interesting that you created the dummy GPS stations. Did you have criteria for creating such dummy stations? For example, did you make a rule that one dummy per frame, per scene, or how did you decide?
So if I scroll back, the decision was quite based on trial and error, to be honest. So our initial approach was to use as few dummy GPS as possible to pin the edges of the frames where I don't have a good distribution of the GPS velocities. But that's showing some stitching problems across the track, and then we can see the track boundaries, which will be picked out as fake signals in the strain rate map. So I ended up adding more GPS, especially at the track overlaps, so as to tie them better, but giving them this large uncertainty in the interpolated GPS uncertainty map down below, so that the uncertainties are big, but then their distribution is optimized to stitch the tracks together.
Thank you.
Amazing data sets. Thanks, Chi. We know from the past that in that corner of the Tarim Basin with the Pamir, there are a whole series of folds, anticlines, that we think are fed by thrust faults. Do you see any variation in uplift along those folds?
Yes. I didn't zoom into those. They're in a tiny corner. Yes, it's in my data set, but I didn't zoom into that yet.
Yeah, thank you. Very nice data set. There's also an interseismic velocity model by Sabrina Metzger in the Pamir, right? I was wondering, I mean, always you ask how's it going on, like south of this and west of this and east of this. Do you have overlap? So could you stitch together these data, even though maybe it's a bit maybe shorter the time series of her publication? And what happens where Pamir is meeting Tianshan? I mean, this is there's a major divide. This is somehow at your corner.
Yeah, that's a good point. I haven't mosaic our velocities together. I think we have overlaps, but I'm not sure whether we cover all corners in that overlap. Yeah, I should check. Yes, and then as I think at the backdrop, since we're on this slide, the top panel is the east-west velocities interpolated from the GPS, and then we can really see this sharp front at the Pamir front fault.
Okay, let's move on to the next talk.
Oh, yes. Let me introduce.
No, I can. It is
So
me.
So the next talk is given by San Ho from Earth observation of Singapore, talking about optimally balancing INSAR observations for the damaging November 2022 magnitude 5.6 earthquake in West Java, Indonesia.
Thank you, Chi. I moved to Singapore during the pandemic, and there was a new lab building effort in Singapore. So I'm leading that lab, which is Earth Observatory Singapore Remote Sensing Lab. Because it was created during the pandemic, I thought I would give you some short introduction of the lab. So August 2021, we started with 4 founding members, as you see on the photo. This is Cheryl, my PhD student. This is Lynn, my research assistant. Now she's becoming a master's student at University of Bristol, working with Juliet Big. And that's Eleanor Einsko. Some of you are aware of her already. She studied in the UK and now a research fellow in Singapore. They're all here, flying 14, 15 hours, taking 4 hours train ride. So if you see them, say hello and talk to them. So the group is growing. As you can see, we have 6 Singaporeans, 2 Indonesian, 1 Filipino, 1 British, 1 Nicaraguan, and 1 Korean American. So what we do, we use satellite remote sensing, radar remote sensing mostly, for humanitarian assistance and disaster response. And in between the response support, we develop, improve, innovate algorithms, and sometimes AI. We tried RNN, we tried Conval STM, Pred RNN++, and then also we improved the automated system that would automatically discover, access, process, and produce decision support product. Impacts to date, we supported a lot of events since 2018 when I was in JPL. I was at JPL for 14 years and came to Singapore 2 years ago. But since 2018, we started collaborating with EOS and we cloned the system that was developed at JPL. And since the beginning of that collaboration, we supported 81 events to date, including the Libya flooding that we just produced and we're delivering as we speak to the World Food Program, as well as the Morocco earthquake that occurred last weekend. You can see geographically we focus on Southeast Asia, but for big events, we also support elsewhere. As you can see, the Beirut event, for example, this one here. After the explosion in Beirut, 30 minutes after the event, Sentinel-1 acquired SAR data, from which we produced a map that was used widely by NGOs and responding agencies. Featured in a lot of media, like New York Times, Washington Post, BBC News, National Geographic, and Fox News. Some turning points of our disaster response support after the Beirut event support. I got an email out of the blue from FBI saying that, oh, thank you so much for sharing your map. We were able to discover several places that are heavily damaged, which would otherwise not be discovered. So that was very nice gesture from FBI. I didn't expect this coming from explosive unit. So that's first and last email that I ever received from FBI. For some reason, they were out there checking what happened, right? After 2016 Central Italy earthquake sequence, geotechnical engineers, a group of them went out and made ground observations and confirmed that our map correlates well with what they observe as a geotechnical engineer's eyes. Back then it was as part of ARIA. I was leading the disaster response of ARIA project at JPL and Caltech. Also, Barack Obama praised our product when he was hosting Matteo Renzi, former Prime Minister of Italy, at the White House. I was invited to give presentations at the White House Conference Center 3 times following Louisiana flood, Central Italy earthquake, and Mexico City earthquake. And our map of Hurricane Dorian damage map of Bahamas was featured in the cover page of Science. I'm sharing this because I started this effort in 2009 with passion and with a group of capable people. I thought we would achieve this kind of stuff like a decade earlier. It takes more than a decade to penetrate through the resistance and convention of these responding agencies to make it really, make our maps really be used for response. So something to think about. It doesn't mean that you produce something that is potentially useful, automatically gets used. After Turkey earthquake, we produced a lot of maps covering 204,000 square kilometers. I call that 280 times the size of Singapore within 10 days, and deliver this map to the United Nations World Food Program. This is the organization who won the Nobel Peace Prize in 2020. And it's an organization that operates 30 ships, 100 planes, 5,600 trucks on the move every day. And whenever there's a big event, they need to know how many people are affected right away. So our map was quickly shared, produced and shared, and in Ankara, the Emergency Management Center in Ankara, they downloaded our map to their cell phone before they dispatched 10 teams of 50, almost 60 people to go out on the ground to make observations. Also, the World Food Program, they had a luxury to compare a lot of different products and then decided, they discovered that our product produced the number of affected people closest to the number that was generated by the Turkish government based on ground observations. They compared with all sorts of MIT product, Google, Microsoft, and Defense Innovation Unit, UC Berkeley, AI, high-resolution optical. They collected everything that are possible out there. And then they ended up writing a proposal and submitted to their own headquarters to support my lab. I didn't ask for it, but apparently they saw the value of it. Now this part 2, this is what actually I want to talk about. One of the events, there were a lot of events that we supported. One of the events was in November last year, and it's a moderate-sized earthquake, magnitude 5.6 in West Java, Cianjur earthquake. And that was quite alarming because it's a very fatal event. 603 people died of magnitude 5.6 earthquake, which is quite unusual. It has important implication because there are like 50 million people living in West Java. So for that event, we produced damage approximate, as you can see in the middle, but on the top right, you can see 166, almost 7,000 people were displaced. And the pressing question was, where is the safe place when they were building shelter for the displaced people? So they were talking about candidate 1, candidate 2, candidate 3 spots, and these crosshair image is showing the location of the double couple quadrant. And the question was, which one is the fault plane, and which one is auxiliary? You would think with INSAR, it's an easy question, but for small magnitude earthquake, it's not easy. So I'll show you the interferograms, and this the star is the USGS epicenter, which is about 10 kilometers away from the actual geodetic observation made by INSAR. So this is the ALOS 2 interferogram, and one ascending, the other descending. You can see the double couple, sort of double coupleness here, this plane and this plane. And in this case, if you have two interferograms, how would you use for your own inversion to estimate the slip distribution? By the end of all this very technically dense meeting, we talked all the fancy corrections, ionospheric correction, tropospheric correction, closure phase correction. And then at the end, what you need to do is you need to decide how to weight the interferograms. I have not heard a single detailed description of how people are weighting the interferograms. I remember Shawnee was saying like yesterday, we paid attention to weighting. Now, I want to pay more attention to this weighting issue. So you might think, okay, half and half, how about that? That sounds reasonable. Now the problem is, there was another interferogram because the second and third is from wide swath. And they share a very similar look angle. In that case, how would you weight those three interferograms? Is 0.3, 1/3, 1/3, 1/3, is that okay? Or is that not okay? If that's okay, let's say thought experiment, if the second and third became closer and closer and became identical, then what would you do? You end up weighting 1/3 and 2/3. Is that okay? Well, you just said half and a half is okay. Well, I just said half and a half is okay. Now, 1 and 2, 1/3 and 2/3 is okay. There's this fudge factor. You start finding yourself suddenly having to hand wave by the time you have to wait between different data sets. So that's what I want to address. So these are the three interferograms again, just to show you the detailed structure. This is rewrapped at what it would look like if it's X-band. Although this is L-band, you can see the structure of the deformation. And you can always estimate the spatial correlation by calculating variance and covariance matrix, but this does not solve the problem because this is data noise. But we want to talk about data signal and how important data signal is depending on, this is all about geometry. So look at data importance. This was coined by Menke, 1989. When you have model prediction, D pre, which is calculated by design matrix times your best fit model, then you can replace that model with a generalized inverse times the observation, right? You all are very familiar with this. And G and G general light inverse is what is called data resolution. And the trace of that is data importance. And that use of that work is not new. It was published in 2005 by Rowena Lohman and Mark Simons. And they compared different scheme of data reduction. In SAR, we have luxury of too many pixels, so we have to reduce the data points, and how you reduce matters. So this is about balancing pixels. And as you can see, the first two, first row, first, second, third, fourth, the results is quite different. In the second row, here, the top row shows the true solution. I think this was derived from Hector-Mine earthquake. But then the following rows, you can see the visually quite different. So it matters how you balance the pixels. Now then you use the data importance space subsampling. You can calculate just by plotting the data importance or trace of data resolution matrix. You can produce this data importance of each interferogram, first, second, and third interferogram, if you're looking at north-south trending fault plane. And that changes if you assume that it's a east-west trending fault plane. We go back and forth, north-south versus east-west. And then based on then important data importance calculation, we can assign a number of points to each interferogram. And it turns out for north-south trending, the balancing of the interferograms, the weight that we should give to each interferogram should be 0.66 for the first one, 0.14 for the second one, and 0.2 for the third one. Notice that the sum of the second and third is still smaller than the first one. So it's far from one-third, one-third, and one-third. And one way to maybe visually show the data, the reduction, your reduction scheme, and how you weight is assigning the proportional number of data points to reduce to. For example, if you want to use 1,000 data points for your inversion, you can distribute this way. And this is when you assume east-west trending fault plane, then you have this number of data points. So this is a work in progress. To summarize, satellite SAR observations has become one of the mainstream information at the forefront of disaster response. It took a lot of disaster response supports, communication, a lot of emails, a lot of presentations, but at last it's validated by response agencies. It's being now used, geotechnical engineers as well as Federal Bureau of Investigation. November 2022, magnitude 5.6 Cheonju earthquake really highlighted the need for rigorous balancing of multiple co-seismic interferograms, because if you come up with the wrong answer, that really affects 167,000 people, displaced people's location in a not very safe place. Again, this work is in progress, and I think data importance-based balancing has a great potential to move forward. Thank you.
Thank you for the great talk. Do we have any questions? Yes.
I would have actually two, but I start with the first one. So I'm wondering, why is it so it's important to get the fault plane right to estimate where the aftershocks are closest then to candidate 1, 2, 3. But isn't that an information you get from aftershocks often earlier than from the second imagery? And also, I guess also in seismology is the answer, because sometimes if you have closer stations, you can get for larger earthquakes the directivity. Also, so is the solution maybe elsewhere? Because otherwise I would say, why
we cannot tell, and then you just have to account for both cases?
That's a very good point. Seismic data is available almost immediately. It depends on the distribution of seismic stations. The accessible seismic station distribution was not ideal. If you right west of the epicenter, there's a Mount Gede, where we have our own network of seismic stations. But the station is only one side of the main shock. So aftershock, we tried relocating the aftershock seismicity, and it was not showing any. They did not align in any preferred direction. It was all cloudy, always cloudy. We even work with local collaborators in Indonesia, the government agencies. They went out in the field, made field observations. It was inclusive because it did not clearly break the surface, and there were damaged ground cracks in both directions. So one day they said this is the fault plane, and the following day they said this is the fault plane direction. So there was a lot of confusion for many days, or many months, I should say.
Thanks, very nice talk, Franco. I was wondering if you always change your data importance subsampling every time you change your geometry. Do you run the risk of somehow having a runaway, that your fault geometry goes astray because your data importance data subsampling will somehow follow that? So
That's true. Yeah. Data importance requires your a priori knowledge of fault orientation. That's the drawback of what you proposed much earlier. Of course, then your approach and Mark's approach is prone to error, data noise. Yeah.
No, I mean, if you're searching for the geometry and then you subsample each time, you see what I mean? If you would do this in an iterative process, that you would always change the data subsampling each time that you come up with a new geometry from the Monte Carlo approach.
Yes, if you are running nonlinear inversion trying to come up with the best fit orientation, fault geometry, then you have to resample every time. So that is true. You can't get out of it.
That's why the question. You could run in the risk that this would run away into some corner, you know. If you do this always, if you subsample every time that you change the geometry. I wonder if it's a stable optimization or not. That sounds like it could be that you would need to realize it somehow.
I think you just said something important, but I didn't understand. So you're suggesting something?
Well, if you have a nonlinear inversion looking at different, searching for different geometries, it seems like you need to subsample your data again and again.
Yes.
And this could be a runaway process, such that you would run into the corner with your geometry and end up with one data point, I would think. Unless you put some kind of a regularization into the system that you have a minimum amount of data points on a regularly sampled across the space.
I think there are a lot of different sampling schemes when you run inversion, but I think if you, in this case, if you remember, the focal mechanism from USGS was quite supporting the vertical, either this or that. So that sort of ruled out all the possibility. I mean, that's usually we get that information. So we have some knowledge of range of orientation, hopefully.
Great. I'm sure there will be a lot more questions, and I was too absorbed by the talk, I forgot to keep track of time. That was the alarm for 20 minutes. So let's keep all the questions to the roundtable afterwards, or maybe after the session. Now let's move on, and yes, we have the next speaker, Professor Tim Wright from the University of Leeds. I'm sure you'll know him now. So he's going to talk about from Turkey to China, tectonic strengths and velocities in the Alpine Himalayan belt from Sentinel-1, INSAR, and GNSS.
Yes, good afternoon, everybody. You'll be pleased to know I'm not going to sing.
again. I'd like to present some results, really, the sort of an update on our mass processing effort. This is not something that one does alone. I've had the pleasure of working with lots of brilliant people over the years. Many of you are in the audience. Many of you are at Fringe as well. So it's been a real pleasure to have so many friends, colleagues, collaborators here in Leeds. So we're in an era of geodetic big data. This is just the GNSS sites that are processed by the Nevada Geodetic Lab. There are many, many more than that. This doesn't include all the continuous stations in China, for example. And INSAR, so Sentinel-1 has acquired a vast collection of SAR data over the whole Earth, but in particular the Earth's tectonic areas. Within the Comet LIXAR system, we've now processed more than 1.3 million interferograms. We'd like to be able to combine all of this information to get high-resolution maps of tectonic velocities and strains on a continental scale. So I guess the first question is why? It's a lot of work. I think primarily we're interested in seismic hazard models. If we look at the conventional way of calculating seismic hazard, it's primarily based on earthquakes that have happened in the past. The idea is if we can measure strain, it should be causally linked to future seismic hazard. There's a couple of correlation plots here, which doesn't prove causation, of course, between the earthquake rate and the strain rate. These are from this paper that was mentioned before by John Elliott and colleagues, but you show both in California and Eastern Turkey this nice correspondence between strain rate and earthquake rate. We have a particular interest in the Alpine Himalayan belt, and really that's due to the high vulnerability to earthquakes. There's a distributed zone of intense seismicity here, and if we just plot earthquakes based on the number of people who've died with a minimum threshold of 10,000 events, about 3/4 of those events are in the Alpine Himalayan belt. Okay, so I'm going to give you a bit of a method that summarizes how we do this work, and then I'm going to focus on Tibet within that study, and then I'm going to show some highlights from work across the Alpine Himalayan belt, and then talk a little bit about the future. So, how do we do it? So this is the sort of summary of the methodology. We make the interferograms. We then invert for line of sight velocities on a frame by frame basis, and then we invert simultaneously the GNSS and the INSAR to get both the INSAR into the line of sight, into the reference frame defined by the GNSS, and also to solve for the 3D velocities and strains at the same time. So let's start with making the interferograms. You've heard a bit about LIXAR before. We're doing that on 250 by 250 kilometer frames in general. There's a few bespoke frames that are bigger than that, particularly where they automatically define boundaries. We're right on top of faults, and that's not ideal. So there's a few but in general, they're 250 by 250 kilometers. You can read more about it in the Lezecki et al. Paper, and in Milan's poster as well at this meeting. So as I said, we've got something like 1.3 million, more than 1.3 million interferograms you can download. They're all available in a fairly straightforward way to get. That's about 3 times as many as we had in Fringe 2021. So we're really in a kind of production phase of these interferograms. I should say we largely form these networks of plus or minus 5 dates from each epoch. In some cases, we've got some bespoke processing where we're adding longer interferograms, as Chi mentioned in her presentation. Here's the coherence across the Alpine Himalayan belt. You can see it's very spatially variable. We've got some beautifully coherent areas like Iran, and then we've got some areas of dense vegetation and desert with sand moving around that gives us incoherence. So it's quite spatially variable, some more straightforward areas than others to work in. If we look at Tibet in particular, I mean, these maps I think are beautiful. There's all sorts of information in these maps, but again, some spatial variation in coherence across the plateau. So what we do then is we take all those data, we invert for the line of sight velocities for each frame using LIXBAS. Yu Morishita's in the audience somewhere, or at least at the conference, so you can talk to him about that approach. We do that at 1 kilometer resolution to give us the kind of scale we're interested in for tectonics. So it's going to miss some of the finer detail, but it makes it kind of tractable to work on this kind of scale. We don't really need, for tectonics, we don't really need higher resolution than that. So overall, we've got something like 651 of these 250 by 250 kilometer frames, something like 155,000 acquisitions and 670,000 interferograms that are all going into this work. So it's a lot of data, a lot of processing that's been going on. The way we currently work on this is we remove long wavelength quadratic ramps from each frame because we're essentially, when we adjust the reference frames, we're resolving for those, so we don't really care about the long wavelengths. Since developing this methodology, there's been, of course, lots of advances in being able to get those long wavelengths directly from the INSAR data, and I suspect in the future we'll move to be doing that. But as things stand, we use the GPS then to tie it together. So we've got a lot of data now. So we've got the colors here show the length of the network for each of those frames. So we've got at least 5 years of data everywhere across the Alpine Himalayan belt. That's the ascending, that's the descending. It's a constant battle. You finish one area and then and it's yes. So it's a constant battle, and there's a huge thanks particularly to Yasser Magsudi for managing this system so that we're continually generating these interferograms, into Milan for making the codes work. So those are all the line of sight velocities. That's ascending and descending. This is plus or minus 20 millimeters per year. So we're hiding a lot of things. Some of the things that leap out, you can see some of the water subsidence signals in Iran, for example, some of the strongest signals we see there, which you see, of course, the same sign in ascending and descending. If we focus in on Tibet, you can see some features associated with tectonics. So here's the Altintag fault here. If you look at the color change across there, as others have shown, Dohua showed yesterday, you've got red-blue that switches signs showing you that it's horizontal motion across there. But this color scale is a little bit broad to see all the details we want to see. So what we really want is to actually get all these things in a sensible reference frame so we can start to understand and tie all this information together. So we do this joint inversion based on a code that we wrote that was written by Hua Wang, published in 2012, called VELMAP. And essentially what that does is we set up a triangular mesh and we solve for the velocities on each of those nodes. And we also simultaneously solve for the reference frame adjustment parameters. So it's a big inversion, essentially. And once we've got all of that, of course, you've then got information. You can go back to the original resolution of the interferograms. So if we just focus on Tibet, this is our latest velocity field model for Tibet. So we only use the horizontal GNSS in this particular inversion, but we can incorporate vertical if we've got that information and we trust it. The INSAR essentially refines and sharpens the east component. It doesn't do much to the north-south. As we know, we don't have much sensitivity there. And you can see the kind of broadly the difference in texture between that east-west velocity and the north-south velocity in those, and that's the sharpness is coming from the INSAR. The vertical component is also coming from the INSAR in this case. We put a constraint that the average is 0, and those are the smooth verticals that we need in order to be able to tie everything together and for the long wavelengths to make sense. So those are our mosaics, ascending and descending velocities. Obviously a different sign, so Tibet is, there's a lot of east-west motion as well as the north-south convergence, and that gives you an opposite sign in the ascending and the descending. Once you've got that reference, so these are referenced back at the full resolution that we put in, so back at that 1 kilometer resolution, and that's the prediction from the VELMAP model. So the nice thing about that VELMAP triangular mesh model is it gets rid of some of these noise features that people have been talking about. So a lot of those can't contribute to the horizontal velocities. It gets rid of any short wavelength things. So most things in here should be tectonics in that model. And it fits the data pretty well. There's a lot of short wavelength features in the residuals, but probably these are largely non-tectonic. From that, you also get the strain rate fields derived from the velocity field model. So those are the three components of the horizontal strain rate tensor in A, B, and C there. And in D, we've got the dilatation, the maximum shear strain, and the second invariant, which is a measure of the magnitude. And I'll talk about what these mean in a bit later. Just an obvious question is how much impact does the INSAR have on this inversion? So what you can see here is the eastward velocity and the shear strain rate with and without the INSAR. And you can see what it's doing is it's really focusing things in on some of the big faults here. So it's making the strain rate along, for example, the Altin-Tag fault much more consistent along strike, and it's really just sharpening up that entire strain rate field really nicely. So we're also interested in, rather than looking at ascending and descending geometries, also interested in referencing that into looking at the east-west and the vertical velocities, essentially. So we do this sort of standard pixel-wise inversion here. We're assuming the north-south velocities that we get from that mesh inversion are correct, and we're combining all that, and that gives us these INSAR resolution east-west velocity fields and vertical velocity field. So again, a really beautiful data set. You can see very nicely, even just looking at this without thinking about the strains, you can see these quite strong changes in velocity associated with some of the big faults, like the Altin-Tag fault, the Kunlun fault, and others. The vertical field, as Chi mentioned, is a bit more variable. There's lots of contributions in the vertical. There's probably also some phase bias, which largely maps into the vertical. You can see some short wavelength features associated with resource extraction, but there are some long wavelength features there that I think are genuinely tectonic. But there's some work to be done, I think, to disentangle the noise contributions, the hydrological loading contributions from the genuine tectonic contributions here. But there's some tantalizing features in that vertical field that I'm not going to say much more about. Let's focus on the strain rates. So what are the key features we're seeing in the velocity of Tibet? I think the big obvious one is we're seeing this focused strain on a bunch of major faults. So really the big faults are the ones where we're seeing the concentrated strain. We're also seeing some long-lived post-seismic from the Mani earthquake, the Kunlun earthquake in particular, potentially also around Yuchan here from 2008. Even though that wasn't a strike-slip fault, there seems to be a concentration of strain in that region. We've got regions of low strain. Again, these were known about beforehand. But within the plateau itself, the central, south-central plateau, it seems to be fairly distributed, the strain. If we look at the dilatation field or the dilation field, I've asked lots of people whether there's a difference between dilatation and dilation, and nobody seems any the wiser. If anyone actually knows, then please tell me. I apologize if I've got it wrong. I've used both on this slide just to cover all bases. But the south-central, so central Tibet is basically extending sort of perpendicular to the collision. And then we've got these areas of contraction, obviously around the Himalayas, also in the northeast region and in the Tian Shan, as Chi showed as well. If we look at how to model that, and you can read a lot more about this in this preprint paper and also in a companion paper with work done led by Jin Fang in the audience, who's done a lot of this work on modeling. If you want to try and model this with a dynamic model, you need a combination of continuous deformation, but also some focused deformation around the faults. And those faults seem to make quite a long wavelength difference to the deformation field. They're not just influencing the area near the faults, which was, I guess, my prejudice before we did those calculations. They have a long wavelength influence. So I'm just going to end by sort of showing a few. How long have I got left, Chi? 1 minute. 3 minutes. I was 5 minutes late when we started. Thanks.
Sure.
Okay.
Fair enough.
Okay. Right, so I'm just going to quickly just highlight a few results. So you'll hear more about some of these later in the next talk in this area. But this is work we've done in Turkey. This is published. I'll flick through this. But the strain rates here are very similar to the most recent seismic hazard model, which was derived independently. And if we just look in the area of the earthquake, as others have shown, there was strain accumulation in that area that you see very clearly also in the GNSS data. I also want to highlight work by Andrew Watson and Jessica Payne, who've been doing these, looking and analysing these velocities across all of Iran, and there are posters on this in the poster hall, so I encourage you to go and see those posters as well. Similarly, Jin Fang has done a really beautiful detailed study in southeastern Tibet, and they're looking at really refining those networks, doing a lot more work that you can do when you're trying to do the whole plateau. Number of things you see here, most notably this very high strain here. This is an area of fault creep on the Zhenshuhe fault. But also, one thing he's done, and you can look at his poster, is compared it to a block model in this region with the block boundaries defined before we had the INSAR. And you can see a number of areas of misfit. For example, here, that's a block boundary. And as soon as you put a boundary in, you get strain on that boundary, but there's no strain in that location in the real data. So go and have a chat at his poster, really interesting results, I think. We heard also various results already in this meeting from Qi, we heard earlier, Dohua yesterday on the Altintag fault, and Lin Shen has a paper in review, which I'm sure she would share if you have detail. The interesting in Lin's paper, as she's not presented at this meeting, is there's quite a variation in the degree of localization of strain on the Altintag fault itself compared to strain in a broader shear zone, and that seems to vary along the fault. So just a quick outlook. I think this is a really exciting time for tectonic INSAR with the Sentinels and the future generations of those missions, the Roselle and the Harmony missions, and NISAR coming up as well. So it's a really exciting time. So just to conclude, we can combine lots of data, map tectonic strain now over really large areas, and it's really thanks to the large open archive from Sentinel-1 that's made this work possible. We get good results for the automatic processing, and when people put the real effort into refining that in smaller areas, we get even better results. And they're telling us some really interesting things about the geodynamics. So I shall leave it there. Thank you.
Great. Thank you very much. Are there any burning questions which we can ask now? Otherwise, I think Tim gave us like a very nice outlook and overview, which might be a very good introduction to the roundtable discussion. So any questions specific to Tim's talk now? Oh, yes, there's one.
Just a bit neat speaking. I was wondering, you guys are fitting heavily to the GPS, but then you said, I guess, so by that time, the GPS and INSAR are aligned. I would have expected that everything is the reference frame already. So why in the inversion, you still, you said that you guys are inverting for the reference frame rotation still? Maybe I'm
quite, so the microphone's quite boomy, isn't it? So we're inverting for the, why are we inverting for the?
Reference frame.
Because, well, I should be clear actually, we're only adjusting the reference of the INSAR to essentially it ties it to the GNSS. But if you do it we do that as one big inversion rather than frame by frame. If you do it frame by frame, you don't necessarily get consistencies between the frames, and also there are frames with very few GNSS in there. So if you do it all together, then you get the benefit of tying, a frame in the middle that has no GNSS in it is still tied into the reference frame. So we do it all together for that reason. Does that answer the question?
Thank you, yeah. My misunderstanding, I thought you were double doing the...
No, we just do it once. So we flatten everything, and then we invert in that joint inversion for velocities and reference frame.
Okay, thanks.
Great, okay.
Thank you.
Thank you. So now let's welcome our last speaker, Chris Rollins from GNSS Science, talking about strain rates in the Anatolian Caucasus region from Sentinel-1 INSAR and the GNSS, and the quantitative comparison with earthquake catalogs.
Okay. Hi, everyone. Thanks for staying to the end of the session. This is work I've been doing too slowly over the past 4 years and really need to write up. From 2019 to 2021, I was a postdoc at Leeds, and this is the work that I started there and kind of am continuing when I can. And it's focused on the Anatolia to Caucasus region, just shown on Google Maps here. Most of you might be familiar with this scheme by now, especially from the session this morning, but the tectonics of Anatolia and the Caucasus are kind of driven by the Arabian plate impinging upon the Eurasian plate. Let me just do this. The Eurasian plate from the south, and Anatolia is being squeezed out to the west, sort of like if you're trying to squeeze a seed out of a watermelon with your thumb. Arabia is your thumb, Anatolia is the seed, at least that's one model of it. And then the Caucasus are also being built by this collision further to the east. Anatolia is also being pulled towards Hellenic subduction, so there's extension going on internally. But as you'll see, a lot of the motion we can see is this big wholesale block rotation. And then the Caucasus mountain building, it builds some very high mountains, including Elbrus, which is about 18,000 feet, is the highest mountain in Europe. And a lot of Anatolia's wholesale motion with respect to Eurasia and Arabia takes place along two strike-slip faults that are conjugate, the North Anatolian Fault and the East Anatolian Fault. North Anatolian Fault being right lateral, East Anatolian Fault being left lateral. The East Anatolian Fault no longer needs an introduction for the worst possible reason. It's the earthquake, it's the fault that ruptured in the 7.8 earthquake earlier in February this year. And also in an earthquake of magnitude 6.8 in 2020. And then the North Anatolian Fault has had a earthquake sequence of its own that's caused a lot of fatalities as well over the past 120 years. It was kind of kicked off by a 7.8 earthquake, like the initial one in February, in 1939 in a city called Erzincan, and that started here and I believe propagated to the west in a sort of tragic parallel to the 2023 earthquake. A blizzard dropped in 2 days after the earthquake and basically hampered rescue efforts the same way that happened after the February earthquakes. Then there was a westward unzipping of the North Anatolian Fault throughout the remainder of the 20th century, culminating in the devastating Izmit earthquake, 7.6 in 1999. And there's an unruptured gap south of Istanbul along the Marmara segment that's received a lot of attention and a lot of anxiety, understandably, since this has all been going on, but especially recently. And so we have these devastating earthquakes. Istanbul is threatened by them, possibly going into the future. Turkey is, it's maybe doing the best it can, but it's got infrastructure problems everywhere. And so, one thing that we can try to do to help is try to figure out what's going on year by year, kilometer scale in terms of the tectonics and the tectonic loading, and can we see that from space? And then going from that into what might that imply for earthquake hazard. Can you guys hear me okay? Am I too far? Okay, great. All right, so here's what we can see from space, kilometer by kilometer, or I think this is multi-looked, but this is from LIXBAS, which Tim explained. This is the COMET's INSAR processing service, and these are velocity maps. And so each of these is a frame, so there's a number corresponding to the frame. We have 83 frames total that we used. This is a pastiche of a few different processing efforts that Yasser and Milan have done over the past few years, and I just picked the least noisy looking one in each frame, kind of in a not particularly sound way, but just based on eye for this purpose. But essentially, you see a lot going on, and then this kind of gets to the question Haresh asked Tim, which is, you don't see a lot of like wholesale Anatolia motion, and the reason is that all of these frames all these velocities are referenced to a 0 point in somewhere in each of these frames. So frame 14 might be referenced to a 0 point right there. And so it doesn't know that it's in Anatolia, it just knows how fast stuff is going with respect to that point. Similarly, frame 27 doesn't know it's in Georgia, it just knows how fast stuff is moving with respect to whatever reference point. So we need to unzero these frames by tying them to a GNSS velocity field that knows about Eurasia's motion relative to Anatolia and vice versa. You can see some features that do pop up even without sort of de-zeroing. This bullet hole here is the Konya Basin, which is a giant agricultural or hydrological center. And you think you might be able to see some things coming down in the Caucasus over here, and some signal along the North Anatolian Fault, which we'll see much better in a few slides. And then this is the descending track, and you can maybe see some signal along the East Anatolian Fault and over here. But we need to, again, unzero these. So to do that, we compile a big, we put together a big compilation of GNSS velocities throughout this region. And these are basically compiled from me trawling Google Scholar and various other things in the past 3 years, and just finding the global strain rate model compilation, which is Kramer et al. 2014, and then everything that was published after them or that they didn't use for some reason and deserves use. There's a few different criteria for how I select these. They gotta be published in a Eurasia fixed frame that they explain and that you can Euler pull rotate back into a Eurasia fixed frame of other studies, stuff like that. It's gotta be internally consistent. But yeah, so these are all of these studies that I use. This is a big new compilation from this past year that was super useful. This is another one that I just added a couple days ago from the same journal article, and then this one also. There's a few studies in here. I think there's 7 that I added in the last like 3 days. So when you apply some, okay, so the first thing that we do, and she kind of mentioned this, we up-reference the locations of these to the most precise locations by basically going through common station names, and I won't go into that, but basically, if some study publishes ARC1 station, but only rounds the latitude and longitude to 2 decimal places, but another study didn't round it and has it at 6 decimal places, then we identify the similar name and move the 2 decimal place station to the 6 decimal place location. And then, so we do that. That matters more in China for cheese work. But we also do it here. And then we do some culling based on the total horizontal and vertical uncertainties. And so we're just trying to remove really bad velocities in a rigorous way. It's not always rigorous because we do some outlier removal by eye. And there's nothing sacred about how that's done, but I think we got most of the outliers that are really obvious. And so you can see that we start to thin it. This is actually fairly generous as far as criteria, because what we do next is average them and propagate the uncertainties fully into a combined uncertainty on each of these velocities. So it's a weighted mean based on the individual uncertainties of the individual velocities going into each station, and then we also do propagate the uncertainty formally. So we get this sort of nice even GPS velocity field across the Anatolia-Caucasus region. And you can see the wholesale rotation of Anatolia counterclockwise relative to Eurasia. This is fixed to Eurasia, or relative to Eurasia in the ITRF Eurasia frame, like the one that she showed. And yeah, then you can see the slowdown across the Caucasus, and that's, so Tim explained VelMap somewhat, but basically it's our in-house strain and velocity mapping program, and also solves for the other stuff that may not have been removed correctly in processing, such as orbital and atmospheric errors, and biquadratic and bilinear ramps if you want. We did put those into the model, just in case they remain in Lix-Bass velocities. So, and then this is our model mesh, these gray triangles. And so what VelMap does is solve for the velocity at each of these mesh corners, and then there's a strain interpolation step that happens after. So the next step is the part that's a little bit new. I should have made a slide about it, but I was too busy rerunning models at the last minute. But actually, Song Ho helped introduce this pretty well, which is in terms of model resolution and data resolution, like you don't have very much resolution coming from the GNSS in, for example, here. You don't have any stations. You have a lot of resolution over here. Now, one of the things that VelMap uses is traditional second-order Tikhonov regularization, where the roughness of this triangle mesh motion solution is penalized. So it's not too rough, it's not too disjointed. Now, that's generally a good idea, but if you picture a creeping fault, it's going to have a sharp offset with infinite strain. So it's going to over-smooth that kind of feature. And that's an extreme example, but there's always kind of a battle between, you don't want to over-smooth legit signals coming from faults, but you also don't want giant blobs where you have no data just because the model is floating between different possible realizations and has no preference for one or another. So what I did for this is you run a bunch of jackknife, which is related to Bootstrap. You run a bunch of jackknife samples of the GPS velocities, fit a VelMap model to each of them, and then take the median model at the end. In this case, I used 150 different random samples of the GPS sites, anywhere from only 10 velocities, or that was the lower limit that I imposed, to all of them, and it's just a random number. And you keep the sites the same, you keep all the velocities if you pick a site to remain in. And so when you do that and then take the median model, it helps beat down the sort of blobby effects that you get from undersmoothing away from faults, while also not smoothing too much along faults where you have an actual gradient in velocity. And so yeah, you get this output model, which this is colored by eastward velocity, reference to Eurasia, so you can see the westward motion of Anatolia coming up pretty well. And also a little bit of eastward motion in the Caucasus, which is consistent with the GPS and sort of guided by it. And then this is the north-south, and you can see north going to southward. So that's, and then the slowdown across the Caucasus. And then this is the up, which it's a continual battle to keep this not too rough. And this is, it's sort of an art, if I were to call it that, to, you know, do this in terms of smoothing versus bootstrapping and how many bootstrapping or jackknife samples you want to run versus your mesh size versus your GPS and INSAR uncertainty. This is what happens, by the way, if you don't put dummy sites that she was talking about. I tried not to, and I think I'm going to have to put one there because this corner of, I think it's Dagestan, is just, it just always goes up at 12 millimeters per year for no reason. But the rest of this looks fairly consistent with the GPS verticals, which are these colored circles. And then these are the original INSAR velocities. These are the unzeroed INSAR velocities in the descending track, and so you can start to see the gradient across the EAF and the North Anatolian Fault come up pretty well here, and then also some of these signals across the Caucasus Faults possibly, and that one. And then these are the ascending track original velocities, and these are the unzeroed ascending track. It doesn't look as convincing. I think this frame we need to work on, and I just realized that this morning. But there's a lot of good stuff coming out of it. You can see this gradient across the greater Caucasus Fold and Thrust Belt, which we'll see in a second. Actually, we'll just see it right now. This is the strain, the second invariant of the strain rate that you get out of this model. And so this is what we care about because it's related to earthquakes, because earthquakes release strain, they don't release velocity. So this map has a lot of interesting features. The North Anatolian Fault is the big player in strain accumulation, as kind of was already known. We see some sort of spotty stuff coming down the EAF, and it is non-zero in the area where the 7.8 earthquake occurred. Let me just see how I'm doing, okay. And then the greater Caucasus Fold and Thrust Belt shows up pretty well. And we think we see some other features in Western Turkey that may be phase bias, but it may be legit tectonics. And I'll just speed up. So what we want to do is relate this to earthquake occurrence in a quantitative way. So what we do is compile a combined earthquake catalog, sort of the way we do with the GPS, but just with earthquake locations. trying to pick the best for each given earthquake based on what different catalogs are good at and specialize in. And so we put together this regional catalog for Anatolia and the Caucasus. It goes back to the year, I think it goes back to 342 BC, thanks to Marco Bonhoeff's catalog, which we, along the NAF, which we used. You can see to first order the locations of earthquakes and strain agree pretty well. Of course, the NAF dominates that correlation. So in some places, you get earthquakes off in the middle of nowhere in terms of strain. The Dead Sea Fault doesn't come up as well because, well, the INSAR is less sensitive to it. I know Andy Hooper and his group have been doing a lot of stuff that might help with that in the future with north-south. And then you can see the Greater Caucasus Fold and Thrust Belt. This is probably a very incomplete catalog, I've realized over here. And this is capped at, this is magnitude 5.5 and greater anyway. But we can make this more quantitative by going to turning strain rate into moment deficit buildup rate by just, Dave was talking about this earlier, but you just assume that the strain is continuous down to an effective locking depth, and you multiply, you integrate over this volume, multiply by the shear modulus, and you get to moment deficit accumulation, which can be compared to moment release in earthquakes. This is our locking depth grid. This is preliminary, but basically this is Iqbal Hussein's locking depths across the NAF. We assume 15 most elsewhere because I haven't looked at it yet. 5 on the northern or the northeastern part of the EAF that's based on Canton Blettery's work, and then 10 for the extensional part of Turkey, that's just a guess, totally just a guess. But yeah, so then you can convert strain rate to moment deficit buildup rate, and then you can start to look at individual faults and whether the moment release in the catalog compares to how it compares to the moment buildup we see from the geodesy. So if we isolate a plus or minus 60 kilometer sort of sausage around the NAF and look at earthquakes versus moment deficit buildup rate, that's the deficit buildup rate per year, and that's the moment release rate in earthquakes since 1900. So it actually is almost in moment balance since 1900. Now we know that the last 100 years along the NAF are not, it's an earthquake storm or earthquake cycle, and there's probably a silence that happens in between each of these. There might have been, a 250-year gap since the last giant earthquake in 1668. So we want to integrate a little bit further back in time to get a more balanced picture. So if we go back to 1450, which is when the Ottoman Empire was kind of consolidating and probably record keeping and record communication into the future was improving throughout Turkey, we can look at earthquakes, giant earthquakes since 1450. It's actually behind in moment deficit buildup rate. There's a few reasons for that I probably won't have time to go into the details of. But if we look at the EAF, if we go back to 1900, it is way ahead of moment deficit buildup rate. It's 2.5 times it. And if we go back to 1450, it's actually in moment balance. So again, this catalog is probably very incomplete. This moment deficit and strain picture there's a lot of work to be done to refine this with some of the methods that Chi and folks like Dehua were showing, which helps localize this a lot more. But it's just an interesting, I think this is interesting that it's almost kind of in moment balance in the last 500 years. Tragically, it required the 2 earthquakes this year to have that be the case. And we'll go forward assessing the robustness of that more. These are kind of some of the things that might fall into it. And I've gone way over time, right? Well, yeah, I mean, so some of the things that complicate this comparison are, we're still aliasing some creep as seismic strain buildup, but non-tectonic deformation, phase bias, hydrological stuff. And so we might be overestimating the moment buildup rate. And then the earthquake catalog is probably not complete, especially pre-1900, although many teams are trying to make it better. And there's a couple of regional catalogs that I need to digest into this that hopefully will improve in that. And yeah, I'll just leave it with that.
Great. Okay, shall we have one question, if there's any?
Thanks, Chris. Great work. I just wanted to ask, I have loads of questions, but the one I want to ask you about is the two Dusche earthquakes, the one in '99 and the one last year. If you were to do a calculation of the strain buildup since the last earthquake to last year, does it equate to the moment release in the earthquake last 2022? Would it?
That's a really good thing to check. I'm not sure. This catalog, I think, only goes to 2018 because it uses what was the most recent ISC GEM catalog to do a lot of the since 2012. But that would be a good. That definitely would be a good thing to investigate. That'd probably be a good kind of lab-like test case for this kind of stuff. So thanks.
Do you find a correlation between the moment rate and the amount of smoothing that you put into the bell map?
I think it's a slightly inverse correlation. Like you over smooth. So the bootstrapping or the jackknife with under smoothing and then take the median was an attempt to leave in whatever seemed legit, especially from the GPS. So for example, if you run a GPS, I didn't show this, but if you run a GNSS only strain model, there's so much GNSS along the NAF that it almost looks the same. So that's possibly an okay result, but yeah, probably the most appropriate thing is to use methods like cheese or dehuas going forward so that are smoothingless and not model-less or more so. But the most appropriate thing for me to do is to write this up. It's been too long.
Okay, then we conclude this session, but I don't want to create a sense of ending and let you go because we have round table, right? Okay. So how do we do the round table? We are oh, okay. Why don't you, all the chairs come out? Oh, is there a break? Huh?
Yeah, I think that's a typo. In the other room, they just continued straight to the round table.
Yeah, it's easier to just have round table and break. Well, why don't we have individual break? John, you can go to restroom.
No, I just commented that there's already plenty. Subsequently, yeah, okay.
Thank you for doing that. Yes, I think so. I guess so. Like, yeah, there are 8 questions. Yeah, cool. Thanks so much. Amazing. Yeah, thanks.
there a giant sweat stain on my back that formed gradually?
No.
Like through the top?
No.
Okay.
The rock. The rocks. Yeah, that's right. That was neat.
Oh, I see. There was a Michigan State professor that he would just give lectures sitting in the back of the room just with a pointer. And I thought
Seriously?
That was, and I wish like
you could do that.
Yeah, like
Yeah.
we could take a mic over there. That was what I was originally thinking.
Wow. Just being cool, I guess. Yeah? That's okay. It's unusual because there's so many of us. I think other roundtables don't have so many people. I don't know why my Evernote is not styling. I'll just do it. What do you want? I think that this is supposed to be recorded. But you can also do that. It sounds good.
You're going to run this then?
Should I? Okay. We can take turns.
In the first one, we kind of covered that, right?
Yeah. It was just a way to prod people into giving controversial opinions.
Normally we get through about 4.
Yeah, that was what I was worried about.
So you're gonna ask the questions and then like go over notes sort of like psychology style.
That's what I usually do in meetings. All right. Let's begin. We have so many questions to get through. We're going to keep you guys here until we finish all of them. We are going to solve everything right now. And the first thing we're going to solve is we have the first 2 questions that we have are kind of related, and they're both sort of technical, and the rest of them are more about data sets and missions and recommendations and how those things can be improved. So there were a lot of talks that covered separating tectonic deformation from soil moisture in different terrains, in different landscapes. So the first and second question have to do with that. Do people, what have we learned from this meeting, from these past several days regarding how do we separate the tectonic deformation that we care about from the soil moisture effects that other people care about? Questions 1 and 2. Who would like to start? What are the best ways? In your opinion, what are the best ways? What do you do? Do you throw out interferograms you don't like entirely? Do you do some kind of modeling? If nobody has strong opinions, we'll just... You guys are like a high school class. Go ahead, Chris. 1 and 2.
Just to launch off of what John Elliott was talking about this morning, I'd love to. People might be already doing this, and I may have missed it, but have hey, is this a phase-biased pixel? Okay, ramp up the uncertainties on the deformation for people that want to use it for tectonics or for anything, I guess, kind of workflow. Where if you're less prone to, like Chi was showing the areas, and the Tian Shan is not prone to phase bias as much, but higher biomass areas I think are. So something sort of scaling on that in addition to, the unwrapping and where you are, and then just other sources of error, which I guess could all be added formally.
So you're saying you could scale your uncertainties based on loop closure or non-closure?
Yeah, some of the stuff in Western Anatolia in mine, like I'd love to just put like infinite uncertainty on some of the things that look like phase bias so that the model doesn't try to fit it and no interpretation does.
And would you do that by hand or?
Well, ideally not, because I'd probably screw it up.
Okay, yes? Oh yeah, we have microphones.
So we did a good test of just taking out the shortest and then the next shortest, so you can identify the most vulnerable pixels. That's a quick and dirty way. And then we've done these more seasonal, sort of longer interferograms of Tian Shan
and then there's empirical corrections that have been done by others, and then hopefully get to a physical understanding of what's actually driving these would be the ultimate goal, rather than having to throw stuff away or empirically guess it. Is actually, as a community, can we understand a bit more about the earth or vegetation and soil moisture? That would be the end goal. I think Rowena, I missed it because I wasn't here, but Rowena showed something as well as pushing towards that.
Yep. Yeah, some people were commenting that the soil moisture and things, those effects are not necessarily noise that we need to get rid of, but a signal that we need to understand. Signal that we need to get rid of. Okay. Great comments. Any other comments?
If I could just make one comment. I mean, I guess we discussed this, if those were at the previous session this morning, we discussed this quite a lot, and I guess it was a move towards having a workshop on this. So I mean, I guess we could reinforce that if we think that's a good idea.
Since we're, we're encouraged to give recommendations, so this is a recommendation to have a workshop.
And a test area study.
I mean, there's a corollary to that then. Are we worried if we go back to 6-day interferograms, are ESA wasting their time for certain areas of the world, or we still want to keep encouraging ever shorter? And then what happens when we do get to daily interferograms? Are we going to be more worried?
Right. We really want that frequent repeat, but it sounds like it can also be problematic. And does it get more problematic as we make it even frequenter? Scary question.
You know, I think Charlie Warner, someone showed an interferometric analysis of only sequential pairs of interferograms that really highlighted the soil moisture effects. It didn't look like tectonics at all. I don't know if anybody remembered that analysis, but I think it was in California. So that's one way to isolate the soil moisture part, right? Just sequential interferogram time series.
And then remove it if that is not what you're
remove it,
interested in, but
understand it.
Understand. And then okay, great. All great suggestions. Anyway, PCA methods, AI. All right. That would be that's all good ideas. Okay, if there are no other suggestions, if there are other suggestions, we can talk about it more. If not, we can move on to the more general questions, I think. Okay. So this is a hugely general question, number 3. What scientific advances do you envision will drive our community, the Fringe community, in the future? If you were to dream and imagine what you're going to do, what you want to do. Okay.
An understanding that the Earth deforms in a north-south direction.
Well, then you need a left-looking SAR and a right-looking SAR. They're simultaneous. North-looking SAR.
You have to make sure they don't collide.
What else? Sorry, struggling with notes.
So it's very nice to see this specialized INSAR stuff that we do, but sometimes I have the feeling we should connect more with other sciences. I mean, I'm trying to do this with seismology, and I saw we have this nice automatic systems coming up. But I think it would be so much meaningful if seismic data would be included right away. So there are things that yeah, I think we could look out also more for other products for these worldwide to really integrate what there is. Yeah. So I'm not sure if I'm now really overlooking a lot of efforts that are done already, but I think this is I think where we will gain a lot.
I think that's a great point. So seismology, seismological studies is one. What else?
Seismology is one thing that it's just a very small point and very concrete on the topic of the damage maps, for instance, Sang-Ho. There is a Copernicus build-up area layer, yeah, where you have 4 pixels, you know how much percentage build-up layer is. And one could use the damage maps to combine this to say, okay, we have damage where people live or where there's infrastructure, and then we have damage in like rocks. It could also be important because it can block roads and landslides and so on. But I think then these like damage our products, which is an INSA product. Yeah, when we combine this with something else, it could be so much more useful. And if this is combined by someone who knows like also limitations maybe of INSA damage maps. Yeah, so this is something where I see links that we may miss at the moment.
Sorry, combining damage maps with what?
Yeah, with population. Yeah, with we call it like exposure data maybe. I also, because I was playing with this a bit, we have blind spots, right, in these damage maps. We should communicate that. So there are areas that are never coherent, and I at least maybe I'm doing it the wrong way.
Yeah, for those land cover type that has persistent low coherence, you can use intensity information, and it seems to work well. One of the things that Eleanor is doing is to combining joint methods to utilize both coherence and intensity correlation in a way that you don't have to choose one of each depending on the land cover type, but to combine them so it always produces optimal performance.
So I'm stopping here because I don't want to offend anyone by overlooking things. But I think in general we should.
Well, a data set that makes sense to auto-combine is optical. Like if somebody can fly over optical imagery, and then that can be I mean, there's probably a bunch of methods for doing that. But, yeah.
But speaking of damage proximate, for this Morocco earthquake, I noticed that Lixar deformation map was produced quite quickly. And I haven't looked into details how to further, I mean, is there a way to reduce the latency? Because primarily because our processing time was the major contribution to the latency, but we got to the point now where even time series analysis, it takes only a few hours to generate that. Highlighting the latency from satellite to from ESA's Sci-Hub to show up. I wonder if Lixar has faster routes?
No, I think we use essentially the public access, but the biggest delay, I think, is obviously the earthquake to the overpass, usually, at the moment. So I think the biggest thing that would make a difference would be more satellites, more publicly available data sets. Whether that's commercial providers opening up their data sets kind of in a routine way or acquiring data after an event. I'm involved in a Earth Explorer 12 proposal, and I think some others probably in the room might be as well, for a geosynchronous SAR that would basically enable you to make a 24-hour interferogram potentially every hour, but it obviously you don't get global coverage. You stare at smaller areas. It also give you a different look geometry. So I think there's that latency. But I think by the time we've got Sentinel next generation, or Sentinel-1, we've got 2 Sentinel-1As. Right. Well, 1A and 1C or whatever it is. And we've got Roselle-1 and Roselle-2 and NISAR and whatever follows NISAR. Maybe the Japanese can open up the data sets as well. I don't know that.
That's happening.
Yeah. So all these things could. So sort of systems of systems that aren't just reliant on one satellite, that are actually genuine. Take whatever you can get. And that would be quite exciting. Eric.
Yeah, and along that line, I think it would be good to recommend that the commercial new commercial satellites establish some kind of background acquisitions, because they can acquire data after an event, but if there's no pre-event image, we can't use it for any kind of change detection or interferogram or anything.
Yeah. Yeah, they didn't for the Turkey earthquake, for example. There was a very nice one-day post-seismic interferogram, but there was nothing spanning the earthquake. That was from ISI.
And if we could use the opportunity to continue to recommend that ESA launch 1C as soon as possible, because it impacts both the science and then also some of these response mechanisms. So for many of these points, just reiterated.
Just to change the topic slightly, I think one longer-term thing that's going to be more and more apparent, it's already apparent in some of the talks at this meeting, is that we've been trying to get these static interseismic deformation maps, but the Earth really isn't static, and there was a nice presentation on Ecuador that showed that kind of really a sort of long-term change in the velocities before and after the earthquake, and we've seen that as well. There's saw in my presentation, you get these very long-lived post-seismic transients. So there's a lot of things, the thought of David's presentation on California, where it's one of the fundamental assumptions there, I think, when you're turning the strain into hazard, is that that's a kind of static strain rate, and it probably isn't. So
maybe moving all this to time series.
Yeah, and particularly exploiting, as the Sentinel time series gets longer, we've still got the ENVISAT data, we've still got the ERS data. It's really, really difficult to use those old data sets. Natalie gave a presentation, but it's really, for example, they've deleted a whole bunch of ERS data that was perfectly usable because it had a few % missing lines and didn't meet some quality. And so we couldn't find, for the Grosvenor earthquake, we couldn't find, even though...
And they changed the data format.
Changed the data format, it's all these things. Anyway, it becomes, so actually also, maybe it is a recommendation to make sure, at least with Sentinel, we preserve that archive and don't delete stuff.
Yeah, we'll also not delete any other ERS.
Don't delete anything else. What's LP? Oh, right, binary. Fine would be good. I'm a cassette person, really. You can get it all on cassette. Back an exabyte. I know. We looked in all the cupboards for the Grosvenor data. I asked people in France. I know CGG, when they were MPA, they processed it. Sorry, this is anecdote, it's not relevant. But they just threw it all away, because it's all online. And it isn't. Well, they won't be. Did you check that they were all online before you did it? No, there we go. They won't be. It is sad. But anyway, I do think that data preservation of these long-term archives, because you don't know when it's going to be important.
So that kind of, that's a good segue into our next question, which is that what are your biggest challenges when you're trying to do your research using the STAR data that exists today? And what, we kind of covered some of this already. We don't have maybe enough satellites. We don't have as much of an integrated system of systems that we would like to have. Maybe we could incorporate other data sets. Data set challenges. What are your biggest challenges now using INSAR? And what would you change? What would you like, if you can dream? What measurements are missing? Or what, yeah.
That's an LOS ambiguity. Where that goes.
I think the reference frame issue is important when it comes to the large scale tectonic studies. Because I remember when we were working for Iran, I mean, there were different GPS studies. They were all saying our velocity fields, this is based on Eurasia fixed. And how different the studies, they fixed Eurasia. It was different. So we should be careful. This is one of the challenges when we get the GPS velocities. Firstly, we should see if they are they have a unified reference frame in Eurasia. And then we go and then use them as a constraint for INSAR. Maybe Tim and his colleagues, they have done this, but if not, maybe in other studies also, we should be careful. We use Eurasia fixed GPS velocities and different reference frames, but this is also part of challenge.
That's a great point. Any others?
I
think I'd applaud your initiative. I don't know whether this is relevant to this question or another one, but something we can encourage. Maybe ESA could fund a comparison study because it's really important. These comparisons of different processing chains, and you learn a lot from them. But it's kind of dull, isn't it? Nobody really. It's much more interesting. I mean, it's much more. It's sorry.
Every Thursday at 3 p.m.
Every Thursday.
Midnight tonight.
Okay. Right. Because what I mean, your work and you presented it beautifully. There you go. But what I mean is, it's much more interesting to process a new area and get a new exciting result than to do actually the really important work of working out what we're doing wrong and learning from best practice.
Well, yeah, it's dull until it isn't. Like all of Jan Kagan's statistical seismology papers are like the most useful papers now, and I don't think anybody else, maybe 2 other people, wanted to work on that stuff when he was doing it. Yeah, it pays dividends.
It's okay. I wrote that down in the nicest possible way.
Thank you.
I'll try and help Tim and move this on. So a challenge, at the moment, we're sort of working in a batch mode. We've got our archive. It's almost a 10-year-old archive now. So we run it, for instance, to get our long-term velocities. And we'll produce velocities from that batch data. But the challenge now will be, how do we continuously update this without starting from scratch? How can we learn from the GNSS community to get the time series? The approach we certainly adopt at the moment, you end up doing it again. But can you do that in near real time, or do you wait until the next PhD student does a batch of 4 years? It's how we address it as a community, how to keep it updated without it being a monumental effort to redo it.
Yeah. And you get down a certain route with an approach, and you think, actually, if you're starting from scratch, you'd probably start it a different way. But reprocessing 1.3 million interferons or whatever, it's not. Yeah, it's a big job to start again. But there are lots of other approaches for processing that have been proposed. The idea of doing these corrected, what we call these SLCs that are geocoded, INSAR ready SLCs. And so different ways of doing it. I think that probably weren't around when we started our system, but would be that people are doing now, and I think maybe are faster for reprocessing as well.
Well, aligned to that is the ARD analysis ready data sets. Some of ours, we try and provide stuff, but I wouldn't say people say it's ARD. And there's quite a few initiatives who see us to try and do that, and I don't think we're there as a community.
Well, good points. Any other question? Any other comments on this question? Data sets? Number 4, technically, we've talked a lot about different things. So challenges that you face in terms of the data sets that you have to use, whatever that means to you. Yes?
I'm not sure if anyone has looked at this. So we have now, as I learned from plots, not from my own experience, that there are larger baselines now for Sentinel-1A because of some problem. And do we know how much this affects coherence? Because there's also this want from other communities, of course, to increase the baselines. And so I'm just wondering a bit if we could make a comment that we would like to still have like small baselines for coherence and frequent revisit and so on. But it would be very interesting actually to see if it has an effect. I mean, it comes on top of losing 1B.
Yeah, I think we should make that point, that we want to keep the shorter baselines, and ESA is already thinking about that. It's the solar cycle that's increasing the baselines, and they talked about perturbing the orbit more often, although then it shortens the whole span of the satellite. But still, we should say something about keeping baselines within 300 meters.
Yeah, maybe for this, so I guess it's about like height estimations for other communities with the longer baselines. But now the question is, are like 500-meter tube, is this helping or is that not helping? Is that enough? So
they can get their own satellites. Nothing.
So we are happy for him.
Yeah, similarly, I think I raised this on Monday about, for Sentinel-1 Next Generation, this idea that you could, or for Roselle, I think they're thinking about having a bigger overlap between the bursts that would allow you to get the north-south out. But it seems, they don't seem particularly keen on it. But Andy, you know more about it.
Yeah, well, so actually I think potentially it's possible for next generation as well.
Okay.
So I think we should make the recommendation for both Roselle and NG that they do it.
Yeah, certainly for our community. I mean, they said, oh, we've got to balance communities, but if we don't actually at least ask for what we want, then there's no chances, let's say.
It's when we're up against the Copernicus service.
Yeah. But if you get 3D data without having to launch Harmony companion satellites, that would be much better.
I thought Roselle was going to use scan on receive, so it's not TOPS mode at all.
No, it's still overlap. It's scan cell, but it's still have overlap.
Yeah, if it's anything like NISAR, then it's complete. There's a lot of there's no burst, so it's continuous overlap. You can do MAI anywhere you want. There's no bursts to only have limited overlap.
Malcolm said it is possible.
Well, there's C-band, and then Roselle is L-band.
But then
NG is C-band. Yeah. So there'll be 2 C-band and then Roselle in L-band, all in the same orbit. So do we have any thoughts from our community about the orbits for those satellites, whether we want, you've had your hand up a long time, sorry.
Yeah.
Go on.
Yeah, just I have I remind that they say that regarding the tube in which the satellite goes, there is a trade-off between the size of the tube and the length of the mission because of the consumption. So we should keep in mind that if we ask for a shorter baseline, we'll have a shorter mission.
Yeah.
There's a cost always.
Tricky trade-off. Yeah. But they've extended the mission by being really slow in launching 1C and 1D.
I have a silly question on the north-south ambiguity and look directions. Is it possible to make an INSAR satellite that spins like a top as it goes across the surface? Or why wouldn't that work?
It's a recommendation for SDC.
Yeah.
One of the echoes had that.
We had a mission proposal called SuperSAR that had a forward beam and a rear beam. We've done that. But the overlap does it.
But I think it's quite likely if Harmony is successful that others will have companion satellites too. So we could have Roselle, Harmonies, and G satellite, and G Harmonies.
When is Harmony launching?
2030.
2030.
I was going to say, I think, Katya wanted me to comment, but pretty much everything you guys said, right? So, Harmony will give you the multi-look, or multi-sprint, I should say. So that will give you the 3D. You could do a spin like a top, but then, you will be spinning like around the equator in a sense, or whatever, so that, you won't get the global coverage, right? You could do weird orbits, but then it doesn't really get the routine coverage that we're used to from, sun-sync things. You can do inclined orbits, which I think Katya could talk about, and what's the benefit of those, at their coverage. Yeah, one nice thing I didn't hear too much expressed in this session is that the multi-sprint will also help with the challenge of troposphere, maybe. I don't know if we talked about that, but yeah, just some thoughts.
So on that note, I was wondering if anybody has any, since you mentioned it, has anybody thoughts about what's more important? So whether it's global coverage that's important, or it's improved measurements, and what if it's a trade-off? Would you like more localized coverage that is really fancy, maybe has 3D deformation and also has atmospheric removal and also has other things and frequent revisit or something like that? Or do you think that kind of continuity spatially and temporally is more important than that.
Well, as always, you ask for both, but we want
you have a
everything.
mic.
I think it needs to evolve, so it needs to improve. So I'm not sure that are we seeing enough shortening in latency, shorter revisits times, and slight improvements in spatial resolution for the non-commercial satellites, that they can at least start to approach what is now possible with commercial SAR. Is the gap too big, and is it going to grow over the next 10 years, where we are working with a couple of satellites as a constellation that gives us more coverage, but at low resolution, time and space, and will there be a gulf with these commercial operators then, that we might miss out as a science community, that we can only do very small bespoke areas if we can get hold of the data, either through paying or with partnerships with these organizations? So is next generation, is it coming soon enough to give us meter scale SAR every day? I don't think it is in my career, and
But I
I'd
don't
like
think
it before I
commercial SAR
retire.
is going to do that either. It will do for your one area that you pay for, but they're never going to have the global coverage that we need for tectonics. We need all the tectonic areas at least, and we also need a background because earthquakes can happen in weird places. So I don't know.
Can I ask, what would be the orbit and the coverage and revisit time after 1C and 1D launch? Because in the past, we only have 2 satellites, and then soon we'll have 3. How would that improve things?
So sadly, the plan is to park 1A when C and D are up there, so we'd only have 2 still. But recommendation should be not to do that.
But we will have NISAR. Okay, so recommendation not to park 1A until it's just dead. Okay, that's a good recommendation.
It's just about saving money.
I think a recommendation for Harmony would be to make it look really complicated. I know we can all do the suns and 3D deformation and what have you, but it would be much easier if that was done for us and we could get the level 3 products whether quickly, so whether that's topography change or 3D deformation, and that was somehow done. So if we can recommend that. There's some processing done so we can get those high level products.
Yeah, if I can add something there. So we're talking about gaps in coverage spatially and temporally. I think maybe the elephant in the room here is if Sentinel 1A goes down before 1C goes up. And Tim over there is grimacing a little bit. I think for obvious reasons this would have pretty big consequences, and maybe it's good to think in advance what impact this would have on different areas of research. Because, yeah, of course, the gap can be filled with some of the other providers, but then you're looking at different geometries, different wavelengths, and you've got a gap to fill over the entire world. So then some of these big continental projects are going to struggle if you ask TerraSAR for data over the whole Anatolian region.
I mean, we've kind of had that experience because we had, ERS and we sat on nothing for a while, right? Till Sentinel. Wasn't nice.
I mean, what was good was it gave an opportunity to light some stuff up. Rather than carry on processing.
Okay. I'm not going to write that down.
No, right, no.
Silver linings.
Yeah, I don't know whether there's a pre-deal that can be done with RadarSat Constellation mission or whatever so just as a contingency, so that they don't have to go into 6 months of negotiations before. In that.
They move pretty quickly with 1B.
But what to do what?
Oh, so they do cover the Arctic.
Okay. Or whether they do tectonics.
Yeah, I think they shuffle things around.
I wanted to add a couple more things. In another meeting, we were talking about the multistatic missions. It was highlighted that the simplest SAR modes are more companion-friendly than, StripMap is more companion-friendly than ScanSAR, TOPS, and so on, because then you need to sync the pulses. So I think if that is one way to push forward the science, multistatic, that might be something to note also, to make it easier for companion satellites. And then the other thing I wanted to add was earlier you were talking about commercial systems collecting background acquisitions before disasters. So one thing maybe we as a community can do is guide them and say, hey, over this volcano or over this fault zone, this is a typical decorrelation we expect for X-band, so please collect it by, every so often. And then that would give them both an area to prioritize and also how often they should target that.
So we're asking them for routine coverage of certain specific areas.
We may not get it, but the asking is free, right? So.
Yeah, along that line, I know the Polar Group has an organization to consult with the space agencies as a group, and we don't have that. We don't have like an advocacy group. But maybe we should form something like that.
That's a good point. That's a really good point.
Yeah, I think when they designed the tectonic area mask for Sentinel, it was basically, they talked to us and we informally talked to some other people and we came up with something that seemed sensible and then adjusted it where needed. But if we could do that in a more formal way, more inclusive way. Yeah.
That's a job for us.
Yeah. They could give us some money to do it. It's another one of those boring jobs, isn't it? But important.
Not as boring as comparison.
Are any of the upcoming satellites dual
I'm not going to live that one down.
Sorry?
Are any of the upcoming satellites dual band?
Just NISAR.
Okay. Can we tell NISAR, look here with this band, don't use that band, it's going to be garbage.
Too late.
That ship
And
has
then
sailed.
switch when it's in this region.
I don't think we can do that anymore. Well, maybe we can. Maybe we can't do it. We have to we just tell them when to turn on a band.
I mean, are they going to do both of them?
In some regions, no. Only in select.
Right.
It's all decided, I think.
Won't
I don't
they?
think this-
They will. Yeah. Yeah, that's true.
I think there was in the opening presentation, there was a mention of this, the fact that they have, because of our request for this community, the INSAR community overall, that the acquisition schedule is very boring. And I think we should reinforce the fact that we support boring acquisition schedules. It's really important.
And research.
But boring, important. But the same again and again, long periods of the consistent. Well, it's boring for the engineers, isn't it? It's fantastic for us.
Yeah.
But,
engineers like more fun.
They like to tweak things, but we don't want that. Pick one and stick with it.
This is a great conversation. Any other suggestions? We have other questions that are geared towards, for example, disaster response. So we're talking about things that we would like to have for our research. How about we switch a little bit and talk about what we need for disaster response? Is that the same? Is it different? Do we want something else? Same stuff?
We did sort of touch on it, didn't we, earlier?
Yes.
Reduce latencies, more
We did,
satellites.
Cheryl and Lynn, those are the guys who worked at the front line of generating the maps. Do you have any complaints, suggestions?
I'm curious, who predicted the casualty and then how? So, yeah, based on your map.
So we always try to stay on a comfort zone of producing first raster image rather than jumping into creating information. And then we started creating a shapefile, which is vector. It's easier for geospatial community to overlay and produce number of people affected. It's partly because the world population density data, they evolve quickly. So if we just host it, it becomes dated quickly. So you want to always tap into the up-to-date, the latest data set. So that requires additional bandwidth to pay attention to with limited number of people working sleeplessly, tirelessly. And usually the user side, they are usually a GIS team. And they know what is the most hip, most accurate population density or infrastructure. So we tend to leave that part to the GIS team, users GIS team.
Unfortunately, somebody looked at the schedule, so otherwise we could have stayed here forever. But maybe let's wrap up. I think we've covered most of these questions at some point, one way or another, and let's just see if there are any other recommendations that have not been mentioned regarding data, missions, workshops, anything else that you can think of that we can make recommendations about.
I didn't hear the word license. For disasters especially, I think licensing is important, right? That the data gets out for openly and in a very short time frame so that...
Right. So what we produce, for example, always put in the public domain. It's open and free. For that reason, it's actually not the best business model. It's very difficult to sell products for disaster response. One thing I wanted to mention is that we used to have easy access to Cosmos SkyMet, which is has a very low latency system. But unfortunately, we lost connection at some point. I know why, but afterwards, I didn't make great effort to reconnect. But I don't know if you happen to have some connection to ASI or maybe it should go through civil protection. If we can reconnect to Cosmos SkyMet data access, I think it will be really helpful to reduce latency.
So regarding datasets, some people were using data that was quite old on the one hand, and on the other hand, with high probability, the satellites takes military sensors. So could we ask ESA to push the military to release old data that could be useful for us and not yet useful for them? Because everybody else died already, for example.
Sorry, push them to release what data? Military. Yeah. It's kind of happened with GPS, right? Eventually.
Yeah, I want to touch up on Sentinel next generation a little bit because ESA is really in the discussion what to put on that mission, and they are talking about having other sensors also and radar sensors. So it's of course very important to have the continuity, and maybe we can have a more overlap to get more north-south. But I mean, what about a mirrors type of instrument? I mean, it can really help to beat out the noise when it's not cloudy. And I think this is maybe something that, or we should at least start to think about. I mean, if they're in the process of potentially putting more sensors on the satellite, what would we like in addition to the radar?
Mm-hmm.
So, and now is the right time because they are still in the kind of, well, they're not even in the design phase yet. I think they're just kind of bringing things up.
So I think that's a very good point. Could you remind us exactly how? I remember Maris was very useful.
Yeah,
how
I mean,
it was
you
useful?
can get a water vapor estimation from when it's cloud free, and it really greatly helps to beat down the turbulent troposphere in cloud free areas where you have still a lot of humidity and turbulence. So it is You were smiling.
I just said like Saudi Arabia, for example.
For example.
Not Singapore.
Yeah.
Oh, yeah. Also Singapore if it's not cloudy.
Okay, that's a great question. Anybody have any opinions on other instruments we could put on satellites? It's already a pretty good comment, but how much to improve it? 1 hour.
Oh,
Every 5 minutes.
So,
Everywhere. So.
I think this geosynchronous SAR would do that.
Mhm.
So you would, but you'd have to, anyway, but yes.
Maybe addition to
What's the orbit time for Sentinel? No, not the repeat pass time, but the time it takes to circle the Earth. 90 minutes? Yeah, so just say hardest starboard, and just get it to go to the place.
Just one more point with Sentinel. If Sentinel-1A will still be alive and C and D come up, I mean, where do we want to? I mean, they put them. I mean, C and D are going to be like A and B in a 6-day orbit, right? So what? But then we have Sentinel-1A. Would it be good to have 1 day or 2 day or a mix? If it was a 2 day, then can be a 2 day and 4 day and.
I think the same would be Roselle with the 2 Roselles. You know, if you've got 2 Sentinel, got the NG. You've got the NGs and the Roselles. I think my gut feeling is we want them evenly spaced, but I don't know whether other people agree.
Because then eventually, if 1A dies, but then you have like C and D kind of not evenly spaced, it might be.
No, they can be 6 days apart, but then A is there, so I mean we can adjust it with respect to A, the 6-day cycle.
Good question.
I don't know what the tectonics community would like. I mean, I think it would be interesting to have a possibility of having 2 day and 4 day, and, if Sentinel-1A is still alive.
Maybe get more of this biased estimated by using, you get a 1 day pair, you have some different lengths. You could maybe get the bias from the difference between the 1 day and the 6 days.
Yeah, I think having 1 day is quite beneficial. I also think it may be that having Roselle 1 day behind might be more helpful for estimating its effects as well.
Yep.
But then the tropospheres would be correlated more.
All right. Any final recommendations? Because people, I think, want to. Okay.
Nice.
We don't have to go anywhere. We just stay here.
To the point of evenly spaced satellites, it's always a compromise. But I also would vote for something that where we can make discoveries, which would be something shorter, like 1 day or so, for very fast processes that we can capture every now and then. I think this could be very exciting.
Yeah, so if we want to make a case for them not to park it, maybe it's actually helpful to have some new.
Yes.
And maybe they don't have to take data when they're not pointing it at something if they want to save cost.
I think the ice community wants a 1 day repeat also, because the ice moves too far in 6 days.
So is that a feeling we're relaxed about it as a community? Some potential interest for 1 day, we're not against it. Yeah. Good.
Okay. Okay, if there are no other comments, you guys.
The
I'll
ETAT
let
thing,
you
you
guys
could write
go.
down that we want them to do ETAT for everything.
Yes.
But they won't.
I thought we kind of, already voiced that sentiment, which is why I skipped over. Yes. Anything else? Any other comments from the leads, the chairs?
Do we want specific format for ETAT?
easy for
Yeah.
Which ones? Which additional? Oh, I see, okay, got it.
I was going to ask the same thing for, can we predict landslides before we get the repeat pass and set up a preliminary disaster response model? But Jack's question first.
So is the recommendation to provide, let's say, a land cover map as a layer in a data set? Is that what you think would be useful?
Yeah.
Okay.
Yeah, I guess so. Just something where we could potentially start to see if we can correlate any of these signals that we are seeing to the land cover.
Well, there is a Copernicus land cover map already, isn't there? When it's available.
There's no global ones, though, are there?
Yeah.
Oh, well, in that case, done.
I mean, they don't always correspond to the sort of inside behaviour, so it might be the one that was informed by coherence and things might be interesting.
Group at, what's his name, published a global coherence map from Sentinel-1 a couple of months ago. So it exists.
Okay. Meeting adjourned. Thank you.